Why should you consider taking this course? If you want to work with almost any service in IT, an understanding of networking is required. If you want to work with the cloud, Microsoft Azure, Amazon Web Services, the Google Cloud Platform, or any other cloud provider, you have to have a deep understanding of networking because you will be creating virtual networks, subnets. The resources you create in the cloud have to reside on a network, so that is extremely important. Many of the policies that you create will be applied at the network or subnet level in the cloud. If you want to be a systems administrator, you will heavily work with IP addressing, networking. Many of the services you would configure, like DHCP, automatically assigns IP addresses. You have to have an understanding of how that process works. You will work with DNS, the domain naming service. That resolves names to IP addresses. So again, you're back to heavily working with IP addresses. And those are common services that all systems administrators would actually work with. If you will work with any virtualization technology, that could be Hyper-V, VMware, Nutanix, or any of the other numerous virtualization technologies that exist, they have virtual switches. All of the virtual machines you create have to have IP addresses. So again, you are heavily involved in networking. If you directly support users, whether that is desktop support or help desk, part of your troubleshooting process is going to be network related. Even if you work with applications, this could be something like Azure SQL or just applications in Azure or AWS or even on-prem. For your applications to be reachable, they have to be accessible by IP addresses. And many of these applications do have their own security tools built in. Some applications like Azure SQL has firewalls that can be defined. Even if you are an applications administrator, you still need to understand networking. Your application may require multi-factor authentication based on where a user is connecting from. If they are in the office versus if they are at home, much of that gets tied back to IP addressing. So extremely important, regardless of what your role is or will be in IT, extremely important that you have a solid understanding of networking. We will use lots of different tools in this course. I'll show you how to configure switches. We'll look at configuring interfaces and other settings on those. We'll configure routers. We'll also configure a full simulated environment. So I'll configure my routers, switches, I'll put IP addresses on these end devices, and we'll make sure we have connectivity through our entire simulated network. We'll also use Wireshark, which is a tool that lets us actually capture network traffic. We'll capture traffic, then we'll analyze different types of traffic using this tool. We'll use PowerShell to run various commands in our environment, along with lots of other tools to give you hands-on experience with networking. In this course, we will cover IPv4 addressing, the OSI model. I will show you how to subnet, and we'll work through several exercises where you can practice subnetting IPv4 addresses. We'll also talk about different switch types, layer 2 and layer 3. We'll cover routing, and you will actually configure routers and switches with this packet tracer tool that you can actually download, which lets you simulate a medium network, a small network, even a large network. You can add different network components into this tool and go through the entire configurations. So that is an incredible asset for us. We'll also look at public and private IP addresses. We will touch on network address translation, also known as NAT. We'll look at flow control, how you configure clients for IPv4 addresses, the different options that exist to do that. We'll look at some PowerShell commands and traditional Windows commands for IPv4 troubleshooting. We'll cover Wireshark, so we can actually capture traffic. We have a download link for that as well, so you'll be able to run that on your own computer if you choose to, and capture traffic and analyze it on your network. We'll also look at how IP addresses are automatically assigned to laptops, desktops, mobile devices, just clients on your network by configuring DHCP. We'll look at all the benefits associated with that. We'll see how that actually works. We'll look at the installation and configuration of DHCP on different types of devices, whether that's servers or routers. We'll also look at how you can configure scopes in DHCP. We'll look at making it highly available, how you can maintain and even migrate the database of a DHCP appliance. In this course, we also cover DNS. We'll look at the name resolution process, the different components that you have in DNS. We'll touch on zones, records, client configurations. We'll look at how DNS ultimately resolves internet-based names through root hints and forwarding. And we'll also look at troubleshooting DNS-related issues, which can be pretty challenging to troubleshoot. So we'll look at some different methods for that. We'll also look at how networking is related to Active Directory and what you need to be aware of for that. Then we move on to understanding IP version 6 addressing. We cover why you would use IP version 6. How is IP version 6 different from IP version 4? What are the address types in IP version 6? How clients can be configured? How do these protocols, IP version 4 and IP version 6, how do they coexist on networks and on the internet? And we'll also look at some things to be aware of, some considerations for implementing IP version 6. And we touch on IP version 6 tunneling so you can get all this to work through the internet. Module 1 is understanding, implementing, and troubleshooting IP version 4. In this module, we'll cover planning IP version 4 addressing, configuring an IP version 4 host, and we'll also cover managing and troubleshooting IP version 4 network connectivity. When we're done with this module, you'll understand how end-user computers, whether they're laptops, desktops, servers, telephones, whether they're desktop phones or mobile phones, printers, if you have cameras in an environment that you're in, and various types of network devices, routers, switches, access points, we'll understand how all of these devices communicate with each other on the same network, if they're on different networks, and everything that's involved with making that communication happen. This module is great because it lays the foundation of some basic information about IP addresses and these different types of devices and the configurations we can define, and the modules after this will build on the foundational topics that we covered here in Module 1. In Lesson 1, Planning IP version 4 Addressing, I will cover an overview of IP version 4 settings. I will show you how to define subnets, and we'll also look at public and private IP addresses and many interrelated components to these topics as we go through this lesson. Let's start off by establishing what an IP version 4 address is in practical terms. All of these are examples of IP version 4 addresses. An IP version 4 address is always 4 sets of numbers separated by a decimal. So 192.168.1.1, that is an IP version 4 address. An IP address, short for Internet Protocol, is just a series of numbers that identifies any device on the network. Computers, or any device we should say, will use IP addresses to communicate with each other, whether that's over the internet, if it's on the same network or other networks, any type of communication by any of these devices, whether it's a laptop or desktop, if it's a phone, if it's a mobile phone, a printer, a server, all of these devices that communicate with each other will do so with an IP address. In this example, I have two PCs, PC1 and PC2. I have a phone, a printer, and a server, and you'll notice all of these have IP addresses directly assigned. So if I want to communicate between PC1 and PC2, we will communicate using these IP addresses. But what connects these devices to each other? This is a switch. A switch will connect any network device. That could be computers, printers, wireless access points in your network to other devices, and it allows them to talk to each other. It does this by exchanging something called frames. So if I'm on PC1 and I want to access something on PC2, it simply goes to the switch and it goes to PC2. It's like my connection point. There are many different types of switches. You can find switches that may have as few as 4 ports that are inexpensive. You can find switches that have 96 ports or hundreds of ports that may cost tens of thousands of dollars. Depends on your need, and depending on the switch, it can be very configurable. Something we talk about later in the course will be how switches can actually be managed. But for now, we want to think of it as a hardware device that's just connecting these computers to each other. Now, I'm sure some people are thinking, well, if I have an access point, then I'm not connected to a switch. Well, yeah, you are. If I have a mobile device here, or a wireless device, I'll say, and that device connects to an access point, your access point is going to connect directly to the switch. So you are still passing data through the switch, even though you yourself are wireless, you are just connecting to it via an access point. If you're on a smaller network like a home network and the only device you have is a wireless router, it simply means that device has this capability natively built into it. So even though it may not be called the switch, it still has that switching function, just embedded in one device. I also have a router in my graphic. The purpose of a router is to connect devices on one network to devices on other networks. Now, this could be the internet, it could be another network within your company, just to a different network. When you look at this, you'll notice this router has an IP address, 192.168.1.1. All of these devices here have this default gateway assigned, 192.168.1.1. Whenever you look at the IP settings on a computer and you see the default gateway is always the IP address of a router. Now, it may go by a different name. Sometimes it's called a router. Some places, I know some providers call theirs like a business gateway. It may be called a cable modem, but it has a routing function, whatever you call it. So what happens is anytime I need to connect to a device that's on a different network, that data gets passed through the switch and up to the router, and then it routes on to the internet. So for now, we just want to think of a switch as connecting different devices on the same network to each other, and a router connecting different networks to each other. This is a similar example, but let's say we are at work, and where we work, we have a campus. So we have building 1, and all of these devices are in building 1, and you have another building, building 2. All of these devices are in building 2. These are 2 different networks. Everything over here, you'll notice it starts with an IP address 172. So all of this is on one network. All of these devices over here start with an address 192. They're on a completely separate network. Now, we do break down networking and subnetting and all those things. But for now, we just want to know they are different networks, but I want to allow them to communicate with each other. Well, the way that works, I have my switch on both sides. So the devices themselves all can communicate with each other on their respective network because they are connected to the same switch. When I want to connect the networks to each other, that is where our router comes in. So if you are over here and you're using PC2, your default gateway, 192.168.1.1, that is going to be the IP address of the router itself. So now, when traffic needs to go to a device in building 2, it simply goes to the default gateway, the IP address of the router, and the router has been configured to route traffic between these 2 networks. So now it goes on to whatever device it's supposed to go to. If you're on the other side, you'll notice the default gateway is 172.16.1.1. So this router has just another port on the router, and it has that IP address assigned to it. So if you are now in building 2 and you need to route traffic, it simply goes up to the router through that port, and it just comes out the other side. And you are now connecting your 2 different networks with each other. Now, do know, this is the most simple explanation for a switch and router you will ever encounter, because these are highly configurable devices that have their own certifications from various vendors. We will cover these in more detail as the course goes on, but they're kind of our foundational building blocks right now, so we need to understand the purpose of just what they do, and it ties into a lot of our configurations and components that we'll look at in the next few sections. Then we'll look at these in more detail as the course goes on. All network devices have something called a MAC address. A MAC address is a 12-character hexadecimal address, and it's assigned to the network interface adapter. This can be wired or wireless, does not matter. Your smartphone has an embedded network interface adapter in it that will have a MAC address. If you have a desktop that you can plug an Ethernet cable into, that's going to have a MAC address. If you've ever purchased a USB, a network interface adapter, that USB adapter has a MAC address associated with it. A MAC address is sometimes referred to as a physical address. Those terms are synonymous. So a physical address is a MAC address and vice versa. Just goes by both names. And as we said, any type of network device. This could be a desktop phone, a mobile phone, a server, desktops, laptops, printers. If the device itself can connect to the network, it has a MAC address. Even routers, access points, all of these devices will have a MAC address. Now let's talk about how the MAC address and IP address are related to each other. In this demo, I'm going to show you how to determine the MAC address on the device that you're actually using. The first thing I'm going to do is actually go to command prompt. So to do that, I'm just going to click on Start and type CMD. If you're on any Windows-based machine, you can just do that. Click on Start, type CMD, and command prompt will be returned in your results, and it'll just open up for you. I'm going to put that in full screen here. The most simple way to get your MAC address is to type get MAC. That's going to give me some basic information. So I see my physical address. The computer I'm using right now has two network adapters. One is Ethernet, which is disconnected. So I know this top one, C8, I know that is my Ethernet adapter that's like hardwired. I don't have a cable plugged into that right now, so it says media disconnected, process of elimination. I know the bottom one that starts with a physical address of FC. I know that is my wireless adapter. But it does not directly say that anywhere here. So one of the things we can do is run this in verbose mode. So I'm going to run getMAC space /v, and that's going to give me some additional information. So when I run that in verbose mode, I get the connection name and I get the network adapter with some additional info as well. So here I can see my Ethernet, which is disconnected, has that physical address, which we know as the MAC address, starting with C8, media disconnected. Then I can see the Wi-Fi adapter has the Intel Dual, that's just the network adapter, my wireless one, but it starts with FC. So it's clear which adapter is which if you were to actually do that. So that's pretty straightforward, the get MAC. I can also use ipconfig. Now you can run ipconfig as a command by itself, but it's going to give you very basic information and it does not include your MAC address. If you want to see the MAC address, you can run ipconfig/all. When I do that, ipconfig/all, these are all the settings for my wireless adapter here, and there are a lot of settings actually showing up. Physical address is what the MAC address will be listed as. So again, for the wireless adapter on my system, it is this FC. So I know that's my physical address. But even if we scroll up, you'll see there's a lot of additional info here. And I only have one adapter connected right now. So that can be a bit to scroll through at times. So some people just prefer the get MAC command. Now, one of the things you can do is actually filter this command a bit by using a find string. So if I wanted to see just the description and physical address, I don't want to see all this other stuff in my results, then what I could do is run ipconfig/all. I could use this pipe symbol. Now, the pipe symbol, if you're not familiar with that, it's normally right above the enter key on your keyboard, and you have to just hold down Shift and hit that key, and it will inject this straight up and down line, which we call pipe. What that lets me do, in this instance, is take the command ipconfig/all. I run the pipe symbol. Think of pipe as saying, and then. So run ipconfig/all, and then find the string of description and physical address, and that's all I want you to show me. So to do that, we're going to run find str, which just stands for find string. And in quotes, I'm going to put description space physical address, end quote. That works beautifully. So here, Now, I do have some virtualization running on my machine. I have like Hyper-V installed. So you'll see some of these that say virtual adapter. We will largely ignore the virtual adapters. But what I'm looking at here, well, I should say we will ignore those for now. What I'm looking at here is description, physical address. So this is my one that's disconnected, the Intel Ethernet, the hardwired disconnected. But then I see my, at the bottom here, my Intel dual band wireless has this FCF8. So the two in the middle that say direct virtual, again, we ignore those. I have a virtualization piece of software installed on this system called Hyper-V, which is Microsoft's software that lets you run virtual machines. And when you do that, it creates these virtual adapters. So you normally won't see that on most systems. We do look at virtual networking later on. So for now, we just kind of ignore that part. We just want to see the MAC address returned in those results. Now, a very weird thing with this command is the fact that it is case sensitive. Well, the string is case sensitive. For example, if I make the P lowercase and run that same command, notice physical address is no longer returned in the results because it is matching that string exactly. So that could be a little weird if you forget that or you get unexpected results. I'm going to close the command prompt now. And instead, I'm going to open PowerShell. Now, you could just search PowerShell, but I have it pinned to my start menu already. So I'm just going to click on PowerShell here and it opens the PowerShell window. Now, you could run the same commands we just ran in command prompt. You could run in PowerShell. My getMac /v, same results. We could run the ipconfig commands, same results. I generally use PowerShell because it gives you a lot of additional capability that you don't get in the command prompt. But the common commands that we have long used on the command prompt, gosh, going back even before Windows 2000, so decades, most of those common commands do work in PowerShell as well. So normally we just use PowerShell. There are some specific commands in PowerShell that do not work in the command prompt though. So that's why we use it, just additional benefits. One of those commands is get-net adapter. Now, something else I love about PowerShell is tab completion. So here, I can just type get-net A, and when I hit tab, it automatically completes the command for me. Now, if you keep hitting tab, it'll cycle through every possible command that started with get-net A. So you normally want to type enough characters to make the command pretty narrow in the results. But I'm just going to run get-net adapter. Now, if I run that command by itself, it's going to get all the network adapters in your system, and it's going to give you basic information. So I see my Wi-Fi and Ethernet. I see the description. I can see under status, one is up, one is disconnected. So my Ethernet is disconnected. And I can see just the beginning of the MAC address that shows up here. That's just the format it happens to use. What I want to do is see the entire MAC address. So one of the things I can do is just change the format. So I'm going to run this command, get-net adapter, this pipe, the straight up and down line, format list, and that's going to change the output. Right now, the default format that I'm looking at here currently, this is considered a table format. Sometimes that looks great. If you have a lot of what would really be columns in your table, it kind of just starts getting truncated and goes off screen. So I don't want that. I'm going to just change it to this format list. So I'm going to run that command. And all it did is put this in a list format for me. So I can see my Ethernet adapter here. So that's one of my adapters. We can see the operational status for that interface is down. Does show me the MAC address though. My other is my Wi-Fi. So the name of that interface. I can see status is up. And MAC address is this FC. So another easy way to get the MAC address. Now, I have been using Windows for 30 plus years. So I am a big fan of Control Panel if I'm on a Windows system. So I'm going to open Control Panel here. Now in Control Panel, you can control the view. So you may be viewing like a category view. If so, you can go through network and internet. I normally use the icon view. But whatever view you're in, you will find this Network and Sharing Center. And you'll see your adapter shows up. So right now, I am using my Wi-Fi adapter, and it's connected to a wireless network, and the name for that wireless network, or SSID, the service set identifier, is Superman. When I click on that, I can go to Details here, and you'll see Physical Address shows up. This is the info that you get from the ipconfig/all command. So I don't know if you don't want to scroll through that or type the command, you could just look at Details here. So I'll see the physical address is that FC address again. So that's one way. You can also go through Settings. I'm going to click on Start, and I have this gear icon here for Settings. In the Settings, I get all these categories. One is Network and Internet. So I am connected to that Wi-Fi Superman right now. If I click on Properties, I can scroll down a bit, and somewhere in here at the very bottom, you'll see Physical Address, MAC, shows up here. So that's one way to view this here. Another, and normally what I do, you can just click on your Wi-Fi or Ethernet if it's connected, whichever one you're using. And if you click on Hardware Properties, it just pulls up that same screen. So a few different ways to get to that view. So ultimately, I can view the MAC address in the command prompt or PowerShell with getMAC, our ipconfig commands, getNetAdapter commands. You can also view it through Control Panel and through Window Settings. So those are the common ways we can view that MAC address. The relationship between the IP address and the MAC address is all predicated on this Address Resolution Protocol, known as ARP. If I have devices on the same IP network, ARP will send a broadcast that's directed to the IP address of the destination device. That destination device will respond with its MAC address. An example, if I'm on, we'll say computer A, and I want to connect to computer B. To test connectivity, something I can do is pull up the command prompt on computer A, and I can simply type ping the IP address of the device on the other side. So ping space 192.168.1.200. Well, what happens, before I can even connect to that device, my computer A sends this ARP broadcast to every device on the network. And this broadcast says, hey, if your IP address is 192.168.1.200, I need you to send me your MAC address. So what will happen, that broadcast ultimately reaches over to computer B, and it says, oh, that's my IP address. It will then send its MAC address back to computer A. So once we have that MAC address, we can now communicate with each other. What's interesting is that we can observe this process using this command ARP-A. Let's take a look at this in the interface. Now in my command prompt, I'm going to type ping 192.168.1.200. That is a valid IP address on my network, and I do get a reply. So all that ping did was test connectivity by sending 4 echo requests to that IP address, and 4 replies were received. So I know from my computer, I am able to communicate with the device that has that IP address ending in 200. What's fascinating is how the process worked. I'm going to run this command, ARP space -A. This shows me the ARP table. So for the local computer I'm on, I can see every IP address that's been resolved to a MAC address. This is the address 200. That is the MAC address of that device. For me to be able to communicate with that address meant I had to send an ARP broadcast to that IP address saying, I need you to send me back your MAC address. The MAC address was received. Let's look at another experiment. I'm going to run ARP space -D asterisk. This deletes all the entries in my ARP table. Now, a few may remain resident. So that cleared the entries in my ARP table. Now I'm going to run ARP space -A again. And I have just 2 things showing up right now. The 1.1 is in the list. That is my default gateway on my network. And we have this multicast address. We don't care about those. What we care about is that the .200 address is no longer in the list. Well, I'm going to ping that address again, 192.168.1.200. That worked. That is near instant. Before I can fully depress the enter key, I already have received a reply. But if I go back to the ARP table again, so ARP space -A, you'll notice it shows back up in that ARP table, the 192.168.1.200. That is the MAC address of that device. This is going to be true for any device on our local area network that we communicate with. I'm going to see the physical address of that device listed anytime I run this ARP-A command. Now, these do time out periodically, so you'll see that 200 in the list. If you don't communicate with that device for an extended amount of time, you'll come back and it just won't be in the list. That's of no concern, because as soon as communication is initiated again, it'll automatically just get added back in that ARP cache. The process of connecting to devices on different IP networks is similar but slightly different. ARP will send a broadcast, but it ultimately gets directed to the IP address of your default gateway. A broadcast can only be sent within your network. A broadcast will never go through a router. Routers explicitly do not pass broadcast traffic. And when I say broadcast, you can think of it almost like a TV station. A broadcast is a message that is sent to every device on the network. Every device processes it. There is no way that I could ever be allowed to send a broadcast to like all the devices on the internet. There would be no functioning internet. So when you send that ARP broadcast within your network, it goes to all the devices on your network, whether that's a gaming system, laptops, desktops. If you have your mobile phone connected to your Wi-Fi, it receives the broadcast. But it never goes beyond your router, never goes to other networks, never goes out to the internet. What it does, it only communicates with the default gateway. So that's where your ARP broadcast would actually stop. What happens is, if I want to connect to Google, and we'll say this is the IP address of Google. It's not the IP address, I'm just making up some numbers. But what happens, when I need to connect to Google, the first thing that gets determined is the IP address local, meaning it's on the same network. All my IP addresses here are all this 192.168.1. Now, we look at network breakdowns and subnetting later in the course, but these addresses are on the same network. The 42 dot address, clearly that's on a different network. Think of it like making a long distance phone call, like equivalent to being in a different area code. So now, for me to connect to Google, I have to send my traffic to the router, which is going to be the default gateway address listed on my computer, and then it gets routed all the way through the internet up to Google, gets returned back to my client computer. Let's look at how that works, but we're going to use a few different commands. In the command prompt, we have this route print command, and we have this get net route. They are the same. One is just in PowerShell. Get net route is PowerShell. The other is in the command prompt, but they serve the same purpose. So let's take a look at that and how all that relates to ARP. Back in my command prompt, I'm going to type route space print. When I type this, the bottom is the IP version 6 route table. We don't care about that one for now. But if we scroll up, there's an IP version 4 route table that actually shows up. Here, I can see a few things. One is my IP address, 192.168.1.196. I can also see the network I'm on is this 192.168.1. So the way ARP works, looking at this table, if I want to connect to another device, and it knows my IP address is 192.168.1.196, but if I want to connect to another device on the same IP network that I'm on, which is 192.168.1, what happens is it scrolls over and says, okay, that is on link. That means I am directly connected to it. And the interface it communicates with is my network adapter. That's my IP address. So this is simply meaning if you want to connect to any device, 192.168.1. anything, it's on your local network and you communicate with it just directly using your network adapter. You don't have to go through a router or anything like that. For dramatic effect, I'm going to type ping rtsnetworking.com. You could ping whatever site you want, but that's the IP address for rtsnetworking.com. 185. I'm going to scroll back up in the list and notice there is no network destination that starts with 185. Doesn't exist. But notice there is this destination of all zeros. The network mask, all zeros. This is often called an any network. So what it basically means is if the IP address you're trying to connect to is not on a network in the route table, our address for RTS networking is not in that route table, then you need to send that to this gateway, 192.168.1.1. That is the default gateway address assigned to my computer. If you were to set an IP address on your device and you do not have a default gateway assigned, then this entire top line of all zeros would be missing and you would not be able to connect to the internet or to any other network. So this, again, think of it as like an any destination, any network mask. Says if whatever you're trying to connect to is not in the route table, send any other traffic to this IP address and it will be sorted out. And the interface just means when I send it to that address, it's going to be sent from the 192.168.1.196 interface, which is my local address on my machine. So now that I've pinged RTS networking, when I run my ARP-A, 185 is never going to show up in this list no matter what. What we will see is the 192.168.1.1 because that's my default gateway, and you'll see that MAC address for the default gateway show up. Now, as much as you communicate with the default gateway, this address is always going to be listed. Even if you clear it with the ARP-D command, if you come back, you're going to see the gateway address. That's going to just always be present because you are really communicating with that through every website, and all types of traffic will get passed through that. But that's the relationship between the IP address and the MAC address. On my system here, I'm just going to pull up PowerShell and I'm going to run get netroute. So get-netroute. You'll see that same information will show up here. The format is a little different, but you'll see my IP address shows up, the 192.168.1.0. You'll see the all zero shows up. So the format is a little different, and it is displaying what we call this sitter notation prefix with this /number. That is something we cover a little later on when we look at subnetting, but it gives you the same information, just a slightly different layout. So get-netroute is the PowerShell command. Route space print is the traditional Windows command that you would use in the command prompt. A model that explains how communication takes place between devices is this Open Systems Interconnect, or OSI, model. With this, I have my computer, an application my user is using, and I have my actual user. They sit atop this model. From top to bottom, layer 7, the layer closest to the user, is the application layer. This is where things like email would run. Various types of applications. If you connect to a website, like HTTP, that would run here. If you are connecting to an FTP server, those types of applications run at the application level. Makes sense by name. Below that, as we drop down, we go to the presentation layer, layer 6. This is where some of our formats take place, like HTML, JPEG, MP3. It determines how data is actually represented to us, and encryption can also occur at this level. Down from that, we move to layer 5, the session layer. What this will do is establish inter-host communication. That is going to be communication over various types of protocols, and it actually manages the session between a sending device and a receiving device. So when I'm browsing a website, this is the layer that maintains the connection between my computer and the website and all the intermediate devices I actually go through. Moving down to layer 4, the transport layer, various protocols work here, including TCP. Moving down to the network layer, this is where IP works. So a term we see all the time is TCP/IP. They are different protocols. One is a layer 4 protocol. The other is a layer 3 network protocol. ARP also works at this layer. If you want to have network level encryption, IPsec has that ability to actually encrypt network traffic. And this would be network traffic. We did talk about encryption at the presentation layer, but that would be encryption of the data itself, not of the actual network connection. So, two different types of encryption. One is an application encrypting data, and wherever that data goes, it's encrypted. IPsec says, I'm going to create a secure connection. I don't care what data passes through the connection, that data will be encrypted. And there are also some other protocols here, like some routing protocols, IGMP, OSPF. We're not concerned with the individual protocols, just how this overall model functions. Moving down to layer 2 is the data link layer. This is where our physical address works. MAC address is a layer 2 address. From a hardware point of view, switches work at this level. I did not say before, but routers are layer 3 devices because they are routing IP addresses. That's where IP addresses actually work. Switches are not routing IP addresses. As we said earlier, they are passing frames. And those frames are sometimes called data link frames, or usually just data frames. But switches operate at layer 2. And you'll see many protocols associated with hardware, like Ethernet, the fiber channel standard, all would work at layer 2. And down to layer 1, the physical layer. This is where your cable physically plugs into your network adapter. So at this point, you are connected out to the network. This would be a communication example. In this example, I have PC1 and PC2. Both have their configurations already defined, but internal, anytime I communicate between PC1 and PC2, data will flow all the way down this model. So we have the application layer process first, then the presentation session, we get down to the transport, that's where our TCP. So everything we know to be true about TCP happens at this layer. IP at layer 3, our routers, as we said. Information related to our switching here, our frames. Then we get down to the physical layer, and that data is then placed on the network. So when my switch receives this, what the switch actually does is take this at the physical layer. I'm just going to write P. And it processes up to the data link layer because that's where that frame that contains the MAC address actually resides. So that's why a switch is considered a layer 2 device. It reads up to the MAC address, and then it just sends it back down that model to the physical and sends it to whatever address it's supposed to go to. Pretty fascinating overall. An interesting thing related to how switches work at this level. Let's say I just have an 8-port switch. A switch actually maintains a MAC address table. What this MAC address table does, it actually stores the MAC address for the device connected to each port. So when PC1 gets connected to this switch, when it sends traffic to the switch, it goes in, I'll say that's port 5, and that's port 8. What it does is examine the MAC address for traffic it receives on that port. So it says, okay, I know the MAC address of the device plugged in this port. It does the same for computer 8. The moment PC2 sends any traffic, it simply takes the MAC address and it stores it in this MAC address table, and it's documented that that MAC address is connected to port 8. So what happens, when PC1 connects to PC2, the traffic comes in on port 5, but instead of being like broadcast and sent out the entire switch, it is directly sent to port 8. So that's as efficient as we could possibly be. Now, that does bring up the question, what if you're trying to connect to something that was just plugged in and it has not yet exchanged any data? Then that is called flooding. If it does not have an entry in the MAC address table, it just assumes maybe some other devices were plugged in some other ports, so it'll send it out every port if that were to be the case. But still, very efficient overall. Switches can operate at layer 2, the data link layer as we just discussed. With that, you are simply having your switch look at the MAC addresses of your devices, and that's what you use to locate. So whenever you try to connect to a device with a certain IP address, an ARP request is simply sent to that IP address saying, I need to know your MAC address. So computers respond and their MAC addresses get stored in that layer 2 switch. That's what a layer 2 switch does. A layer 2 switch can also be broken into virtual LANs. We just call them VLANs. So in this example, my PCA could be plugged into, I'm going to say port 1 on the switch. PCB can be plugged into port 8, we'll say. PCC is going to be plugged into port 11, and PCD, I'm going to say port 13. With many layer 2 switches, you can log into the switch, and from either an interface or a command line at the switch level, you can go to a port and say, and I want this port to be part of a specific VLAN. So here I could say ports 1 through 7 on this switch are all part of this VLAN here. VLAN 10 it is in this example. What that means is any computers plugged into those ports on the switch, they can communicate with each other. If you are plugged into a port that's in VLAN 10, you cannot communicate with VLAN 20. So effectively, a VLAN lets you take your network at a switch level and you can break it up into separate virtual LANs, hence the term VLAN. So it's like having separate networks, but they're physically not separate. Just communication will be separated at the layer 2 level. When I do this, there is no communication between different VLANs though. So if I'm on VLAN 10 and I want to communicate with VLAN 20, no, we can't do that. Does not work. And notice each of these VLANs, they're actually on separate networks. So I have 192.168.10.0. That's one IP network. 192.168.20.0. 192.168.30.0 is VLAN 30. So at a switch level, you can have these separate VLANs, but there's no communication between the three. So the only way communication can happen, you would have to have a router, and your traffic, if you're on PCA and you need to connect to a PC down here, your traffic would actually have to leave your PC. It would go to your switch is connected to your router, and it would have to get routed back into your switch and then pass to that PC. So any communication between VLANs, if you're using a layer 2 switch, has to go to a router, then it gets routed back in. We may not want that to happen. Where a layer 3 switch comes into play. With a layer 3 switch, I can have inter VLAN routing. So here I have VLAN 10, which is on IP subnet 192.168.10, VLAN 20, 192.168.20. So they are two completely separate networks. Again, layer 2 switch does not allow communication between those because it does not process even up to the IP address. It just says this port is in this VLAN. That's all it's capable of actually doing. When you get to a layer 3 switch, easiest way to think of it is a switch that has routing capability. Nothing more than that. So at this layer 3 switch level, now in this picture, we already discussed the layer 2. So we don't even need that. I'm just going to cross that out. With a layer 3 switch, even though we're on separate VLANs, I can configure routing at the switch level so you can directly communicate to and through the switch to devices on other VLANs. Now that has to be configured. Maybe you don't want them to communicate. If you don't want communication between the VLANs, you simply don't allow them to communicate. But you have the option for this inter-VLAN routing, which is simply not a possibility with a layer 2 switch. So the moral of that entire story there. Layer 2 switch works strictly based off MAC addresses. A layer 3 switch works based off MAC addresses, but also has routing capability between separate VLANs on the switch. When we define IP addresses, we will use a decimal number, like 10.1.1.5. That's a valid IP address. When you set an IP address, we always type it in a decimal number, but computers do not use decimal. Instead, computers actually take the decimal number and they convert it to binary code. Now, the reason for that is because we understand the decimal number. It's easy for us to remember, easy for us to type in versus typing in an IP address in binary code itself. But to fully understand IP addressing and to understand how we can take a large IP network and break it up into subnetworks, then we have to understand the binary code conversion process, because that's required when we actually start subnetting. When you look at an IP address is broken down into octets. Each octet represents 8 bits. So when I look at this IP address here, 10.1.1.5, each of these is a separate octet. So my IP address is broken out into 4 8-bit octets for a total of 32 bits, my IPv4 address. In binary, a bit that's set to 0 has no value. Essentially, just think of it as being off. A bit that's set to 1 has a decimal value. Just think of it as being on, and the other as being a bit that's off. Now, you see this concept all over. Every remote control I've seen in the last, 20 years, I believe, has some symbol like this on it. That's the on-off switch on your remote control, the computer monitor you're using right now, or the power button on your laptop. If you're on a mobile device, it may very well have this type of symbol on it instead of just saying on-off, but that's what it actually represents, the on-off button. Or you'll see many light switches just have a 1 and a 0, or different types of switches. My coffee maker has a 1 and a 0. So you slide the button to 1, it's on, slide it to 0, and the coffee maker is off. So we see this concept a lot of places. When we work with binary code, what we refer to as the low order bit represents a decimal value of 1, and the high order bit represents a decimal value of 128. So that is the value assigned to the bits. If all the bits in an octet are set to 1, the decimal value is 255. 255 is the highest number you will ever see associated with anything related to an IPv4 address. Not possible to have a number that's 256. 255 is the absolute highest possible value you can get because we're only working with 8 bits. So when we say low order bit, what I mean is this bit. The rightmost bit is a 1. The leftmost bit is the high order bit, and it would be 128. So when we convert this, our rightmost bit, we always start from right to left. The value simply doubles. So our second bit has a value of 2, 4, 8, 16, all the way up to the 8th and final bit of 128. This is a better view of that. So here I have my 8-bit octet. Now again, think of an IP address. Each of these numbers in an IP address, like the 10, is actually represented by an octet. So to make 10, there is going to be a combination of these 8 bits here that are 0 and 1 to equal 10. The same thing is true for the second octet, the .1, the .1, the .5. So just a combination of 1s and 0s that equal these numbers. Now when I look at this, I have my 8 bits here. So our first bit is actually bit 0 up through bit 7. There are 2 ways to think of this. When we want to do the conversion, we can do 2 to the power of, or many people just call it exponent. Now that's actually what it is. The exponent. So 2 to the power of 0. Then 2 to the power of 1, 2 to the power of 2. If we look at that, 2 to the power of 0 is 1. 2 to the power of 1 is 2. So you could do that all the way up. Or you can do what I do. And you just know it starts at 1 and it doubles. So 1, 2, 4, 8, 16, 32, 64, 128. That is as far as we can go because IPv4 addresses are only 8 bits. Now 8 bits does equal 1 byte. So you could say this is a byte. That is exactly the same thing as saying 8 bits. But we cannot go beyond the 8 bits in the IP address itself. If you were to keep going just mathematically, your next number would be 256, then 512, 1024, 2048, 4096, and so on and so on. It just keeps doubling. But we are limited to the 8 bits here because of our IP addresses. Let's start off converting an IP address, 172.16.1.59. I want to convert that from decimal to binary. What we know to be true before we even begin is that each octet in my IP address, the 172.16.1, the 59, each of those 4 octets is comprised of 8 bits total. So what I have to do is figure out which of those bits are on and which bits are off. Now I want to convert each of these 4 octets to its binary value. To do that, I'm going to put 172 up here. Now the easiest way to do this is just to start asking yourself, can 128 go into 172 or be subtracted from? The answer is yes, it can. So I need to subtract 128 from 172. I personally do not like math, so I'm actually going to use my calculator. 172 minus 128 is 44. So that is my number. Can 64 be subtracted from 44? It cannot, so that's a 0. Can 32 be subtracted from 44? It can, so that is a 1, and I subtract 32. When we do that, we have 12 remaining. Can 16 be subtracted from 12? No, so that's a 0. Can 8 be subtracted from 12? Yes, so we make that a 1, subtract 8, 4 remains. Can 4 be subtracted from 4? Yes, so we make that a 1. 4 minus 4 equals 0. 2 cannot be subtracted from 0. 1 cannot be subtracted from 0. So when I look at this in binary, from right to left, our rightmost bit, the 1, is off. The second bit is off. My third bit with a value of 4, decimal value of 4. My fourth bit with a decimal value of 8, both of those bits are on. Bit 5, decimal value of 16 is off. My 6th bit has a decimal value of 32, that bit is on. 7th bit is off. And my final 8th bit has a decimal value of 128, and that bit is on. So ultimately, 128 plus 32 plus 8 plus 4 equals 172. Now, we just rinse and repeat that process. That's all there is to converting binary code. Just do that same exact process over. Now, my IP address was 172, then it was 16. There is nothing to convert for 16. I know that the 16 bit here, the bit with that value is going to be a 1. All other bits will be 0. When I want to convert the 1, I know the rightmost bit is 1. All the other bits will be 0. Now, I chose this IP address because 172.16 is a very common address, is why I chose that address. But when I look at the 59, that one is not quite as clear-cut. With the 59, we can do what we were doing before. I'm just going to put 59 right here. And start asking yourself, can 128 be subtracted from 59? No, it cannot, so that's a 0. Can 64 be subtracted from 159? No, so that's a 0. Can 32 be subtracted from 59? It can, so we make that a 1. Then we just subtract 32. If my math is correct, that is 27. Can 16 be subtracted from 27? Yes, it can, so I make that a 1. And now I subtract 16 from 27. And we get 11. Can 8 be subtracted from 11? It can, so I make that a 1. That gives us 3 remaining. Can 4 be subtracted from 3? It cannot. So I'm going to make that a 0. Can 2 be subtracted from 3? Well, we know it can, and you'll have 1 that remains. Then 1 subtracted from 1. Yes. And that's what we get. So our 59 is going to be our decimal value 1, 2, 8, 16, and 32. add all those up, and it will equal 59. That's all there ever is to converting from decimal to binary. Just figure out which bits have to be turned on to get the number you're actually working with. Let's look at a conversion example. So here, I have my decimal value. If I want to convert, let's say I have an IP address, 192.168.1.25. I want to convert this entire IP address to binary code. Well, what we have to do is figure out which numbers actually equal 192. And it is totally fair to use a calculator if you don't want to write it out. But I just know that 128 plus 64, if you add those up, 128 plus 64, they actually would equal 192. So the IP address itself is going to start with, in binary, 1, 1. That's 192. So I know all the other bits here will be 0. Now, if we do the same for 168, which bits equal 168? Now, we know that if the number in your IP address is higher than 128, we know that that's going to be 1 for 128. So we'll make that a 1. Now I'm going to use a calculator because that's exactly what we would do in the real world. On my calculator here, what I'm going to do, that 168, we said that 128 does go into it. So I'm just going to subtract 128. 168 minus 128. That gives us 40. I know that my 64 is going to be a 0 because you cannot subtract 64 from 40. So I'm going to just make that a 0. Now on the calculator, I'm going to try to subtract 32. So 40 minus 32 gives us 8. So that worked. So that's a 1 because we're taking 32 away. Now, if I go back to the calculator, we have 8 that remains. So 16 cannot be subtracted from 8. So that's going to be a 0. Now we have 8 that remains. Well, we know 8 minus 8 is 0. So that's it. This is going to be a 1, and there's no other numbers left. So 0, 0, 0. So the first one here equal 192. This equal 168. Now, when I want to convert 1 to decimal, I don't think we need a calculator for that. I know that it's going to be 0, 0, 0, 0, 0, 0, 0, 1. So 7 leading zeros, and the rightmost bit is going to be a 1. To convert 25 to binary, the first thing I want to do is ask myself, can I subtract 128 from 25? You cannot, so that's a 0. Can you subtract 64 from 25? No, so that's a 0. Can you subtract 32 from 25? No, so that's a 0 as well. Can you subtract 16 from 25? I can, so that's going to be a 1. Now, if I take 25 and you subtract 16, I'm not going to show my work here, but we know that is 9. So I have 9 that remains. Can I subtract 8 from 9? Yes, I can. So that becomes a 1. Now, when we subtract 8 from 9, you have 1 that remains. You cannot subtract 4 from 1, so that's a 0. You cannot subtract 2 from 1, so that's a 0. You subtract 1 from 1, and that is the final answer. So 0, 0, 0, 1, 1, 0, 0, 1. So this would be our binary equivalent. Now, if you were to look at this in reverse, we'll say, for 192, the only 2 bits that are on, 128 plus 64 equals 192. For the 168, we said 128 plus 32 plus 8 equals 168. For the 1, well, that one's easy. Just the rightmost bit is on. For the 25, the bit in the 16th place, the 8th, and the 1 equals 25. To look at this with a calculator, I'm using Windows 11. Depending on what operating system you're on, your calculator may look a little different. But even the calculator on an Android and an iPhone can do binary conversion. In my Windows calculator, I'm going to change it from standard to programmer mode. With this calculator, I can simply here, just click on decimal, and I'm going to type 192. When I type 192, it tells me the binary for 192 is exactly what we said. On the left, our two most left bits are 1, and all the other remaining bits, the 6 remaining, are all zeros. So we know that's correct. 168 was our other number. So with 168, we said it was 10101,000. So we were correct with that as well. We don't need to convert 1. Actually, I'm going to convert 1 anyway. Now, when you convert 1, depending on the calculator you use, you will have some bits omitted. Some calculators will only show you the number 1. They will not list the leading zeros. The Windows calculator will list the 3 leading zeros, but it will not list all 7. So just be aware, that can look a little weird when you look in some calculators. Now, our last number was 25. So for binary, 0001, 1001. That is exactly what we came up with. So our binary is correct. Now we can work through a practical exercise. We want to convert 231 and 117 from decimal to binary, and we want to convert C and D from binary to decimal. The answer key to these 4 problems are under this lesson as a downloadable resource that you can just click on. Each computer on a network must be assigned a unique IPv4 address. That address is what allows it to communicate with other computers. Network communication for a computer is directed to the IPv4 address of that computer. I always compare this to a phone number. If I want to call you, I need to know your phone number. You can think of an IP address almost like a computer's phone number. If you want to communicate with that computer, you have to be able to determine what that computer's IP address is. The same way that phone numbers are broken down with a country code, you have your area code, then you have the unique portion of your phone number. The IP addresses work on the same concept. IPv4 addresses contain 2 components. There is a network ID that identifies the network the computer is actually on, and there is a host ID that uniquely identifies that computer on that network. When we look at IP addresses, we also have another component, the subnet mask. The subnet mask identifies which part of the IPv4 address is the network ID and which part is the host ID. Whenever you look at an IP address, you're going to see the IP address and the subnet mask. So when I look at this IP address here, 172.16.0.10, then I have a subnet mask, 255.255.0.0. When you look at the subnet mask, the network ID by default is any part of the IP address that sits above 255 identifies the network. So in this case, 172 and 16 are all part of the network ID. So my network ID is 172.16. Any bits in the IP address that sit above 0 are part of the host ID. So my host ID is the 0.10. So what does that mean to me? It means every computer on the same IP subnet that I'm on will have an IP address that starts with 172.16, and I'm going to say .x.x, because the last 2 octets there, those numbers can be unique. But if we are on the same IP network, then your IP address has to begin with 172.16 because that is the network ID. I'm in Control Panel on my computer. I'm just going to open the Network and Sharing Center. And I'm going to click on Change Adapter Settings, and that will show me a list of my adapters. I'm going to click on my Wi-Fi adapter. Properties. I'm going to select this TCP IP v4. Just double click that. When I click use the following IP address, if I type the IP address that we were just referencing, which was 172.16.0.10. When I click in the subnet mask box, you'll notice it automatically fills itself in with that same subnet mask 255.255.0.0. So just looking at that address, I know the network ID is 172.16, the host ID is 0.10. I know that just looking at the 255s and the zeros in the subnet mask determines where that's broken down. Now, before we get ahead of ourselves, we will look at how to take a subnet and create custom subnets from it. So we'll see how to break this down so we have multiple subnets within that range, but we're just not there yet. That's where we're headed to. To look at an example that has multiple computers on the same subnet, here I have 192.168.1.182, and notice the subnet mask has 3 255s. That means the network ID is actually 192.168.1. We'll say .0. Some places you'll see .x, they are synonymous. But anything above the 0 in the IP address is now the host ID. So here, I know the host ID is actually 182. The 192.168.1 is just the network ID. And we'll just write net ID. When I look at the other computers on the same subnet, we'll notice they are the same. Well, the network ID is the same. 192.168.1, a unique host portion, 180. 192.168.1, unique host portion, that host ID is 181 at that level. So what that means to me, all these computers can communicate with each other. They don't have to connect through a router or anything like that because they are on the same local IP subnet. Most home routers and home networks are set up using 192.168.1 addresses. Very common that you'll see that for the small office, home office networks. So if you have multiple computers on your home network, it's going to be defined just like this. You're going to have 192.168.1, and the last octet or that last number in your IP address will be unique on each individual device. I'm sure some of you are wondering, where the 255 in the subnet mask, where were all those defined? And the answer is they are automatically defined for us when we enter the IP address. But let's take a look at that in the next section. One of the most important things we can understand about IP addressing is the concept of classful IP addressing. There are 5 classes of IP addresses, A, B, and C. Those are the 3 classes we care about. The class D addresses are reserved for multicast use. So they're not addresses that you could actually type as your IP address on your Mac or PC or mobile device. They will be embedded in firmware on devices with multicast capability. And there is a class E that is experimental. So those addresses are reserved. We can only manage class A, B, and C IP addresses in our environments. What's interesting is what determines the class of your IP address. It is the first number of your IP address that determines the class. If your IP address begins with 1 to 126, your IP address is a class A IP address. Now, there is one footnote to this. Something we look at later on is this thing called a loopback address. It is for troubleshooting the network adapter in your own machine. So if your computer cannot connect to the network, cannot connect to the internet, and you are the only device with this problem, but everything seems to be configured correctly, then I would start to be concerned. Maybe I have a bad network adapter in my computer, or maybe the protocol stack on my network adapter is corrupt. So what you could do is just test that by trying to ping this loopback address, which is actually 127.0.0.1. And if you just go to a command prompt and type ping 127.0.0.1, it just does a self-test of the network adapter, and you should always get a reply indicating that that was successful. Now, we look at the loopback when we look at our IPv4 troubleshooting section shortly, but that numerically is in the class A address range, but not a valid address you could ever assign to a device. So everywhere you see this range, you're always going to see class A is 1 to 126 because that is the usable address space. The subnet mask is always 255.0.0.0. Now that we are masters of binary code, If you convert 255 to binary code, it's going to be all ones. So you have 8 ones. Sometimes you'll see, instead of the 255.0.0.0, sometimes you'll actually see /8. That just denotes that the first 8 bits of the subnet mask are all ones. So you may see an IP address like 10.1.1.1/8. That is exactly equivalent to looking at an address that has this subnet mask, 255.0.0.0. You'll see like /8 in a lot of router configurations and things like that because it's just easier to look at than looking at the 255s. What this means for me, with Class A, if my IP address is 10.1.5.89 with that subnet mask, that means the network ID, I'm going to write net ID, is the 10. My possible host IDs are all going to be represented by the last 3 octets in the IP address. In short, any computer on the same IP subnet as me, the IP address has to begin with 10. If that is true, then we are on the same IP subnet. Now, we are assuming these computers are connected to the same physical network. As long as that's true, and your IP address starts with 10, we can communicate with each other. This does produce a lot of IP addresses. Actually, 16,777,214 IP addresses you get from a single Class A IP address. So pretty large overall. I said that Class A usable addresses stopped at 126. 127 was reserved for loopback. So Class B, the first number of the IP address, 128, and it goes through 191. So that is our range of Class B IP addresses. The default subnet mask for Class B is 255.255.0.0. Again, we are masters of binary now. If you convert the binary, that is /16. So 8 ones make up the first 255, another 8 ones make up the second 255, so /16. Now this still produces a lot of IP addresses. 65,534 IP addresses. Now, I know some are thinking, how do we get to those numbers? We will see the exact formula as soon as we start subnetting, and we'll verify that those numbers I wrote are actually the correct numbers. They are correct, but we'll see exactly how we arrive at those numbers. Now, if I move to a Class C IP address, Class B ended at 191, Class C starts at 192, and it actually goes up to 223. 224 actually starts the Class D multicast. So for my address here, the subnet mask is going to be triple 255. So 3255.0. If I wanted that to be in what we call that sitter notation, I may not have said that earlier, but this slash number is called sitter, CIDR, and it stands for classless interdomain routing, CIDR. Many people just call it a prefix. Class C addresses only produce 254 IP addresses, so a very small number of IP addresses. Now, let's look at a few things. The first thing I want to show you is how we actually know what the subnet mask is and how that actually gets defined. To briefly recap, we said Class A addresses have a default subnet mask with 1255. Class B have 2 255s, and Class C will have 3 255s. Well, let's look at that in the interface. So back on the properties of my network adapter, I'm going to open my IP version 4 settings, use the following IP address. Now, as we saw earlier, if I enter a Class A address, the moment I click in the subnet mask box, it automatically gives me that subnet mask. So it is defined strictly based on the first octet, or that first number, if we want to say that, in the IP address itself. If we choose a Class B address, I'm going to choose 172.16.1.1. Now we know the number just needs to be between 128 and 191, But when I click in the subnet mask box, you'll notice it has two 255s. Then .0.0. So looking at this, I know the network ID is 172.16. If we're physically connected to the same network and this is your IP address, and your IP address starts with 172.16, then logically we're on the same IP network and we can communicate with each other. If we look at a class C, I'm going to choose 192.168.1.5, we'll say. Click in the subnet mask box, and we have three 255s.0. So now the network ID is 192.168.1. So for class A, B, and C, it's that easy to know what the network ID actually is. You simply look at the subnet mask. Any number in the IP address that's above a 255 in the subnet mask is part of the network ID. Any number in the IP address that sits above a 0, that is going to be your host ID. Now, to verify these numbers here as to the number of IP addresses produced, I need to convert the subnet mask to binary code. Luckily, it is very easy. We established that 255 is actually 8 ones. So my class A subnet mask, 8 ones, then we have 8 zeros, another 8 zeros, another 8 zeros. I counted as I was writing, so I think I wrote the correct number. But we know it's 8 ones in the subnet mask and then a total of 24 zeros. So to determine the number of IP addresses, the entire formula is nothing but 2 to the power of our exponent. I'm just going to put the number of zeros in the subnet mask. I'm just going to put in mask. And then you subtract 2. That will always give you the number of IP addresses. Now, the reason you subtract 2, one is for the network ID, we'll say net ID, and the other is for the broadcast address. The network ID is the very first IP address on the network. That cannot be assigned to a device, just identifies the network. And then we have a broadcast, which is the very last IP address. But we will expand on those in just a moment. But I said here, I have 24 zeros in this class A subnet mask. So all zeros, all zeros, all zeros. Now let's put that in our formula. 2 to the 24th power minus 2. I'm going to pull up my calculator again. On my calculator, I'm going to go to scientific mode. And most calculators have this button. It's called X raised to the Yth power. What that allows me to do is just type 2. Then I click XY. It accepts 2 as X. Whatever number you type now, it will accept as the exponent. In our case, that's going to be the number of zeros. So 2, XY, 24. And we said we need to subtract 2. That does, in fact, give us 16,777,214 IP addresses. If we were to look at a Class B address, I know the subnet mask for Class B is 255, all zeros in the third octet. So 8 zeros in the third octet. And then we have another 8 zeros in the fourth octet. So we have a total of 16 zeros. So if I just did 2xy 16 minus 2, we have 65,534 IP addresses in a single Class B address. Now, if we were to look at the Class C address, the subnet mask for Class C is 255.255.255.0. Only the last octet in the subnet mask is all zeros. So we know that's going to be 8 zeros. So for that, I'm just going to do 2xy 8 minus 2, 254. So we verified those address ranges are correct. If I wanted to write this out, we have 4 numbers we're concerned with. I have the first IP address. I have the last IP address. So that will be your assignable numbers. Then we have the network ID and the broadcast. The first assignable IP address, 192.168.1.1. The last assignable IP address, 192.168.1.254. The network ID itself would be 192.168.1.0. The broadcast, 192.168.1.255. So the very first number in the IP address is always the network ID. The very last number is always the broadcast. They are not assignable addresses. So that is why in our formula for the class C address, we did 2 to the power of 8, which is 256. Then we did minus 2, which gave us 254. So those are the assignable IP addresses. Now let's look at one that's a little trickier. I'm going to take a class A address. I'm just going to say 10, well, 0, 0, 0, we'll say. So 10, that network ID there. We have, well, the net ID. We have the first IP address, last IP address, and broadcast. The first usable IP address is going to be 10.0.0.1. That is the way it's always defined. 10.0.0, the rightmost bit would be a 1. The network ID is actually what I wrote above, 10.0.0.0. Every bit in the host ID is going to be represented by a 0. So they're all zeros in the host ID. The last usable address, 10.255.255.254. Now that looks a little weird always, but the broadcast is 10.255.255.255. Again, that is the very last IP address, 10, all 255s. So that is one of the addresses you have to subtract because it's the broadcast. So here, when I subtract that address, it means the address beneath that is 254. So that's my last usable address. And as we said, the network ID, all zeros in the host ID. So that is the other we actually subtract. So my range of usable addresses would be 10.0.0.1 through 10.255, 255, 254. Now what's impressive, if you use all the possible combinations, we get that 16,777,214 IP addresses. So I'm using like 10.0.0 and up. Then I'm using 10.0.1 here. Then you're using .2 and 3 here. Then you're doing the same with the second octet. When you've exhausted all those possible combinations, you get that almost 17 million IP addresses. Pretty interesting overall. So that's how our class A, B, and C classful IP addresses actually work. Before we start getting into subnetting and heavy IP address conversations, let's talk about the possible values for a subnet mask. Most subnet masks will look something like 255.255.0.0. That's like a default subnet mask. What we have in our chart here to help us out is all the possible values a subnet mask could actually be. So here I have my binary, just 8 bits. In this chart, we consider this to be bit 1, and we consider this to be bit 8. So this is from right to left. I put the decimal value under each of these bits. When you look at a subnet mask has to be all ones. For example, 255.255.248.0. That is a valid subnet mask. But in binary terms, that's actually 8 ones, another 8 ones. So that's 255, 255, 248 would be 5 ones and 3 zeros and 8 zeros in the last octet. So a subnet mask has to be contiguous ones, then contiguous zeros. Subnet mask never alternates. all ones, then all zeros. What that means is there's a finite number of subnet mask values that we can come up with. So here, when I look at a subnet mask, you could have a subnet mask that has a 128 in it. So 128 is a valid number. If you take 128 and add 64, it actually equals 192. That would be a valid subnet mask. You could take 192 and add 32. That will equal 224, a valid subnet mask. Rinse and repeat. Add 16, that will equal 240, plus 8 would equal 248, plus 4, 252, plus 2 would equal 254, 1, if you added, would equal 255. So I just know if my subnet mask is 248, instead of trying to convert it in your head or on paper, going through the long binary conversion process, with this chart, all you have to do is write out 8 ones like I did here. Write the decimal value under each of those ones from right to left. 1, it doubles all the way up. So 2, 4, 8, all the way up to 128, all the way up to 128 for the 8th and final bit. So that's our little conversion there. So that's our chart we can use to convert. Now, all I'm doing is adding the possible subnet mask values below. So for the subnet mask, 128, we start with, plus 64, valid subnet mask. Take that and just add the next bit and the next, and these are all the values you come up with. So other than 0, these are the only possible subnet mask values that you could ever see in an IP address. You'll see how beneficial this is in some of the upcoming lessons here, because we're going to use this chart as we go through the subnetting process itself. Let's make sure we understand the subnet mask. I could have an IP. I'm going to just use 172.16.0.0. And I'm going to use the default subnet mask, which is 255.255.0.0. If I convert that to binary code, I just know it's going to be 8 ones / 8 more ones. Then it's going to be 8 zeros and 8 more. So this is the binary of 255.255.0.0. Now, when I do that, that gives me one network, which I could divide here. So the network itself, we'll say net ID, is 172.16. The 0.0, that's all possible host IDs. So you just use different numbers here and you come up with your host IDs, which actually gives us a total of 65,534 possible IP addresses that we can actually use. So you get one network with 65,000 addresses. No one wants that. You don't have 65,000 devices in a single location on a single network. So where the subnet mask comes into play, it lets me break up this one network of 65,000 plus IP addresses into multiple networks, but each of these networks will have fewer IP addresses. So hence the term subnetting. I'm taking one big network and you're just subdividing it up to create many smaller networks. Now, before we do that, we have to look at the subnet mask portion. With the subnet mask, these are the only valid values a subnet mask can ever have. So in your subnet mask, you can have 255, 254, 252, 248, 240, 224, 192, 128, and 0 would be the only other valid number. The only possible values. So if I were to have a subnet mask that's 255.255.248.0, that is a valid subnet mask you could set. What it actually means is that your third octet here has a value of 248. Now, if I look at this little chart, this is a handy chart. So I have the possible subnet masks value, and we'll see 248's in the list. 248, if you do the binary conversion, is actually going to be 5 ones. So 248, this is going to be 1, 1, 1, 1, 1, then 3 zeros. So that is 248. Now I know that from looking at my chart here if I don't want to actually do the conversion. So now when you see a subnet mask that has some number other than 255s and zeros, we know what it actually represents. It simply means there's an octet that has a mix of ones and zeros, and that's how you get a subnet mask that has like a 224, 240, 248, 254, one of those types of values in the subnet. The network ID and the host ID, they just split in one of the octets. Now let's take this one step further and actually try subnetting it. The first thing I want to show you is the subnetting process itself. Step 1 in subnetting is to convert the subnet mask to binary code. I'm going to use this example. 172.16.0.0, 255.255.240.0. So if I convert this to binary, I know it's actually so that would be 255, 255, 240 would be 4 ones. So we have that here. So 4 ones, then 4 remaining zeros. This is why binary code was critical for us to actually work through. So now I know what the binary equivalent is of the subnet mask. Now, when I want to convert this, all I have to do is count the zeros. I have 4 zeros here, and I have 8 zeros here. 8 plus 4, if my math is correct, equals 12. So now, in my Windows calculator, I will simply take 2, I'll put that right here, 2 to the 12th power minus 2 will give me the right answer. Now let's look at the Windows calculator. In the Windows calculator, just be sure that you are in scientific mode. 2, and we're going to use this x to the yth power button. So that accepts 2 as x. Whatever number you type next, it will accept as y, like the power of or exponent. So 2xy 12 minus 2. 4,094 IP addresses is what I actually end up with. That's the entire process of figuring out how many IP addresses exist. Convert the subnet mask to binary code, count the number of zeros, and then we simply use this formula. 2 to the power of minus 2 gives us the answer. Well, let's do another one. Let's say 252. Now, I'm not going to write all this out again. We don't need to duplicate it. So I'm just going to erase part of this here. But if we made this 252, then for 252, I actually have 6 ones and just 2 zeros remaining. So I'm going to make this a 1 and this a 1. And then it's just 2 zeros that now remain, and that actually would equal 252. So it's 2 zeros here, 8 here, 2 plus 8 is 10. So now if we do 2 to the 10th minus 2, we'll get our answer. I'm going to clear this from before, and we'll just do 2xy 10 minus 2, 1,022. So you get 1,022 IP addresses on a subnet with a subnet mask of 240. So with that subnet mask, 255.255.252.0, I know right now I have 1,022 IPs per subnet. But you know what's missing? I don't know how many subnets I actually have. Don't worry, that is super easy to figure out as well. So with the subnets, to figure out how many you actually have, because again, this started with one network with 65,534 IP addresses. Now we know I am down to subnets with 1,022 IP addresses per subnet, but I don't yet know how many subnets. Well, that's easy. We agree 172.16 is a class B IP address. That means the default subnet mask is 255.255.0.0. How many bits have I borrowed? Meaning, how many bits have I taken from the host ID and have I moved to the network? So how many zeros have been converted to ones? Well, when I look at this, I know the first octet, that's part of the default subnet mask. That's part of the default subnet mask because, again, it's the 255.255. So we didn't do anything with those. So I'm not counting those. I borrowed these bits here. So for 252, I actually borrowed 6 bits. So what you always do, look at the default subnet mask, exclude those bits, then count the ones that remain, the ones that you've borrowed. Now, to figure out the number of networks, it's simply 2, and I'm just going to write to the number of borrowed bits. Again, that's nothing but bits that were zeros are now ones in this subnet mask. In my case, that's 6. So 2 to the power of 6. There is no minus 2 when I do the networks. 2 to the power of 6 gives you the right answer. Now, if we pull up our calculator again, I'm just going to go 2xy6 equals 64. So right now, I know I have 1,022 IPs per subnet, and I have 64 subnets. Pretty fascinating. I created this How to Subnet document to help you through the process. So you can refer to this, and it makes it much easier to actually follow along and work through this on your own. To use this, I am starting with network 172.16.0.0, subnet mask 255.255.252.0. When I want to determine the number of host IP addresses per subnet, step 1, convert the subnet mask to binary code. Step 2, count all the zeros in the subnet mask. Step 3, using the calculator, 2x to the yth power button, enter the number of zeros that you counted, then minus 2. That's going to give you the right answer. In our case, it's 1,022. Now, this is just an example of the steps above. So with that subnet mask, 255.255.252.0, this is what you get converted to binary code. And you'll see it's 2 zeros in the third octet, 8 zeros in the fourth octet. So at step 2, there are 10 total zeros that I counted in the subnet mask. When I use a calculator, it's simply 2x to the yth power button, 10 minus 2 will tell you there are 1,022 addresses per subnet. To determine the number of networks, basically the same process. Convert the subnet mask to binary code. Exclude the default subnet mask bits, then you will count the remaining ones in the subnet mask. Using a calculator, 2xy, the number of ones that you counted that were remaining. Do not subtract 2 when you do the number of networks. That is the most common mistake people actually make. The example of that, same subnet mask ends with this 252.0, converted to binary code. Step 2, there are 16 ones in the default subnet mask. That's because addresses that begin with 172 are Class B addresses, and their default subnet mask is 255.255.0.0. So I exclude the default subnet mask bits. So in red, that's what we excluded. Then I count the remaining ones. In that third octet, there are 6 ones that remain. So that would be step 3. Count those. Step 4, on the calculator in scientific mode, 2xy6, because that's the number of ones that remain, and the answer will be 64 subnets. One thing great about this is once you understand this one time, you should always understand it. The only thing that will ever be different, the subnet mask will be different. That means you have a different number of ones that you counted and a different number of zeros, but everything else is the same. So our concern is the process itself, making sure you understand the process and you are a subnetting guru. I have saved this as a resource under this lesson. Now let's keep going because we're not quite done just yet. I've created a document that actually walks you through the subnetting process. In this example, I use 172.16.0.0, with a subnet mask of 255.255.252.0. The first thing I walk through is how to determine the number of host IP addresses available per subnet. So step one, just take that subnet mask that's provided here and convert it to binary code. Count the zeros in the subnet mask. Then, like we did in our examples, using the calculator, 2x raised to the yth power, followed by the number of zeros, we will subtract 2. That will give you the number of IP addresses. And I show you what those results would actually be in this example here. Then we determine the number of networks available. So again, convert the subnet mask to binary code, which that should already be done from the previous step. Exclude the default subnet mask bits based on the class of the address itself. Count the remaining ones in the subnet mask. Then use your calculator, 2x to the yth power, and you will enter the number of ones remaining. I did put a note that said, do not subtract 2 like we did for the host IP addresses here. We don't do that when we calculate the number of networks. And then I provide an example of the 4 steps you actually go through and what the result would actually be. So this is a great refresher because what happens is once we go through subnetting, everyone understands how to subnet. But then if you come back a week later, you may forget, when do I subtract 2, when do I not? Some of those small details can kind of get lost over time, so this just serves as a great refresher. This example is a little different because it's a Class A IP address, but the fundamental rules remain the same. I have this 10 network that I want to subnet. The subnet mask that I want to use is 255.255.248.0, or I should say that is the subnet mask that is used. I need to determine the number of networks and the number of host IP addresses. So those are the two things I have to figure out. The first thing I need to do is convert the subnet mask to binary code. Now, you probably don't need to write out the 255s, but I'm going to do it anyway because I just like to do it. So that's 8. That's 8. So that's 255, 255. Now 248, if you have this chart already sketched out, then we just know 248 or converted to binary is going to be 5 ones, then 3 zeros in that third octet, and 8 zeros in the final octet. So looking at my 248, if I want to determine the number of, well, let's do the number of IP addresses first. For no reason, but I always do that first. When I want to figure out the host IP addresses, count the zeros in the subnet mask in total. So we have 8 in the fourth octet, 3 here. So that is a total of 11. 2 to the 11th power. I'll put that here. 2 to 11 minus 2 is going to give us our answer. Now I'm going to switch to my calculator. And on the calculator, we will simply do 2xy11 minus 2, 2046. So that is the number of host IP addresses per subnet, 2046. Now, this one's a little tricky. I want to figure out how many networks I have. Whenever you work with networks, always be cognizant that you have to think about the class of the IP address. So this is a Class A IP address. That means the default subnet mask is 255.0.0.0 is the default subnet mask for a Class A IP address. So here, I'm going to exclude the first 8 bits. Now, when I count the remaining ones, I actually have 8 ones that have been subnetted here and 5 here. That's a total of 13. Because it's Class A, we only excluded the first octet. If it was Class B, like a 172, you would have excluded the first 2 octets. That's why the class is so important. But 8 ones in the second octet, 5 in the third, a total of 13. Now, if I go back to the calculator again, we are 2xy13 equals 8,192. So now I have 8,192 networks with 2,046 addresses per network. Now keep in mind, before this was subnetted, you had one Class A network. And that one network had 16,777,214 IP addresses on a single network. Now you have 8,192 with 2,046 addresses per subnet. Pretty fascinating. If at any point this throws you off, just refer back to that document under the previous lesson. Now let's look at one more example, and we have one further step to go, and we are done subnetting. Let's say I'm looking at this address, 172.16.244.0, and that's the subnet mask, 255.255.224.0. And I need to create a chart with all the possible network IDs based off the subnet mask. Now, the fact that this IP address has 244 in it, we don't really care about that. We just care that this is a Class B IP address because it starts with 172. Class B, if your IP begins with 128 through 191, you are a Class B address. So we care about the class, and we care about the subnet mask. Now, I'm not going to bore you by converting 255. We know that's 8 ones and 8 ones. I don't need to do that. I'm just going to sketch out the 224 in binary code, which is 3 ones and 5 zeros equals 224. We know that from the previous example. So here, when I want to know what my networks actually are, ask yourself, what is the decimal value of this 1 on the far right? So the rightmost 1 bit. What is the decimal value? Well, 224 has a decimal value. That bit in that place has a decimal value of 32. So we're not adding anything up. I'm just saying the rightmost 1 bit. What is the decimal value? It is 32. That is the increment of all my networks. Now, in this chart, it is a foregone conclusion that every cell here, every network is going to be 172.16. So you can sketch that. Now, I won't bore you by doing that over and over. We just know they're all going to be 172.16. Then just dot. The third octet is the one we mainly care about because that is the one that will increment based on our subnet mask. The first network here is going to be, choose a different color, is going to be .0. So that's the increment in the third octet. So it's actually 0.0. The second network, we're going to start incrementing by 32. So it's going to be 32. Add another 32 and you have 64. Plus 32 is 96. 128. 160. 192. And 224. Now, if you add 224 plus 32, you get 256. That's illegal. We can't do that. We know there will never be a number associated with an IP version 4 address higher than 255. So that's illegal. So that means my last valid subnet will actually be that 224. And just for the sake of clarity, I'm going to just put in the last octet here is going to be a 0. So this is the network ID for my 8 networks that I actually have. Now in the chart, if I wanted to fill this in, what is the first IP address, like usable IP address on the first network? It's actually going to be 172.16.0.1. Now it gets a little tricky. I always do the broadcast address next. So when you look at this chart here, ask yourself, what is the network ID for the next network? It's 32 is the increment in that third octet. That means my broadcast, we know it's 172.16, but it has to be 31 because the next network starts at 32. So you go one number below that. This ends at 31. The broadcast address itself will end in 255. So 172.16.31.255. For the last usable address, it is 172.16.31.254. Now, this explains something that we saw earlier. When we were subnetting, what we were coming up with earlier, when I wanted to determine the number of hosts, it was always 2xy, the number of zeros you counted, minus 2. Well, that minus 2, 1 was for the network ID. So let's put a minus 1 here, because that is not an assignable address that you could use as an IP address for a device on your network. The broadcast is the other. So we'll put a minus 1 here, not an assignable address. So what we do, the network ID, you move up one number past that, and that is your first IP address. For the broadcast, one number below, so 254 in our case, this would be the range of IP addresses, 172.16.0.1 through 172.16.31.254. If we were to do another, I'm going to jump down, well, a couple of networks. I'll take network 4. So we know they're all 172.16, but the first assignable address would end with the 96.1. The network ID starts at 128 for the network below, which means this has to end with 127.255 as the broadcast, which makes the last usable 127.254. Now, again, we know they would begin with 172.16. That's true for every cell in this little chart. Now, I don't know why, maybe because you can't visualize it necessarily, but the one people have the most problems with is the very last one. Just what it would look like when it's done. I just always either write it or just pretend that there is a 256 here, although we know that's not a valid network. So the first IP address, that's easy, 224.1. The broadcast, 172.16.255, because just adding 32 numerically, 256 would be the next number. You back off one number from that. It's 255.255. That makes the last usable address 172.16.255.254. It looks a little weird, but it's the same exact principle as what we did on every other network in that list. So now I would be set to tell my network people on network 4. This is your network ID, your first assignable, your last assignable, and your broadcast. Pretty neat overall, and not very complicated in any way. A great website to visit is subnet-calculator.com because it lets you easily check your work. And honestly, in the real world, this is what you would do. We're not going to use pen and paper to subnet, but it's a huge benefit to us to understand the process itself. So when you use a calculator to subnet, you understand what it's actually doing. To verify that we are correct with what we just did, I'm going to choose a Class B address. So this calculator lets me choose Class A, B, or C. You can enter whatever IP address you want to put in. This is the subnet mask we just did. 255.255.224.0. Now, what this is telling me, I have 8 subnets. We came up with that number when we did our formulas. I have 8,190 hosts per subnet. That's the number we came up with as well. So 8,190 IP addresses on 8 different subnets. This also tells me how many bits have been borrowed for subnetting. When we came with 8 subnets, we did 2 to the power of, or exponent of 3 gave us the 8. So looking at that subnet mask, we know 3 bits are used for the subnet. So all they did was exclude the 255.255, and they're just using the bits for the 224. So that's what that represents. Now the 19 mask bits, that means the entire subnet mask has 19 ones in it. So that would be 8 for the first 255, 8 for the second, so 16 bits total, plus the 3 that equal 224. So entire subnet mask would have 19 ones in that subnet mask. Now, the only other thing the calculator does that is, fairly useful, an IP address. I'm going to put an address like 199. So 172.16.199.1. Well, this tells me if your IP address in the third octet is 199, that this is the subnet you're actually on. So the subnet ID or network ID is 172.16.192.0. For that, the broadcast is 172.16.223.255. And that is the first and last address. So you could just put an address and you know what subnet it's actually on. Or the way we did it in the chart, you sketch out your chart and you would just see whatever your number is, where it fits within that range of addresses. So this is an easy way when you want a subnet and make sure you're correct. Just pop the numbers into the calculator and see what you come up with. So very useful. Subnet-calculator.com. We have two types of IP addresses, public and private. Public IP addresses are used on the internet, meaning they are internet routable, and they have to be globally unique. So no other device directly connected to the internet can have that IP address. And ultimately, they are assigned by the Internet Authority for Names and Numbers, pronounced IANA. Now, most people get IP addresses from their internet service provider, whoever that may be. But your ISP likely acquired those addresses from either a larger ISP or directly from IANA. But that is the authority that manages the assignment of IP addresses. Private IP addresses are not routable on the internet. They are only used internal on local area networks. So when we talk about IP addresses and look at IP addresses, pretty much through the duration of this course, they will almost exclusively be private IP addresses because that's what we manage internal. All the other addresses, the public ones, they just work out on the internet. What's interesting is the range. Class A, B, and C. There are private addresses defined in each of these classes. So for Class A, 10 anything, an IP address that begins with 10 is a private IP address. Very common, you see that on networks. Never is it going to be an internet routable address. And notice it has the /8. So we know that /8 is the equivalent of having a subnet mask of 255.0.0.0 with the network ID being 10. And any host ID still would be private. It gets interesting when you look at Class B. Class B, 172.16.0.0/12. That's actually a range of addresses. For Class B, it's actually 172.16.0.0 through 172.31.0.0. Now, we don't need to do the math of the /12, but when you look at that, you just know if an IP address begins with 172.16, 172.17, 18, 19, all the way up to 172.31, it is a private IP address, not internet routable. Now, this makes perfect sense because if I'm in an environment where I have a location in, I'm going to say, New York, I have another location in Toronto, another location in Vancouver, then for all of these locations, I need private IP addresses in each of these. I could make Vancouver 172.16. Toronto could have a network ID of 172.17. New York 172.18. And it eliminates the need of me subnetting these out. You just use those individual subnets that are already reserved as private, and you don't have to subnet, just use those. Also interesting is the Class C. Notice it's 192.168.0.0, but it's a /16. What that means to me, 192.168. I'm going to put X here in this third octet, .0. So 192.168, every number in that third octet. So really that could be 0 to 255. But if an IP address starts with 192.168, don't care what number is in the third octet, I know it's a private IP address. So 192.168 dot everything. Now, this is the address that people are most experienced with on their small networks and their home networks. Most devices like Linksys, D-Link, those types of devices like Netgear, they will ship with IP addresses that are 192.168. My personal experience has been most common 192.168.1, but I have seen some that are like 192.168.0. I've seen some that are .2, but 1 just seems to be the most common. So with those private IP addresses, you simply assign those locally within your environment, and they must be translated before they access the internet. This leads us into something called Network Address Translation, or NAT, which is our next topic. A fascinating concept is Network Address Translation, which we just call NAT. With NAT, my internet service provider will assign me a public IP address. And I'm going to say my public IP address is 27.1.5.42. Now, I have no control over that. That is assigned by whoever my ISP is. And that IP address is actually on the internet side, sometimes called a WAN, wide area network side, of my, in this case, we'll say my modem. So in this example, we'll say you have a home network. Now, one of the tricky things is terminology. Some service providers will call this device a modem, like a cable modem. Some will call it a router. It goes by a lot of different names. Verizon, I know the one I have, they call it a gateway. But they all do the same thing. They connect your internal network to the public network. So really your private network to the public network, we could also say. So this device has a public IP address, but it also has a private IP. Very common that it's 192.168.1.1. Now on my network here, I have an Amazon Echo. I'm going to say 192.168.1.5. Now I'm not going to keep writing 192.168.1. So I'm going to say my desktop is .6, my laptop is ending in .7, and my Xbox here ends in .8. You have, well, we know that is a Class C IP address. So I have all of these devices on my actual network. Now the question is, how do they all connect to the internet at the same time? Because I only have one public IP address that's internet routable. This is where NAT comes in. What NAT actually does is translates your IP address. So under this NAT concept, when my desktop, 192.168.1.6, when it routes traffic to the internet, packets will leave this device with a source address of 192.168.1.6, and it goes all the way up to my modem, we'll call it in this example here. What happens, the modem, or whatever device is acting as your router, will actually take that private IP address out of the header in your packets, and it inserts the public IP address. So when this now goes out to the internet, the IP that's on the internet is this 27.1.5.42. So it goes out to whatever website it is you're trying to connect to. When all that data is returned, this device simply has a mapping that says that session is mapped to this private IP address. So it sends all that directly back to your device. From my laptop, it would do the same thing. My laptop has an address ending in .7. At the exact same moment I can surf the internet, it's going to send all that traffic using the same public IP address, but it's going to manage that as a single session. So any data that gets returned is sent back to my laptop that ends with the .7 and the IP address. Same with your Xbox. If you or maybe your kids are gaming online or your Amazon Echo, you only need that one public IP address. Now, what's interesting is how many different devices can actually do this. Instead of this device being a cable modem, this could also be a wireless router. Well, wired or wireless would not matter. Like a Netgear, Linksys, any of those, they have that capability. This could be an enterprise router, something you would use on a corporate network, like a Cisco router. They are just more configurable. Many have firewall capability built in, just tons of features. They can be very advanced, and they can cost tens of thousands of dollars on the high end, or maybe $100 for some of the lower end ones. Some actually well less than $100. Just depends on the capability. But that is our purpose of network address translation. Takes a private IP address on the device on an internal network and translates that to a public IP address so that device has internet access and manages the session so data can be passed between the device on the network and out to the internet. This is an example of a small office home office network. I have a Verizon service provider. My router is connected and online. This is the IP version 4 address. 108.4.63.150. That's the current IP version 4 address that's defined. That's the only IP version 4 public address. But if I look at the devices, I have this RTS AIO. That is actually the computer I'm using right now. The IP address is 192.168.1.196. But if we look down the list, there are lots of devices on this network that actually show up. But all of those devices have a 192.168.1 address. They're all on the same network. Whenever they connect to the internet, they are simply using network address translation and routing through the internet with that public IP address that's assigned to this router that I actually have here. Pretty interesting concept. And it just works. You don't have to configure anything like that. The router is already designed to actually do that, so I don't have to tell it to use NAT or anything like that. Not for these small office, home office routers. Just built into the configuration out of the box. One other thing I wanted to show you, I'm going to pull up a command prompt here, and I'm going to type ipconfig, and you'll see the IP version 4 address of this device is 192.168.1.196. That is the exact address we're seeing here. I'm going to go to another tab, and in this tab, I'm going to type, what is my IP version 4 address? So I'll just Google that. And this, what is my IP address.com. It always takes a moment for the IPv4, but notice it is saying my IP address, 108.4.63.150. If I go back to the router, that is the exact address on the router. So even though I'm using this computer here, RTS AIO, with that private IP address, the 192 address, on the internet, everything appears as though my IP address is the 108 public address, because it actually is. That's what's in all the packets that I send out to the public internet. And the same would be true for every other device here. Go to any of these devices, and if you go to whatismyipaddress.com, it's going to tell you from any of these devices that your IP address is that public 108 IP address. Pretty neat concept overall. What I love about these concepts is once you understand the concept, it does not change. You could be on a home network with one computer. This is how it works. That same concept carries over to a corporate network with thousands or tens of thousands of computers. You just have more configuration options, but the concept still holds true. A great example to look at how NAT works is to use a small office or home office network. The network I'm on right now has a Verizon Fios router. The IP address of that router is 192.168.1.1. So that's the default gateway for the network that I'm currently connected to. When I click proceed, it's going to just automatically sign me in because that's the way I have this device set up. Just automatically signs me in when I'm on the local network. Now, some interesting things I can see here. I can see the router status says right now it's connected. It is getting IP addresses from DHCP. And right now, the IP version 4 address is showing as 108.4.63.150. So that is the public IP version 4 address that is assigned to the internet facing side of my router. Now, when I look at the network though, I'm going to click this show more here under this my network. And you can see on this network, there is an Xbox. That is the IP version 4 address. This 192.168.1. This is the computer I'm using, RTS-AIO. So that's the IP address of the local machine I'm on right now, 192.168.1.196. This is Ring Doorbell. Some other computers here, this new host 3, new host 2, some Amazon, Kindle, Echo devices. A lot of things show up in this list. So everything that's active right now has recently connected to the network. Then you'll see some things here that all say inactive, meaning they've just not been on the network for a while. So they're considered inactive, and eventually they'll just fall out of the list. But what's interesting, all of these active devices, they could be connected right now to my network, and they can all connect to the internet at exactly the same time. So that always brings up the issue of just how is that working within the router itself? All that's happening, this router is performing network address translation. So if this Xbox with this IP address attempts to connect to the internet, when that traffic reaches the router will physically take those packets that need to be routed through the internet, and it will remove this IP address, the 192.168.1.24, and it will insert this address, that public IP version 4 address. Now, it's going to do that for all of these devices. Even if they surf the internet at exactly the same time, we have no problems whatsoever. So a very neat technology as to how it actually works. Now, what it does is remember who requested what. So if I'm surfing a website from RTS-AIO, it removes my private IP address, this 192.168.1.196, injects the public IPv4 address, connects to the internet, but it remembers that mapping. So when that traffic is returned from the internet, it then will remove the public 108 IP address, and it just reinserts the IPv4 address of my device itself and passes that traffic right back to me. So I only need one public IPv4 address to work on the internet, and I can have multiple devices on my actual local area network all connect to the internet concurrently. Pretty fascinating. Now, to make sure no one tries to hack me, I'm going to take these IP version 4 addresses I have here, and I'm going to renew them so they will just come up as new IP addresses, as different IP addresses, so no one tries to hack my little network here. So I'm going to go to my network, network connections, my broadband connection, Ethernet coax. I'll just edit that, and I'm going to scroll down and go to settings. And now we'll scroll down until we find DHCP. DHCP lease. We'll just release, then we will renew. And that'll just get me a new IPv4 address. And that'll take just a minute, but then it'll be done. So now I would have a new IP version 4 address. One of the most interesting things related to how computers communicate is this concept of TCP windowing. With TCP windowing, computers can control how efficiently they communicate. Now, my goal is always to have my computers communicate as fast as they possibly can, but I don't want to saturate the network. I don't want to overwhelm the other computer. This is where windowing comes in. What happens with windowing? If I'm exchanging data between computer A and computer B, the data I'm exchanging gets broken up into messages. So here I have my messages. It is broken up into 5 individual messages in my example here. Well, what happens? Message 1 gets sent. That gets processed. And it actually sends an acknowledgement back saying, I've received message 1. So now I know message 1 was received. Then message 2 gets sent. I get an acknowledgement back for message 2. That process repeats. This is why the TCP protocol is a reliable protocol. If an acknowledgement for message 4, if that is not received, it'll actually resend it because it says, you should have received that by now, something's wrong. So it'll resend just that one message. So when I send email or anything like that, anything that uses the TCP IP protocol, I know it's going to be delivered. It's not going to get lost on the network and never be resent. That's just not possible. You certainly could have misconfigurations that disrupt communication, but the protocol will never just lose a packet. It also does something called flow control. So instead of sending one of these at a time, it could send a lot at a time. If the other computer can handle it, then it'll just keep sending more and more. These computers all have a buffer. So what happens, let's say you have 100 messages here. Now, again, that message is a transmission. Maybe I'm copying a file from one computer to another. That goes over TCP/IP, but the transmission of that breaks the file down into these individual message components, then they're transmitted over. So let's say it's 100 individual messages. They will be transmitted over. Maybe not all at the same time, but when they're transmitted over, many of those will sit in a buffer and they'll wait to be processed. When that buffer's been reduced, it'll send back another notification saying you can increase the send rate. So this is as efficient as possible, but neither side gets overwhelmed. The sending side, the receiving side, they will communicate with each other through this TCP windowing concept for the duration of their transmission. Just makes this incredibly efficient. It also has a security component to it. When I'm sending data, one of the first few packets likely has your credentials. Because once you connect to a computer, one of the first things you do is authenticate. So I could monitor the network and capture all these packets, and the first time I see two computers communicating, I may assume one of these first few messages has credentials embedded in it. I'm probably right. Well, what happens, let's say that message is, we'll say message 1. That is a sequence number. So sequence number 1. What happens, for the duration of this conversation, I will send message 1, message 2, 3, 4. We're into the thousands of messages between these two. What sequencing actually does, let's say later on, a hacker had captured that message with the credentials in it, but the sequence number was 1. So hours later, you try to send that to the machine, believing it will authenticate, and then you'll have access to that machine because you think it has credentials in it. Well, what happens, it may very well have credentials in it, but won't matter because this machine will say, this session expired long ago, and I've received, 15,000 messages. So there is no way that you could legitimately be sending message 1 or 2 or a lower number message after I've received in excess of 16,000 messages, and I already sent you an acknowledgement letting you know message 1 had been received. That's actually called anti-replay, is what that's called, but just eliminates the ability to resend a message that's already been received by the other side. So it does have a security component to it as well. When I want to set the IP addresses on my own device, I have the option to use the following IP address. This is often referred to as a static IP address, sometimes a manual IP address, meaning someone has entered that address in the computer itself. So I could select use the following, and I just type in the IP address, the subnet mask, the default gateway, which is our router, so I can connect to other networks and to the internet. And I also have a preferred DNS server in my example here. That preferred DNS server is for name resolution. So when I type in google.com or microsoft.com or whatever website it is that you are trying to go to, that name ultimately gets resolved to an IP address because the DNS server, that server has a primary purpose of allowing you to send a query to it. It takes that query, which is a name like google.com, and it resolves that to an IP address and informs you of what the IP address actually is. We have an entire module dedicated to just managing that DNS server on the back end. Very interesting concept. You also have the option to obtain an IP address automatically. This means somewhere on the network, you have a server or some appliance. Could be a DHCP server. It could be a router, even some like home routers. Most home routers have this capability natively built in, where it simply assigns IP addresses to your computers. So I don't have to go to my laptop, my smartphone or anything like that and ever try to set an IP address, you have a server or some appliance or device on the network that automatically assigns you IP addresses. For that, we just select obtain an IP address automatically, obtain DNS server addresses automatically, and those are simply going to be populated from this server or router supplying DHCP services in your network. We also have an entire module in this course dedicated to the configuration of DHCP on routers, on servers. Very interesting topic as well. We have a few different ways to set the IP address in the interface. The first thing I'm going to do is go to Start and Control Panel. And in Control Panel, I'm going to go to my Network and Sharing Center. And I'm going to click on Change Adapter Settings. And this will show you all of the network adapters connected to your system. I'm going to open my Wi-Fi adapter. So I'm going to just right-click that and go to Properties. And you'll see Internet Protocol version 4, TCP IPv4. I'm just going to click that and Properties. Right now, I am set to obtain an IP address automatically. But if I wanted to set that address to be a static IP address, I would just click Use the following IP configuration. Then I could simply set whatever IP address I actually wanted. I'll just use 192.168.1.210. When I click in the subnet mask box, it will automatically fill itself in. Earlier, we discussed class A, B, and C IP addresses. 192 is a class C IP address. You may remember we said 1 to 126 is class A. 127 was reserved for loopback. So then we had 128 to 191 was the class B. 192 up to 223 were the class C addresses. And the class C address has a subnet mask of 255.255.255.0. So it automatically fills itself in. Likewise, if I were to use a class A address, I'll say 10. When I click in the subnet mask box, automatically fills itself in with what would be the default subnet mask for a class A IP address. So that helps you out a bit there. When you want to set your default gateway, whatever that value is, we just type it in. And I set my preferred and alternate DNS servers if you have an alternate. Just manually type those in, or we just let that obtain from DHCP. And that's going to be common on almost all networks you go to. Certainly on home networks, your iPhones, Androids, all your mobile devices, laptops, desktops, if you have like Amazon Fire Sticks, Amazon Echo devices, Google Home devices, all of those things will default to obtain an IP address automatically. And when you are on a corporate network, all of your clients on the corporate network, your desktops, laptops, mobile devices on that network will also typically get an IP address from DHCP, because it's simply too much administrative work to manually go set these IP addresses on these devices. Later in this course, we do look at the DHCP, Dynamic Host Configuration Protocol, and I'll show you exactly how that's set up so that device can then assign IP addresses to all your clients on the network. So that's one way. Just go through Control Panel down to your network connections, and you can just type the address. Another, if you go to your settings, so I'm going to go to Start, Settings. Under my settings, I'm going to go over here to Network and Internet. You'll see I'm connected to this Wi-Fi right now. When I go over to the left, I have Wi-Fi and Ethernet. So one of those are going to be the type of network you're connected to. But I'm going to click on my Wi-Fi. And here, this does not look like something you can click on. To me, it looks more like just something you would read. But it's actually a clickable icon. So if I click on this Superman, Connected Secured, when I click on that, it actually opens up. And I can scroll down. And the first thing I notice is in the properties, I get all the information related to my IP configuration. So I can see the IPv4 address, DNS servers, all of this type of information, my physical address. But if I scroll up under IP settings, I can see right now it is automatic that the IP address is being assigned. But if I were to click Edit, I could change this from automatic to manual. And manual is almost always called static. But I could simply slide that to on to use a manual address, and you just type in the IP configuration that you want it to be. The only thing that is truly different, if I could type, once I set the IP address, I'm just going to say 192.168.1.210. This wants a subnet prefix length. That is that sitter notation we talked about earlier. So in this example, I would type 24. That would be the equivalent of 255.255.255.0, just displayed in a different format. This would be all the ones in binary that actually equaled 255, 255, 255. So same thing, just looks different when you type it in. Then you would just enter the other addresses in decimal format. Whatever they would happen to be. Once you're done, just click Save, and you now have a static IPv4 address. One of the most useful tools to understand networking is the Cisco Packet Tracer tool. This is a network simulation tool developed by Cisco, and it is completely free. Anyone can download it. This will let you design, configure, troubleshoot networks using virtual equipment. You can add routers, switches, servers, different types of end-user devices, even mobile devices, PCs. You can add these in the packet tracer. Then you can create and test various network topologies, experiment with different types of configurations. You can implement different protocols in the tool itself. This is a great educational tool that you can actually use to understand networking concepts. It's also great for people that already have experience. So network professionals, if they want to test in an environment, but they don't have the actual hardware they want to test on, or they don't want to physically connect to it with cables and all those things, then you could simply use Packet Tracer, and you could just simulate entire configurations in the Packet Tracer tool. It's fairly user-friendly. You can actually deploy IPv4, IPv6, VLANs, network address translation, DHCP, VPN technologies in this tool itself. So it's an incredible tool. Over the years, I have spent several $1,000s on routers, switches, different types of hardware, and much of that was so I could learn, and some of it was also so I could build configurations in my own environment and then take those configurations, export them, import them into our customer environments. Or if I wanted to troubleshoot something, but I wanted to do it in my own environment, I would export a configuration, import it to my environment, go through the configuration. Packet Tracer eliminates the need of having all of this hardware in your environment to learn or test. Just use the Packet Tracer tool. The URL to download the Cisco Packet Tracer is under this lesson. I have the Cisco Packet Tracer installed on my computer, so I'm just going to go to Start, and I'm going to open my Cisco Packet Tracer. Packet Tracer is a fairly complex tool, so if you want to know this very well, you can go to Help, and they have tutorials that cover the interface, configurations, everything you need to know about the tool itself. So that's useful if you plan on becoming network certified in some discipline like Cisco down the road. Then you would definitely want to go through the tutorials just so you can become very familiar with the Packet Tracer tool itself. In the tool, I'm on the logical pane right now. If I go to the bottom, it has an option for network devices, and under that, they have routers, switches, hubs, just different types of network devices, wireless devices, and I could simply select the device and I can drag it to this workspace here. They also have end devices, so that's going to have PCs, laptops, servers. They just represent end user devices that you would have on your network. I could drag any of those to my logical space as well. So what we're doing is just laying out a logical representation of our network. Then we can walk through the configurations. What I'm going to do is choose a PC. So I'm going to put a PC here in my environment. And right now it's saying PC 0. What I'm going to do is click that PC 0, and I'm going to type in an IP address. Now I know in my configuration here, I want that to have the IP address 192.168.1.25. And I'm going to add another PC as well. And I'm going to make that 192.168.1.26. What I'm also going to do is go up here and I'm going to click on this note icon. And here I'm just going to type 192.168.1.0 just to represent the network itself. So right now I have 2 PCs on my network. Click this to get rid of my note. But I have 2 PCs on my network. Now I'm going to go to Network Devices, and I'm going to go to Switches, and I'm going to choose one of these switches here. I'll just pick this first one. It says 2960. So I'll just put that in my picture. So right now I have a PC, well, 2 PCs, and I have a switch in my environment. Under my Network Devices, I'm going to go to Router, and I'm going to choose this 4331, just the first router in the list, and I'm going to put that here. So I have 2 PCs, 1 switch, 1 router. Well, let's start configuring some things. For my PC, I actually want to set the IP address on it. If I hover over it, you'll see the device name is now being represented by the IP address, but it does not have an IP address set. So what I can do is just click on the device itself. Now, this is just incredible. When you click on the device, I can go over here to this desktop, and it has an IP configuration. When I click IP configuration, I can set the IP address that I want. So I'm just going to type 192.168.1.25. It automatically fills in with the default subnet mask. And the default gateway that I will use on this network will be 192.168.1.1. So that is the IP address I'm going to assign to my router. And that's it. I could go to this second PC I added, and I can go to desktop, and same thing. We said its IP address ends in 26, and I will enter my default gateway. Now, I'm not concerned about DNS, so I'm not going to enter a DNS server right now, nor am I concerned about IP version 6, so I'm just going to leave that with the default. So right now, these PCs have their IP configuration defined. Now, you can click on the switch, but there's nothing I'm actually defining on the switch. What I need to do is have some connections. So I'm going to click on the connections here at the bottom, and it gives me these different types of connections. So there is this straight through copper, or forgive me, there is this copper straight through. There is a copper crossover. They have a connection that represents a phone. So just various types of connections. And they also have this automatic. Then you don't have to worry about it. You can just click on that, and when you drag it, it'll automatically choose the appropriate type of the connection. I'm just going to choose the connection I know I need. Copper straight through. An Ethernet connection is what that would be, where it says copper straight through. I'm going to click on this PC, and it gives me a list of ports on the PC. I'm going to choose fast Ethernet. Now I'm going to click on my switch, and it gives me a list of ports on that switch. I'm just going to choose one of the available fast Ethernet ports. I'll just choose the first one. Now I'm going to do the same for the other PC. Fast Ethernet 0. I'm going to click on my switch, and I'm going to choose another available fast Ethernet port. So my 2 PCs are connected to my switch. Now, do notice it still has this orange circle icon on it. Well, one of them does. That means this is not finished being set up logically. So if I try to connect right now, it's not going to work just yet. But what will happen in a few seconds, this will turn to a green arrow as well, and I'll know I have connectivity. To test this, I'm going to click on my PC, and still on this desktop tab here, I'm going to go to Command Prompt. Notice it's all green arrows now, so little orange circles are gone. I'm going to type ipconfig. Now this is as if you are at the command prompt on a Windows PC. So I can see my IP address is 192.168.1.25. That's the address we set. Well, I'm going to just type ping 192.168.1.26 and I get a reply. So I know my two PCs here are successfully able to connect through my switch. Now, when I go to the router, I'm going to choose my connection for the router. Now, you could choose fast Ethernet or gigabit Ethernet. It won't matter configuration-wise. But I'm going to choose gigabit Ethernet 01 just because that switch does carry traffic from all of these devices up to my router. And on the router, I'm going to choose gigabit Ethernet 0. Now, we do have to configure the router. When I click on the router, when I go to config, it gives me all these options here. If you want to configure this using the command line interface, the CLI, you could simply hit enter here and you could start typing. Yeah, you would have to know the specific Cisco command line syntax to do that. But what makes this a great learning tool, when I go to config, I'm going to go down to the interface section and I'm going to choose gigabit Ethernet 0. It just says, what do you want the IP address to actually be? I want it to be 192.168.1.1. And I'm going to use that default subnet mask. Now, on a router, the interfaces themselves are actually down until you turn them on. So I'm just going to click this on option here. But what's great about this is it gives you the actual syntax. So this interface, gigabit Ethernet 0/0/0, selected the interface. IP address, we defined on the interface itself. No shutdown is me selecting this box so that interface is now up. Great learning tool. But if we click off of that now, again, it will take a moment before I have the green arrow. It's there now. So let's see if I can ping the default gateway. And actually, I'm going to click on this where it says router 0. And I'm going to type that address. 192.168.1.1. Just so when I reference this, it's just easier to look at as we add more devices. But if I go back to the PC, back to the command prompt, and I'm just going to type ping 192.168.1.1, success. So I know in my little environment here, I can ping from this PC. I can ping to the other PC through my switch. I can now ping all the way up to the default gateway. Up to this point, we have not configured anything related to routing though. So I'm going to create another network here. And I'm going to make this one 10.0.0.0. I'm going to go back to the bottom left here, and I'm going to pick some end devices, and I'm going to pick PC again. And I'm just going to put a PC here. And I'm going to say this PC is going to be 10.1.1.25. Now, I only need one, but you could add as many devices as you want to have represented. So I have my PC. Now I'm going to click on the PC. I'm going to go to the desktop, IP configuration. I set that address to be 10.1.1.25. We'll leave the default subnet mask. I will set the default gateway to be 10.1.1.1. That's the gateway I intend to use. So now that device is configured. I'm going to go back to my network devices. I'm going to add a switch. And I'm also going to add a router. So basically the same configuration we have on the other side. I'm going to go to my connections, and I'm going to connect my PC. Same as we did before. Fast Ethernet 0. I'm going to connect it to my switch, and I'm going to use fast Ethernet 01. So we have a connection between the PC and the switch. I'm going to add a connection between the switch and my router. I'll use gigabit Ethernet 01, and I'm going to just connect that to my router, and I'll use gigabit Ethernet 00. Now I'm going to go to the router, and on the config, gigabit Ethernet 00, I'm going to just set the address, which is 10.1.1.1. That's just the address I chose. And I'm going to turn the interface on. As I said before, you can see all the syntax that I could have typed in if I wanted to type this in instead of using the actual graphical tools. If I go to my PC, I'm going to click Command Prompt, and I'm going to type ping 10.1.1.1. So I can ping through my switch up to that router that we just defined. Now I need to configure some routing. Now for the router, you could choose automatic or you could choose this copper crossover. But when I select the router, I'm going to choose gigabit Ethernet 1. And on the other router, I'm going to choose the same. Gigabit Ethernet 1. So we have a connection between the two. What we have to do is actually configure a route between the two. Now, the way routing works, I need a network between these. I'm going to use 172.16.0.0. Now, the reason we do this is because you're going to have a network really that resides between these two routers, and that's how the routers will communicate with each other. So I'm going to click this router on the left side here. I'm going to go to gigabit Ethernet 1, and I'm going to enter the IP address 172.16.0.1. I'm going to use the default subnet mask, and I'm going to turn that on. So now that router has an address. I'm going to go to the other router. I'm going to go to gigabit Ethernet 01, and I'm going to use the address 172.16.0.2, and I'm going to use the default subnet mask there, and I'm going to just turn that on as well. Now, I'm going to put 2 notes here, just so it's clear. 172.16.0.1 on this side. 172.16.0.2 on the other. So my routers have those addresses, so they can communicate with each other. The ultimate goal is to actually route traffic between these two networks, the 192.168.1.0 and the 10 network. That's the ultimate goal. So what I have to do is define a route. So when I am on the router on the 192.168.1.0 network, this router has to be told whenever you receive a packet and the destination address is on the 10 network, you have to route that packet to this router on the other side. So I just need to add some routes. To do that, I'm going to start with my router on the 192 network first. I'm going to go to this static route. And on the static, the network we are trying to connect to is 10.0.0. Subnet mask. I'm just going to use the default subnet mask for a Class A network. And now it wants the next hop. What's interesting about this, the next hop is the router on the other side, this 172.16.0.2. So for next hop, I'm just going to enter that. 172.16.0.2. That takes care of that route. And as we said before, it gives you all the syntax for adding that actual route. So now, from the point of view of my PC here, the 192.168.1.25. If this is trying to route traffic to the 10 network, the moment it determines an IP address is on the 10 network, it's going to send that through the switch up to the default gateway, which is the 192.168.1.1. This router says, oh, I have a route that says any traffic destined for the 10 network has to be routed to IP address 172.16.0.2. It gets to the router then passes it through the switch to that PC. Now, I do have to create a route coming the other direction, because if not, any return packets would simply be lost. So for my router here, I'm going to click on that and go to static. And we're going to enter the network 192.168.1.0. I'm going to enter the default subnet mask. And in this case, any traffic that's going to the 192.168.1 network has to be routed to the router 172.16.0.1, because that's the connection point. So I'm going to enter that address, 172.16.0.1, and add. So if we go back and look at this picture, now I'm going to set the address on this and just in the graphic, but 10.1.1.1. So now, from the point of view of this PC, any traffic that is destined for the 192 network leaves this PC through the switch, goes up to the 10.1.1.1 interface. That simply looks up the route table and says, I see you're trying to get to the 192.168.1.0 network. I have to send you to this IP address, 172.16.0.1. The router looks it up in the route table, and then you exit out of this 192.168.1.1 interface through the switch to that PC. Well, let's see if it's working. So I'm going to click on my PC. Now, the PC I'm on right now is 192.168.1.25. I'm going to try to ping the other side. So I'm going to ping 10.1.1.25. For some reason, that first request timed out. It may have still been setting itself up on the back end. Some of these configurations, when you put them in, takes a moment before it fully applies, even though all the icons have turned green. But I can see my last three requests did receive replies. And if I just run that again, you'll see now we get 100%. So it was just likely still being set up on the back end. But now we look to be fully configured. I have end-to-end connectivity through this entire diagram. So this is a very useful tool to actually play with, but I just want to show you this so you are aware there is such a thing as this Cisco Packet Tracer, which is free. And so when we mention the term routing, switches, things like that, you just have an idea of kind of how all of these logically go together. To summarize what we just defined, I had a PC with an IP 192.168.1.25. That PC was then connected to a switch. No configuration defined on the switch. And I had a router. The LAN side of that router has an IP address of 192.168.1.1. From this PC's point of view, that is your default gateway. Meaning, anytime you try to connect to any device that has an IP address that's on a different network, your computer will send all of that traffic to 192.168.1.1 under the assumption that device will have routes that will then connect you to networks that have whatever device it is you're trying to connect to. On the other side, we did the same thing. I have a PC 10.1.1.25 connected through a switch up to a router. The LAN side of this router is 10.1.1.1. That is the gateway for that PC. So at that point, you have connectivity within each of these respective LANs. What we need to do is simply create a route between the two networks. From the 192 network's point of view, I simply need an IP route that says any traffic destined for the 10.0.0 network. Ultimately, that traffic will be sent to the device with the IP address 172.16.0.2. So now, my router here says, okay, I see you're trying to send me a packet, and that packet has a destination address on the 10 network. It says I'm not directly connected to the 10 network. So let me look at my route table and see who I should send this to. Looks in the route table, finds that 10 route, then it just sends that to the 172.16.0.2. This router then knows it has an interface on the 10 network, so it knows it is directly connected to devices on that network, and it just routes that or passes that to that PC itself. Then you just need a route going the opposite direction. So from the point of view of the 10 network, I will have a route. This route will say any traffic destined for 192.168.1.0 network needs to be routed to 172.16.0.1. So that traffic now leaves this PC, gets up to the router. Router looks in the route table, finds the 192.168.1 network, sends it to that 172.16.0.1 address. Then it just gets passed back to that PC. So pretty neat concept overall. But whenever you hear routing, that is at the core of what a router does. Connect different IP networks based on what we've configured in these route tables. So pretty neat overall and not overly complicated. Now, we don't do a deep dive through different configurations of routers or anything like that. But if that's something that you want to get more into as you progress in networking, this Cisco Packet Tracer tool will be your best friend. I have spent thousands of dollars on hardware, routers, switches over the years. This Packet Tracer tool eliminates the need for that. Just download it and configure everything you want. Earlier, we discussed VLANs. If I wanted to set up my own VLAN, which will just segment my switch, so I can have one switch and I can have computers connected to that switch, and I can determine which computers can communicate with each other just by configuring virtual LANs or VLANs on the switch itself. So in this example, I'm going to create two VLANs. We're going to name one VLAN 10 and the other VLAN 20. And I'm going to say VLAN 20 is for my test dev environment. I'm going to go to my end user devices, and I'm going to put a few PCs on each VLAN. So we'll just put 2 on each side. Now when I go to my network devices, I'm going to choose a switch, and I'll just take this 2960. That's fine for what we need. Now, so we don't get confused, I'm going to change the name of each of these computers to the IP address that we want the computer to have. So the first one will be 192.168.1.10. I'm going to make this one 192.168.1.11. And we'll make the first PC in VLAN 20, 192.168.1.201, and I'll make the second 192.168.1.202. Now, when I connect the computers to the switch itself, I'm just going to go to my connections, and I'm going to choose my Ethernet connection here. We'll pick the fast Ethernet 0. Now, we're going to do that for each of these PCs. But I'm going to connect this first PC here to fast Ethernet 01 on my switch. We'll choose that again, and I'll pick same fast Ethernet 0. And we will pick fast Ethernet 02 on the switch. Now we just rinse and repeat. When I go to the other two, I'm going to pick fast Ethernet 03. And then fast Ethernet 04. So we know the port numbers. 1, 2, 3, 4. Now we do have to give the PCs IP addresses. So I'm going to go to this first PC we added here. And on the desktop, I'm going to go to IP configuration. And we are just going to enter the IP address that we typed in. 192.168.1.10, so same address we typed in the interface. And subnet mask will autofill itself when we just click in the box. And we'll do that for the other three. 192.168.1.11. Then we have our 201. And our 202. That's done. Now notice there is no save button or OK or apply or anything like that. Just whatever you type in, it accepts. So just be careful with these configurations, or just change it to whatever it is if you make a mistake. Well, everything looks to be green. We have all these little green triangles here. So I'm just going to go to my first PC, to the command prompt, and we're just going to try to ping the others. So from the computer with the address ending in .10, I can ping the .11. I can ping the 201, which is my computer here. And we can ping the 202. So we know right now we have connectivity through our switch between all four computers. I don't want that though. What I want is for the computers in the test dev environment to only be able to talk to each other, and computers in my VLAN 10, I want those computers to only be able to talk to each other. So if I just go to the switch itself and go to the config, you'll see there's a VLAN database option. Now there are a few VLANs created by default. The only one we really care about is VLAN 1, which is actually named default. So that's always going to be present. Then we have some other VLANs for different types of media, but we're never really concerned with those. Token ring and FidiNet is how we pronounce that. We don't really use those anymore, or we don't use those anymore. So what I'm going to do is create a new VLAN. So my first one, VLAN number, we're going to say 10. And I'm going to say, in my little small environment here, I'm just going to name that prod for production. So we'll add VLAN 10. And then I'm going to add VLAN 20. And I want that to be my test dev VLAN. So now on the switch itself, we have two VLANs, well, two additional, prod and test dev. Now, if you wanted to know how to do this in a Cisco environment specifically, you can see here, when I am in the switch itself in this config mode, VLAN 10, then that changes this prompt to config-VLAN, and we just type whatever we want it to be named, name prod, and that creates your VLAN. VLAN 20, whatever we want that to be named, test dev. So that's the exact syntax. And if you were doing all this by command line, you could simply have gone to CLI, and you could just type that directly in here if you want to become fluent with the command line itself. But since we're kind of looking at this from a vendor neutral point of view, we'll just use the config here. So on the VLAN databases, we do have our 10 and 20 now added. Well, I'm going to go to the interfaces. We know that fast Ethernet 01 was connected to this computer here with the IP address ending in 10. Fast Ethernet 02 was connected to the computer ending in 11. So when I click on the interface, it has this VLAN option. All computers default to go to VLAN 1. That's your VLAN that's applying to everything. So all I'm going to do is change that from VLAN 1 to VLAN 10, my prod. And again, you can see the syntax. From the config mode, interface fast Ethernet 01, that's the interface we want to manage. switch port access VLAN 10. So now that port, whatever's plugged into that port, regardless of what type of device it is going to be on VLAN 10. And I said fast Ethernet 02, we want it to be exactly the same. So when I go to fast Ethernet 02, defaulted to VLAN 1, we just change it to our VLAN 10, the production environment. And again, you'll see the syntax for that as well. So what should happen now? I should be able to ping from my 1.10 to 1.11. I should not be able to ping 201 and 202 because they're still on their VLAN 1. So in my command prompt, we'll see I was successfully able to ping the .202 IP address earlier. Well, if we try to ping that again, now it does not work. It's just going to slowly begin to say request timed out. So I'm going to hit Control-C to stop that, just so we don't have to wait on all the timeouts. If I tried to ping the IP address ending in 201, it would do the same. It would time out. But if we ping 192.168.1.11, we expect a reply. And we do get a reply. So now, I know that this PC here and this PC can communicate because they're on the same VLAN. Now, these two PCs can communicate with each other as well, the 201 and 202, because we left them on the VLAN 1. But if I wanted to move them to that test VLAN we created, now I remember they were on fast Ethernet ports 03 and 4. So I would just go to 03 and I would choose VLAN 20, the test dev. And I'd go to fast Ethernet 04 and I would do the same. So now we can see here, those interfaces, 03 and 04, are on switch port access VLAN 20. And that's the syntax for the 03. Switch port access VLAN 20. So if we pick one of these, now notice this did turn to an orange circle, so it'll take a moment for that connection to be established. So I can see one is done because it has this green triangle on it now. Looks like they're both done. So this is the computer with the IP address 201. So if we just ping 192.168.1.202, we expect a reply, and we do get a reply. If we try the computer ending in, we'll say ending in .11, we do not expect a reply because, as we said before, they are now on different VLANs. Pretty fascinating. Now, for VLANs, we did this port-based. The only concern that leads to is what port you're connected to determines what VLAN you're in. So if someone were to go into your closet or server room and they're troubleshooting connectivity and they start moving cables around, it's going to change which VLAN you're on. If you are on port 1, that's what you're connected to, and they're troubleshooting, and they move you to port 4, your PC is now physically connected to that other VLAN. So many devices support VLANs based on MAC addresses. So you could simply say this MAC address is on this VLAN. Then it does not matter what port you get plugged into. You'll be associated with that specific VLAN. So there are some different configurations that can exist. But here, looking at my switch, if I just hover over it, we can see all my links are down except for fast Ethernet 01 through 4, because we have devices connected to those, so those are up. I can see the VLAN. I can see the MAC address associated with each of those. The IP address will eventually show up, but for whatever reason, in the tracer, that is just always slow to actually populate. But pretty neat overall. In Lesson 2, we will cover managing and troubleshooting IPv4 network connectivity. This will include IPv4 troubleshooting methodology, tools for troubleshooting IPv4, and we'll also look at a tool named Wireshark. This is how we can think through a problem. You just go through a series of questions and it'll help you narrow down what the issue actually is. Can the problem that you or your user are experiencing, can it be duplicated? What is working and what is not working? What's the relationship between the things that do work and the relationship with those that do not work? Does it work for other systems on the network, or is it isolated to just one system? Has this ever worked? Meaning, is it a new configuration and it's not working initially? Or was this working up until this moment in time? If it was working in the past, what has changed since it last worked? Those are crucial questions to resolve any type of problem. Now, most people that are troubleshooting just analytically think through problems in this type of context, whether it's a networking problem or fixing something in your own home. It's just kind of the thought process of many people. In this example, let's say my problem is I'm using PC1 and I am unable to connect to file 01. A few things come into play here. One is going to be name resolution. Looking at this, PC1 is using a DNS server 192.168.1.10. That is this server on the network here. The purpose of DNS within our network is for you to have the ability to type in a name, and it simply takes the name and resolves that name to the IP address. So if my user is actually typing in file 01 and they cannot connect to the file server, my first thought would be maybe that name is not getting correctly resolved to an IP address. An easy way to test that, I would simply try to connect to the IP address of file 01. So instead of using the name file 01, we would use the IP address 192.168.1.17. If I can connect to that by IP address, but not by name, we know it's a name resolution problem, and maybe we need to start looking at issues on our DNS server itself. If I cannot connect to it by IP address, nor by name, then I know it's not a name resolution issue. It's something larger than that if I cannot communicate by IP either. Next, we could see if this is affecting other systems. So I could just try to connect to PC2 or to the DNS server itself on the network to see if PC1 can connect to any other devices on the network. If I cannot connect to PC2 by name, by IP address, then PC1 likely has some type of network communication issue. If I can communicate with PC1, then we know it's not an issue with PC1 having network connectivity, maybe an issue with file 01. Next, I could go to PC2, and from PC2, can I connect to file 01 by name? Can I connect to it by IP address? If I can, then I know there's nothing wrong with file 01. If I cannot communicate with that from PC2, then what we know, there's likely something wrong with file 01. So we can eliminate PC1 as being the problem system if you cannot communicate through PC2 either. So that's just an easy way to kind of narrow this down to say it's a problem with one specific system like PC1, or we test this from multiple systems and determine it's not a problem at the end user level. There may be a problem at the server level or with network connectivity up to that server or whatever device it is we're having an issue connecting to. If I'm trying to connect to the internet, we go through the same process. If PC2 is trying to go to Microsoft.com and it fails, well, the first thing I would do is try to go to a different website. From PC2, can I get to Google.com or Cisco.com? If you can get to those websites and you know there's not a network issue, there's not a name resolution issue in the environment, there just may be something temporarily wrong with Microsoft that's disrupting your connection. If you cannot connect to any websites on the internet, then that's a bigger concern. One of the first things we would do if I cannot connect to any websites, we would try to verify that we have connectivity to the default gateway. If I can connect up to the default gateway, then I know everything network related inside my network is defined correctly. So it's not a network issue inside my network. Now I would want to see if I can connect to something on the internet by IP address to make sure it's not a name resolution issue. A common internet site you can use just to verify connectivity is 8.8.8. This is actually the IP address for the Google DNS server. It always responds. If I can connect to that IP address, but I'm unable to resolve any website by name, then we would start looking at our DNS server. Something would be going on with name resolution. That logic we can basically apply to any type of scenario that we run into. Can you duplicate this? How many systems does it affect? What's working? What's not working? Has it ever been working in the past? If it was working in the past and not working now, has anything changed since it was last working? So just working through those can help you quickly narrow this problem down and get a resolution as soon as possible. Let's run a troubleshooting scenario. Right now, everything on my computer is working fine. I can browse the internet, I can connect to resources, everything is fine. That's our starting point right now. So let's say my user. One of the things my user routinely does is actually browse the network. And they connect to this machine named testdev, and it has this shared folder named movies. So maybe that's part of my user's job is to upload content into this shared folder. That's working fine. Normally, it's working fine. Today, my user calls and says they have a problem. Now, let's pretend we don't see this. I'm going to disconnect my network here. And just to make sure it does not automatically reconnect while we're talking, I'm going to click forget, just to make sure it does not automatically end up reconnecting. Now I do not have a network connection. So I instinctively know I can't connect to anything right now. But let's say I decide I want to try to browse the internet first. So I'll pull up my browser and it says you're not connected. So I cannot get to the internet. Okay, there could be many reasons. The router could have an issue. The website I'm trying to connect to could have an issue. The first thing I would do is simply try another website. So I'm going to try rtsnetworking.com. Oh, I can't get there either. So it's not just one website that seems to be down. It's a lot of things that are down. So we have some internet issues. Now, something I would also do, I'm going to go to PowerShell here, and I'm going to ping that name. I just tried to go to rtsnetworking.com. It immediately comes back and says, ping request could not find host RTS networking. So I 100% know it's not a problem with Microsoft Edge or Google Chrome or Mozilla Firefox. In no way is this related to your browser on your device. So we've eliminated that at an application level. I just cannot connect to that RTS networking. And I'm going to try to ping google.com as well. That's not working. So you could try a few more websites, but at this point we have determined the internet itself is not working. Now that's one concern. Another concern, my user, they were browsing the network earlier and they were going to that test dev, but now it says computers not connected to a network, click to connect. That's a problem. To do some troubleshooting in PowerShell, the first thing I'm going to do is make sure my network adapter in my computer itself does not have a problem. To do that, I'm going to ping the loopback address, which is 127.0.0.1. I always get a reply. If you do not get a reply, either the network adapter in your machine itself is bad, or the protocol stack may be corrupt and may have to be repaired. Now, I know I am not connected to a network in any way right now. So all this does is go down to your network adapter in your computer. And I always say it goes to the edge of your network adapter through the protocol suite. Then it comes right back and says, yep, that was successful. We can communicate up to and through the network adapter. So I can eliminate the hardware in my computer itself as being a problem. Now, for the network I'm on, I wanted to connect to that machine testdev. Now, I'm going to type ping testdev. That's the computer that had that shared folder. Comes back, says, nope, we can't find testdev. Now, I just know the IP address of testdev is 192.168.1.200. So I cannot connect to that by IP address either. Just gives me these error messages of general failure. So I cannot connect by name, cannot connect by IP address to a remote machine on the network. Now, I would try a few other machines on the network to see if it's just isolated to that one machine or not. And I would also try my default gateway, which in my case is 192.168.1.1. So I cannot connect to anything on the network or beyond, so nothing out on the internet, but I know my network adapter itself It does not have a hardware level or protocol level problem. So you're kind of stuck at this point. What we would do, I would simply go to another computer. From another computer, can I connect to the internet? Can I connect to other devices on the network? If that is in fact true, you know there is something about your computer or your computer's configuration that's stopping you from connecting to the network itself. That's when we would start checking things like, is the Ethernet cable plugged in? Are you connected to a wireless network? Now I'll reconnect to that network. Now, it's unlikely you would ever find yourself disconnected from a network like that. Or if you do, just so you would notice you didn't have your Wi-Fi icon. So that would have been pretty easy to troubleshoot. But I just outlined this as the steps. If you can't connect or your user can't connect, can they connect to the loopback address? Just eliminate hardware as their problem. Can they connect to other devices on the network itself? Yes, no. Can they connect to sites on the internet? Yes or no. And you can now start to isolate that problem. Now that I'm connected back to the internet, everything's going to be working. Ping the default gateway, we get a reply, the 192.168.1.1. If I try to ping test dev, now that is actually an IP version 6 address that's being returned because I don't have that disabled on my network. So if I wanted to ping using IPv4, which we do, I will just type ping the computer name space -4. That pings using 192.168.1.200. And I'm going to hit the up arrow to go back through my history a bit. And I'm going to try to ping rtsnetworking.com. That works. So now everything's working. Now let's look at a more complicated issue, slightly more complicated. I'm going to go to control panel to my network connections here. So for my adapter, I'm going to set a static IP version 4 address. I'm going to use 192.168.1.205. And for the gateway, I'm going to use 192.168.1.10. And for my DNS server, I'm going to use 192.168.1.1. And I'm just going to OK all of that. Now let's see what's working. I'm going to go back and see if I can browse my test dev. So I'm just going to refresh this screen here. That's my test dev. So clearly I have connectivity on the LAN. But when my user tries to go to the internet, and in the browser, I'm going to go to rtsnetworking.com. It's taking a little longer than usual to load. On this other tab here, I'm going to try to go to yahoo.com. That's not loading either. Now, what's interesting is Microsoft, this page loaded. And Google did load on the other tab. So when you click on this and it pops up like this, my first thought is, well, the internet looks like it's working. I'd see web pages showing up here. You can click on some of these links, but they don't go anywhere when you start to click on them. That's because all browsers will cache content to speed up the internet. So if you can see your homepage, that does not necessarily mean you're connected to the internet. What you may find is anything you click on here, once you click on it, does not open up, then you get these error messages. That initially can be a little confusing. So when I click on like the link here, you'll see these pages aren't really working. Now I'm going to go to yahoo.com again. Oh, actually, that gave me a message that said page was not responding, but you'll see RTS networking does not work. The Microsoft, that page never loaded. Can't get to Yahoo. So clearly, I have an internet problem. It says, this page is not responding. I'm just going to click exit page because it's not going to work. But I can still browse through my local network. No problem seeing any of these resources on the network. And we can browse directly through. So I know that part's actually working. I could click on this and I can see my Pirates of the Caribbean movie. So all those things are working just fine. My problem is the internet. So From a troubleshooting point of view, I would go to another computer and see if I can connect to the internet. If I can connect to the internet from another computer on the same local area network, then I know the internet's not the problem. My router on the network is not the problem. Something is wrong with the computer that you're using. So if I go back to PowerShell, I'm going to type ping my default gateway. (192.168.1.1). So I can ping the default gateway. But I'm going to try to ping rtsnetworking.com. That's not working. I'm not getting a reply. Now I'm going to hit Control-C. That just runs a break, so I don't have to wait for this to keep going through and timing out. A very common internet address is the IP address of these Google DNS servers. These has an IP address of 8.8.8.8. If you're connected to the internet, that will always respond. You'll always get a reply from those addresses. So again, we just verified this one machine cannot connect to the internet. But you can browse around the local network. So we know exactly what the problem is. We just don't know what's causing it. Well, I'm going to type ipconfig. And I can see and we're looking at IP version 4. So I can see my IP version 4 address is 192.168.1.205. I can see my subnet mask. That's valid for my LAN. The IP setting that controls my computer connecting to remote networks like the internet is the default gateway. So I can see the default gateway here is 192.168.1.10. Now, is that the correct default gateway for the network that you're on? You have to know that information. If you don't know, you could go to another computer and type ipconfig and see if they have the same default gateway. I know that is the wrong default gateway for this network. My default gateway is actually supposed to be 192.168.1.1. So when I set the static address, we just made a typo in that default gateway. So if I go back and we now correct this, we have the right default gateway. Immediately everything should start working. If I go back to PowerShell, ping the 8888, we get a reply. Well, we don't need to ping anything else on the internet. I know I can connect to the internet if that's working. But if we just go back to the browser for a moment, and well, these pages are already refreshing. My RTS networking. Now my website is, I'm able to connect to it. So everything's working now. So that process just kind of helps us think through what could be causing the problem. Is it your device, a problem connecting to resources on the network itself, problem connecting to resources on the internet? Narrowing that down just makes troubleshooting much easier for us overall. One of the most common tools you will use for troubleshooting is ipconfig. ipconfig, if you run that command by itself, you will get basic information related to your IP configuration. If you want to view help, you can type ipconfig /?. That will give you a list of all the possible parameters that you can use along with ipconfig, and it will also give you a description of each of those. So that's very useful. ipconfig/all will just give you a lot of additional information that you don't receive if you type ipconfig by itself. Most end-user devices like mobile phones, tablets, laptops, even desktops will have IP addresses that are automatically assigned from a DHCP service. This could be a wireless router. It could be a gateway that your internet service provider sent to you. It could be an actual Windows server or a Linux server on your environment. So there are many different types of devices that can automatically assign IP addresses. If you have an IP address automatically assigned, two very useful commands are ipconfig/renew and ipconfig/release. If you type ipconfig/release, you will release an IP address that has been assigned to your device. If you type ipconfig/renew, you actually send a broadcast message out looking for a DHCP server, and you will attempt to have another IP address assigned to your device. So those are useful, release and renew. Release and renew by itself is for IP version 4 addresses. If you use IP version 6 on your network, release 6, renew 6 will do the same, release and renew your IP address, but it will only do that for IP version 6. So one's for IP version 4, one is for IP version 6. Now we do cover IP version 6 in one of the last modules in this course. Related to name resolution, we have some DNS parameters as well. So we have ipconfig/display DNS. This will show you all the contents in your DNS client resolver. We also have ipconfig/flush DNS. This will actually purge everything in your DNS client resolver cache. Now the client resolver cache itself just contains names that you have recently resolved. So if you go to a website like rtsnetworking.com, your computer for some number of seconds will retain that in cache. Now one of the advantages of that, if I go to a website, my rtsnetworking.com, and on the website you start clicking on links on the website, well, every time you click on a link, it has to be resolved. I don't want to send a request all the way through the entire DNS process every time I click on a link on a website I'm actually browsing. So what the DNS client resolver will do is simply cache that name and the IP address it resolved to. Just makes everything more efficient. And if for some reason you're troubleshooting, you could possibly run ipconfig/flush DNS and it purges all of that content. The problem that flush DNS will solve is not really a common problem, but if you were connected to a server in your environment and you now have the name and IP address of that server, maybe it's a web server or a file server, you now have that name cached. If the IP address of that device were to change and you still have it in cache, your computer would keep going to the old IP address, which may no longer be relevant. So ipconfig/flush DNS will just get rid of that, then it goes through the whole name resolution process again. Or you could simply reboot your computer and that will always flush the DNS as well. In my command prompt, if I type ipconfig by itself, I get pretty basic information. Here I can see my Ethernet adapter and some of these other adapters. The media state says media disconnected because they're simply not connected right now. And then I have my wireless LAN adapter Wi-Fi. That is connected right now. So I see some basic information related to IP version 6, and I see some information related to IP version 4. So I see my IP version 4 IP address, my subnet mask. I see my default gateway for IP version 6 and IP version 4. So just very basic information. Now I'm going to run ipconfig /?. That is our help. If we scroll back up a bit, we can see when I run that, the first thing it gives me is this usage, shows me all the parameters you can use with ipconfig. So there are quite a few. Under this options, it gives me the parameters and a brief description of each of the parameters. Now, some of these parameters are not commonly used and some are actually deprecated. ipconfig has not changed other than the options release renew IP version 6. Other than those, this has not changed in several decades. If we keep scrolling down, they do give us a few examples of the syntax, but that's pretty straightforward. It's ipconfig / the name of your parameter itself. Well, now I'm going to run ipconfig /all. This is going to give me some detailed information. Now, if we go back up, all these things above my other adapters, like my Ethernet adapter here, you'll see all that still says media disconnected, so there's nothing for us to really look at there. But if I go to my adapter that is connected, the wireless LAN Wi-Fi, looking at this, I can see my physical address, which is the MAC address. I can see that my computer is using an IP address assigned from DHCP because it says DHCP enable yes. We get some IP version 6 information. I can see my IPv4 information, but what we did not see with the ipconfig by itself, I could not see when my lease was obtained. So I can see right now, Friday, January 13th, 2023, at 4:23 and 8 seconds p.m., this lease was obtained, and I can see when it expires. So this lease is assigned for 24 hours. I can also see the IP address of my DHCP server, 192.168.1.1, and I can also see the IP address of my DNS servers. In my case, that's also 192.168.1.1. So very useful that is. Remember this time, the lease obtained 423. I'm going to type ipconfig /release, and that's going to release my IP address. So that released the IP version 4 address. So notice now under my wireless LAN adapter Wi-Fi, my IPv4 settings completely gone. If I wanted to release IP version 6, the command would have been ipconfig /release 6. Well, now I want to renew those. So I'm going to type ipconfig /renew. That should be done. Now I'm going to hit the up arrow and just go back through my history. So the up arrow on your keyboard will go through your previously typed commands. I'm going to go back to ipconfig /all. And I can see my IP address has been assigned. So I do have an IP version 4 address. And notice the lease obtained is now Friday, January 13th, 8:49 p.m. It was 4 p.m. So that release just told DHCP I no longer need this IP address. When I type ipconfig /renew, it simply sent a message to DHCP saying I need an IP address, and DHCP assigned me a new IP address. That would have also happened if I had simply rebooted my computer. Each time you reboot your computer, it will contact DHCP and it will automatically have that address assigned. We do have a lesson coming up that is completely dedicated just to DHCP itself. Now it gets interesting. Of the ipconfig commands, the parameters I find most useful are the ones associated with DNS. I say most useful. Maybe most interesting would be more appropriate. But I'm going to run ipconfig /flush DNS. Now this is just going to purge everything in my DNS resolver cache because there's probably just a lot of stuff in it from me surfing the internet. Now I'm going to type ipconfig /display DNS. When I run that command, ipconfig /display DNS, we have just a few things showing up, and many of these are associated with my Microsoft 365 subscription. So we have 2, 3, 4, 5, 6 things showing up that are just present right now in my DNS resolver cache. Well, what I'm going to do is type ping rtsnetworking.com. We get a reply. So notice the IP address that resolved to 185.230.63.186. So just remember the last number is 186. Now, if I hit the up arrow, I'm going to go back to my ipconfig /display DNS. A few more settings show up. But if I scroll up a bit, I have this rtsnetworking.com section here. And in this rtsnetworking.com, that is the record name. The IP address it resolves to is ending in 186. When I pinged rtsnetworking.com, that's the IP address that was resolved. Now, if I scroll down, there is an IP address that ends in 171. There's one that ends in 107. So 3 IP addresses have been resolved to this rtsnetworking.com name. Now, the reason it's 3 IP addresses, that's really not a concern for us. That's on the back end. That means there would be 3 web servers that actually host this site. So if for some reason this 186 was offline and could not respond, one of these others would simply deliver that website to your browser and you'd still browse the website. So not a single point of failure, and also used to load balance traffic. If you try this on your own machine, ping rtsnetworking.com, and then you type ipconfig /display DNS, you are going to see perhaps a different IP address show up here. Instead of 186, yours may resolve to the 107. So this load balances through a process that's called round robin, where it just kind of rotates the records through. So when that gets resolved, some people get resolved to 186, others will get resolved to the address ending in 171, others to 107. So it just kind of balances the load. Pretty neat overall. Another very common troubleshooting tool is ping. With ping, I can sit at my computer and I can send messages to your computer. When your computer receives a message, it will process it and then it will send me a message back letting me know that it received the message that I sent. So I would know we can communicate with each other. If I do not get a reply, I know we cannot communicate. I don't know why we can't communicate. I just know I sent you some messages and you did not respond. So we would start looking at network issues possibly. We know we are just not talking to each other. Ping has several parameters you can also use. With ping, by default, if you ping, you send 4 echo requests and you get 4 replies back. That's just the way ping natively works. If I want to ping a specified host until I either close my command prompt or until I hit Control-C to stop, then with the ping-t, it will just keep pinging. So it'll just go indefinitely until you decide you want to stop. If I'm pinging by IP address, I can use ping-a, the IP address, and it will actually resolve the IP address to the name of the host and let me know the name that IP address actually resolves to. The -n lets me specify how many echo requests I want to send. By default, when you ping, you send 4. If I want to send more than that, I could just specify a specific count, or as we said, you could do -t and it will just ping until you actually stop it. You can also set the time to live. So I could ping -i, we choose a number, that's our time to live, followed by the IP address we want to ping. Not very often do you actually have to use that. And I can also force IP version 4 or IP version 6 by typing ping-4 or ping-6, followed by the name that I actually want to ping. Let's look at these in the interface. Back in my command prompt, I'm going to ping rtsnetworking.com, and as expected, I get 4 replies. It resolved to that IP address, 185.230.63.186. So I sent 4 echo requests, and it sent me back 4 echo replies, so I know I am connected. I'm going to hit the up arrow key, and I'm just going to insert a -t. Now when I hit enter, this will just continuously ping. It will not stop. I mean, you could leave this here for days and it would ping for days. So it's never going to stop until you either close the command prompt itself, or if I hit Control-C on the keyboard, that Control-C is a break and then it actually stops. This can be useful if you're looking for some type of intermittent connectivity where you think you get a reply, but it seems like the connectivity may be kind of going in and out. You can let that run and just kind of look at it go through and see if anything's dropped. Now, we do know from me running ipconfig, my computer has an IP version 6 address and an IP version 4 address because I've simply not disabled IP version 6 on my computer. If you have both enabled, IP version 6 and IP version 4, IP version 6 is the preferred protocol. Now, what that means to me, when I ping rtsnetworking.com, it's using IP version 4. But if I were to ping google.com, it's using IP version 6. The reason, rtsnetworking.com does not have an IP version 6 address assigned to it. Google.com does have an IP version 6 address. So my computer briefly does a query to say, Google, do you support IPv6? Then it pings using IP version 6. When I connect to rtsnetworking.com, it determined that RTS networking does not support IP version 6, and it just used IP version 4. So there's no appreciable delay when it checks to see if you use IP version 6, but that's why when you ping some things, this could be a computer in your environment, a server, just something that you can connect to that supports IPv6, you may get that response. I actually have a server in my environment named testdev. It has IP version 6 enabled. So if I ping that, it does use IP version 6 by default. Now, if I want to use IP version 4, I could simply insert -4. So ping -4 testdev. It uses the IP version 4 protocol, and I can see the address is this 192.168.1.200. If I wanted to ping Google, I could insert -4. And it's going to use IP version 4. So pretty straightforward. Now, when I say I have IP version 6 enabled on my machine, all I actually mean is if I were to open my network adapter. So I'm going to go to Control Panel, Network and Sharing Center, And I'm going to go to my adapter settings here. And I'm going to click on my adapter properties, Internet Protocol, TCP/IP v4. So that's my IP version 4. You'll see if I scroll down, I have TCP/IP v6. I could simply deselect this check here and click OK, and it would disable IP version 6 on my system. I've not done that. So that's why when I run ipconfig, we see the IP version 6 address, and when I ping, it's using IP version 6. But disabling it is nothing more than deselecting that. If you want it enabled in the future, you could come back and just click this and it would be enabled. But it is enabled by default when you install the operating system. So that's why I leave it for all the demos and all those things, because likely that's what you're going to see on the machines you're actually using. One of the things that ping does not do is help you figure out where a problem is. If I cannot ping rtsnetworking.com, I don't know if there's a problem on my network. There could even be a problem with my computer. There could be a problem with my internet service provider. There could be a problem with the network that hosts rtsnetworking.com. There could be a problem with the server itself. Ping does not help you with any of that. Ping just says, I cannot get from you to that destination. Onus is on us to figure out why. That's where a useful command, traceroute. Now the command itself is traceRT, but traceroute is what it's actually called. With this, I could specify rtsnetworking.com, and it's going to test every hop along the way. So when I run that from my computer, the first thing it connects to is the default gateway on my network. Then it connects to something at my service provider, which is Verizon. So that IP address, then that IP address, my third hop. So it goes through all of these hops, and it is up to Wix. Wix is my hosting provider. So I know at this point, I have made it that far. So I know everything's good on my network, my provider's network, made it to Wix. There is this request timed out, which initially looks a little odd, but then after that, hop 10 actually worked, and that is ending in 186. So that's the IP address. So that traced the entire route. This request timed out in the middle, all that means is that device does not respond to ping traffic. Ping is in this family called Internet Control Message Protocol, or ICMP. That is the protocol itself. Well, ping is a utility within that protocol. So when I run traceroute, you're actually pinging each of these. Same exact type of traffic. So that device where it says request timed out, that device simply said, I'm not responding to that type of traffic. Perhaps that's a firewall, a server. We have no idea because it just did not respond. Some websites, like if we were to ping Microsoft.com, they do not respond to this traffic at all. So I can see that name was resolved to an IP address, but you will forever get request timed out. We know Microsoft is not offline. They just don't respond to that type of traffic because that's their preference. Nothing we can do about that. Normally when I'm using traceroute, it's going to be in my environment. If I have a network in California, an office in California, and I have an office in Mexico, and I have a connectivity issue between the two, traceroute is one of those things you could do to try to figure out where your break is actually occurring. So useful in those types of environments. A command that is very similar to traceroute is path ping. It's a little newer than traceroute, but it's been around quite a while. This path ping was in Windows XP. So not a new command, just newer than traceroute. What I can do with this path ping is I could trace the route to a site. I'm going to run path ping google.com. Now, Google does use IP version 6 addresses. So I'm going to type -4 to make sure I force IP version 4. So path ping -4 google.com. That's going to trace the route to Google. Now, by default, it's going to go over a maximum of 30 hops, but there's not really anything you would ever find that's going to be 30 hops away. Some of these may say request timed out as well, but that'll run for a while, just going through all of those hops. Then it does something very interesting. So it looks like hop 13 is timing out. And that's as far as that actually went. Now it says computing statistics for 300 seconds. What that actually means, it is sending 100 packets to each of these hops, and it's waiting on a reply. So it's pinging each hop with 100 packets, waiting on a reply, and it's going to then come back and tell me, we sent 100 packets, and we only received 98 from hop 8. So in addition to tracing the route, knowing you have connectivity, it will also calculate packet loss. Now that that is complete, I'm going to scroll back up. And you'll see it says this node link lost/sent. So I can see I sent 100 packets to each of those. We have 12 hops total. 0 packets were lost. So I have no packet loss at any of these hops. If there was some type of saturation or delay on the network, you may see a few packets get lost, and you would know at what hop they were lost. So you would know exactly how many numerically and what percentage that actually worked out to be. So very useful that is. The only difference between this and traceroute is traceroute just traces the route and that is done. Pathping will trace the route, then it sends packets to each hop in the route and calculates packet loss. So sort of a better version of traceroute, if you will. One of the most useful tools we have is Resource Monitor. Resource Monitor will allow you to monitor your CPU, memory, disk, and network utilization, and it does a deep dive and gives you very detailed metrics. Now, a few ways to open it. You could just type resource when you click on start and it'll search through and find it for you. Or if you want to browse for it, it's actually through Control Panel, Administrative Tools, has Resource Monitor. When this opens up, we'll see the 4 tabs: CPU, memory, disk, network. So those 4 subsystem components. We are concerned with network right now. When I look at this, I can see all my processes with network activity. I don't really have much connected right now. What I'm going to do is I'm going to go to my remote desktop here. And I'm going to remote desktop to this other machine on my network, 192.168.1.200. And I'm going to click connect. And I was able to remote desktop to that machine. Now I'm just going to minimize that connection. Remote desktop actually uses this MSTSC, Microsoft Terminal Services Client is what it actually stands for. Some places will say Microsoft Terminal Services Connection. So whichever you prefer. Microsoft goes back and forth with those 2 terms. But nevertheless, it is for remote desktop. This MSTSC, I can see how much traffic is sent and received. Now that is just remote desktop traffic. So sending 6,000 bytes, receiving around 4,000 bytes. And this is all real time. If I expand network activity, I can see a few connections here. Now, one of these will be like a sub connection, but it kind of overlaps what we just mentioned, where I have sent received between the 2. Now, some protocols establish multiple connections. Sometimes they're called sub connections, and remote desktop is one of those. So that's kind of at a low level, the network activity. A little more detailed information here. So I have the MSTSE, so that's the actual TCP protocol we're actually using. So that's the application we're actually using. I have the local IP address. That is the IP address of my computer. I have the local port that I'm using. We don't really care about that on our side. I have the remote IP address. That's important. This is what you're connected to. If I slide that over, Remote desktop uses port 3389. So I can see I am connected to that address and the remote port is 3389. Most impressive, I can see the packet loss. So right now there is no packet loss. I would not expect any because I'm on the local network with that machine I'm connected to. So 0% packet loss. And I can also see it is only 20 millisecond latency, which is incredibly fast. But again, you would expect that being on the same network. If we scroll down, I can see listing ports. Well, that's just going to have the ports referencing remote desktop. I'm going to scroll back up and I'm going to deselect this image here so it's no longer filtered. Well, now you'll see OneDrive is in the list because I have OneDrive on my system. You'll see over here the little OneDrive icon. Everything's up to date. So even OneDrive, if I were to filter that, I could see how much traffic is sent and received using OneDrive in real time. And now that's being filtered here. So I can see for OneDrive, it actually has 3 connections. And they are to 3 different remote IP addresses. They are all over port 443. So you get a very detailed breakdown as to how these actually work. Pretty neat. I'm going to pull up Google Chrome now. And for Google Chrome, I'm going to leave that here or just drag it over that small window. But notice for TCP connections, I had 0 to 50 here in this box. And I would say that was about midway. I'm saying that was like 25 connections. When I opened Google Chrome, it went up slightly. So about 40 connections, we'll say. I'm going to go to ESPN. So ESPN.com. And notice this line will skyrocket here. And also notice we have so many connections now showing up in this list. What I'm going to do is filter this for Google Chrome. So right now I'm only looking at connections in Google Chrome. If I slide this over, you'll see under this image, everything is Google Chrome. So it says image, but that's like the application being used. So I can see all of these remote IP addresses are now in Google Chrome. That is a lot of traffic. It is seemingly all on port 443. There is no packet loss for any of those connections. Now, if I pull that up again, the reason it's so many, something like ESPN, this could be a news website. They do this as well. This is not one website. You're looking at a web page, but embedded in this would be multiple ads, things like that. And they all go back to other sites. They're just embedded in this view. So in reality, you are connected to multiple websites is actually what you're viewing. Like this, when I hover over this, you'll notice at the bottom left, it says add click. Well, that name had to be resolved. This had to be populated here. So any of these types of ads that you see show up, they all get pulled into this view, and that can generate a lot of traffic. But I'm going to close that. And when I close it, notice everything starts turning gray. Like you can see these are still black here, but the other ones are gray. Eventually they will all turn gray and they will just disappear because now Google Chrome has no network activity. So eventually that's going to just fall out of the list in its entirety. Now this is great for troubleshooting for a few reasons. One, let's say you are connected to something successfully, so your connection works. You run ping, path ping, trace route, all those things. You're connected and you get some information from those that may be helpful. But what this would do for you, when I'm looking at anything in this, I can see the latency and packet loss, and I can also see all the different connections associated with a certain application. So you'll know every address it's connected to, every port it's actually using. So that is very helpful for many reasons. Let's run one more quick example. I'm going to pull up my browser here and I'm going to open this in incognito. And I'm actually going to close this one. I'm just going to use the incognito one. And I'm going to go to YouTube. In YouTube, I'm going to search for Space Shuttle launch. I love this video here. I'm going to click on this. I'm going to mute it. Now that the ad is done, I'm going to go to settings here, and I'm going to change this to 144p. That is very low definition. So if I look at this in 144p, I'm going to go to my resource monitor, and we are in Chrome. Now I do have, because I had another one open, so I'm going to select both of these instances. One of these will just time out. It's that initial window I had opened. Then I opened the incognito. But notice, well, this first one here is the one we're interested in. I can see my Chrome is right now sending 4,000 bytes, and it's receiving just under 100,000 bytes. Okay, we're down to 75,000 bytes. So we'll say 75,000 bytes right now. If I go back to that video and I change the quality from 144p to 1080p, it'll take a moment, but you'll notice the clarity does get much better rapidly. Now that's in HD. That went from about 75,000 bytes received to over 300,000 bytes. That is the difference in quality. This is interesting because it also explains the difference between standard definition and high definition. If you have users at work that are streaming content through their PC and it's streaming in 720p or 1080p or even worse in 4K, what was 50, 60, 70,000 bytes now could be 5, 6, 7 times as large just because of the quality. So this is an easy way to get a view of that. So if I have a user that uses an application and maybe they complain, their computer seems to be slow at certain times. If that's true, I could look at the resource monitor on their computer and I could see how much traffic is actually being sent and received. So pretty neat overall. Anything related to networking, this can help you with that. In my opinion, this is one of the best monitoring tools that's natively built into operating systems. This is in every operating system, Windows 7 and newer. It's in the server operating systems as well, so quite useful. Another very useful tool is network diagnostics. To access it, I'm just going to go to Start, Control Panel. In Control Panel, I will go to Network and Sharing Center. And there's this option, Troubleshoot Problems. Now, Microsoft calls this network diagnostics. Nowhere here does it actually use that term, but that is the official name. If I click on Troubleshoot Problems, it's going to ask me, what type of problem do you actually have? It's going to give me several options. So here, this additional troubleshooters is going to give me the ability to troubleshoot everything from audio to printing to Windows updates, Bluetooth. Lots of things show up here. 2 are related to what we're concerned with. 1 is an internet connection. Find and fix problems connecting to the internet or to websites. Well, if you click this, you can run the troubleshooter, and it's going to give us some options. It said it's going to troubleshoot my connection, and it's going to do that by trying to connect to Microsoft.com. So just a public internet website. You could run that and maybe it can connect to Microsoft. You could also specify a web page as well. You just specify the URL. So I'm just going to type rtsnetworking.com. It said troubleshooting couldn't identify the problem because I am able to connect to that, so there's nothing wrong. But I'm going to close that. And if we go down a bit, at a network adapter level, you could also have problems that may prevent you from connecting to the network itself. So with that, you can also run your troubleshooter, and it's going to detect problems at a network level. I could choose all adapters, or if you specifically want to look at Wi-Fi or Ethernet, I'm just going to leave it on all. But it's going to go through and look for any problems, And it will actually, if a problem is detected, it will give you some recommendations. This recommendation could be as simple as restart your computer or what action you should take to solve this problem. So this actually tested my internet connection, made sure I'm able to access some websites. Microsoft.com is what it tests, and update.microsoft.com. And it found no issues. So then it says, are you having some other type of problem? Are you having a problem connecting to a specific website or folder on the network? So if one of those is your problem, you could simply select it there. So a pretty useful tool overall. What I mostly prefer this tool for is helping end users. If I am helping an end user, especially over the phone, I prefer not to have to explain to an end user how to pull up command prompt and type ping space a website name or IP address or something like that, because that's not their job. That's not what they do. That's not what they want to do. So it's much easier to say, I need you to go to these troubleshooters, and I just want you to click on under internet connection, run the troubleshooter, and just tell me what it says, and go from there. So very useful from the end user's point of view. Sometimes you need to capture traffic on the network. Now, this is often called sniffing. A very common phrase you'll hear is, I'm going to sniff the network, or I need to download a sniffer. Wireshark is the most common sniffer that we would actually use. Wireshark is free. It's an open source network protocol analyzer tool. Now, we could call it a network protocol analyzer tool, but it's just easier to say it's a sniffer. This will allow you to capture and examine traffic passing through your network. Now, this will work on a wired network, and it also works on wireless, so no difference with the type of adapter that you actually have in your machine. Wireshark will allow you to inspect individual packets. You can view detailed information about each of these packets. That would include source, destination addresses. You can view the size of the packet, the type of data being transmitted. Now, the reason you may need to do this is because you are troubleshooting some type of network issue, you want to detect some type of security threat, or you're just trying to make sure your network is actually optimized for the best performance. So this gives you insight into that type of information. Wireshark also supports all the common protocols. So TCP/IP, IP version 4 and IP version 6, DNS, HTTP, HTTPS, TLS, all common types of traffic this can actually capture and let you examine. It also works on different platforms. So if you're using Windows, Mac OS, Linux, it's really based on the protocol. So any device you have, this could be an Android device, this could be an iPad, iPhone, any type of device. If it's passing TCP/IP traffic, that traffic can be captured. There is a bit of a learning curve to Wireshark, but overall the interface is somewhat intuitive. It just takes a while to understand how you can filter certain types of traffic and a while to determine the best way to search for a specific thing. But it does have filtering capability natively built in, because this does capture a massive amount of traffic. Then you can just filter out the traffic you don't want to see, just leave what you're actually looking for. Maybe that's based on IP address of a certain device, maybe it's based on a certain protocol. Overall, Wireshark is just a tool for network analysis. That is its entire purpose. Capture and analyze network traffic for various reasons. To look at Wireshark, you need to download it, and I already have it on this computer. So I'm going to go to Start, and I'm just going to click on Wireshark here. When Wireshark opens, you will get a list of all the interfaces on your system. Now, I have quite a few adapters. Some of these are virtual because I do run some virtualization software on this machine, but that's not really important. What's important is the interfaces with activity will display that activity. So right now I am connected to a wireless network, so I can see this Wi-Fi traffic here through this little line graph. So I know that's my adapter. I'm just going to double click that and it automatically starts a capture. Now let's let this run for just a few seconds and we can see how much traffic this thing actually captures. So that's been running for, I can see the time right here. So that's been running for about 16 seconds. So I'm going to go ahead and stop that. So this capture ran for 21 seconds. If I go back over here to the slide bar, you can see in 21 seconds, we captured quite a bit of traffic. The far left of the console here gives you the number. So we captured, well, just 70 packets we actually captured. So not a tremendous amount. But I am on a network right now that has maybe 3 or 4 computers running, some Amazon devices, and that's it. If this were on a corporate network with hundreds of computers, dozens of other types of devices, you would have received in that 20 seconds potentially thousands of packets. Just depends on the size of the network you're on. But even running this on a home network, you still rapidly gather a lot of information. Now, certain things you click on here will show you the source IP address. Now, I know this IP address, 192.168.1.196. I'm just going to run ipconfig, and I can see that that is the IP address on the computer I'm actually using right now. So that's my IP address. This is one of the devices on my network. Well, if I click on that, I get 4 items here at the bottom. Now, sometimes you'll see more than that. This frame, that is operating at the data link layer of that OSI model we discussed earlier. So with the frame, you can see some characteristics about the frame itself. Now, not extremely common that we really go through and look at frames. On the Ethernet 2, you'll see it has this source. Then it has this, which is my MAC address, actually. Whatever device you're connected to, it'll have like your destination MAC address show up here. But if I go back to the command prompt, well, notice before we do that this is FCF8AE. So when I go back, I'm going to run get MAC. And I can see my MAC address is FCF8AE. That is exactly what's showing up here. So that's related to the network adapter in the device itself. Then we have IP. So this will give me IP related information. So I can see the source IP address, destination IP address, information related to headers, time to live, checksums. And if we look at the last one, TCP, I can see information related to TCP. The machine I'm connected to right now, this line we're looking at for that packet, one of the things in that is destination port 3389. I am connected to a machine using a remote desktop right now. So here, I just have a remote machine I'm connected to. So it just so happens the line I clicked on is actually for that remote machine. I know that because the port for remote desktop is 3389. So you get information about that. Now, depending on what you click on will determine what you see. If I click on one of these that says TLS, you'll see it added a transport layer security. That's going to be related to encryption. So you will see different items when you click on these packets, just depends on the packet itself. Now, this is the type of tool that you really have to be looking for something specific. If you just come here and decide, I'm just going to browse around and see what I have, well, that itself really serves no purpose. Normally, you have to know what you're looking for so you can actually start to filter out certain things. So whether it's looking for some type of threat, malware, computers that may be generating an excessive amount of traffic, normally something like that you'd be looking for here. Now let's run a few experiments. What I'm going to do is start a new capture. So I'm going to click this little like shark icon, like the fin icon here. That starts a new capture. Whenever you start a new capture, it will always ask if you want to save the existing. So I could reload this if I were to save it, come back and just browse through it later, but I don't want to do that. So I will continue without saving. And my new capture is running. So now in my command prompt, I'm going to ping a few things. I'm going to ping test dev. That is one of the computers in my environment. And I'm also going to ping Microsoft. So Microsoft.com. Now notice TestDev did give me a reply. Microsoft does not give me a reply. Now, I know the Microsoft site is not down. They just don't respond to ping traffic, which is actually this ICMP, Internet Control Message Protocol. That's the protocol that ping uses. Ping itself is just a utility within that protocol. Well, I'm going to minimize my command prompt so we can see we are at 270 plus captures already. Well, I don't want to scroll through all of that traffic, looking for my ICMP ping information. So I'm going to stop the capture. But now I'm going to filter it. Well, the first thing I'm going to do, I'm just going to type DNS here in this filter, and I can filter based on DNS. So I'm just going to go over here and click this arrow. Now it only shows DNS traffic. Now, if we go back to the command prompt for one moment, when I pinged Microsoft.com, it did resolve Microsoft.com to this address, 20.53.203.50. And TestDev was also resolved to this address, 192.168.1.200. So we know name resolution worked because both names were resolved to IP addresses. Well, if we look at this from the point of view of Wireshark in our captured packets, I can see there was a standard query. It says testdev. Now, this is on my local network, so it automatically appended this fios-router.home. That's unimportant to us. But if I go back to the command prompt here, I'm going to run ipconfig. Notice it has this connection-specific DNS suffix, fios-router.home. What that means to me, any name you query that you do not include a domain name on it. Like for Microsoft.com, I actually type Microsoft.com. For TestDev, I type just the computer name. It automatically appends the fios-router.home because that is the connection-specific DNS suffix that's defined. And that's defined in your network adapter properties. Some devices, you may not have that defined at all, which that's fine. I only point that out so you know why it has that fios-router.home appended to it. But notice it says standard query for that. But then below, it says response. No such name for that testdev. That is interesting. Now, when we look at this, if I look at the source IP address, we ran ipconfig earlier, and we saw the source IP address on my computer ends in 196. So this is my IP address. The destination is 192.168.1.1. Now, this is a DNS query. So from my computer, I queried this 192.168.1.1 saying, do you know who testdev is? It actually replied back. So now this packet says the source is the 192.168.1.1, and it's sending it to my computer, and it replied back saying, no such name actually exists for that. We'll see exactly what that means. Now, the reason that still worked, no name existed, but then my computer just sent a broadcast saying, is there a testdev out here on the network? And it actually replied. So that's why it worked, not because it was resolved through DNS. Ultimately, it was resolved through broadcast. But if we look at the ones for Microsoft.com, I can see query Microsoft.com. Or if we look at this bottom one, query Microsoft.com. So my IP address up to the 192.168.1.1. Now, if you're wondering, why does the query go to 192.168.1.1? If I type ipconfig/all, notice that is the IP address of the DNS server. So anytime I try to resolve anything by name, my computer says, well, I don't know where that is. So I'm going to query the DNS server, and the DNS server is going to take that name, resolve it to an IP address, and it's going to just let me know. So that's the significance of the 192.168.1.1. But I can see I passed a query. This time, DNS was ultimately able to resolve the IP address, ultimately able to resolve that name to an IP address. So over here, I see a couple of IP addresses. There's the 20.53.203.50. There's another, and this A just stands for address. It's often called an A record, address record, sometimes a host A record, but each of those is an entry. So Microsoft.com resolves to multiple IP addresses. If I expand this down at the bottom, I can see DNS shows up here. So some things we can actually look at. Let me be sure I actually click on the one I want. So this is the one I want, the bottom one. When you click on it, it highlights. But what I can see under DNS is I can see the question. One question was asked, and it has answers RRs. RR stands for resource record, but there were 5 records returned. If I expand the queries, you can see I queried Microsoft.com. So that's what I asked the DNS server. Look up the name Microsoft.com and let me know what IP addresses it resolves to. When I expand answers, we can see 5 IP addresses were returned. So we know that Microsoft.com resolved to those 5 IP addresses. We knew it was going to be 5 because answer, resource record, 5. Now, if you are in a command prompt and you wanted to know that same thing, you could actually run the command nslookup Microsoft.com, and it'll give you those same addresses. You can see that one ending in 50 was one of the ones we saw. So it just returns that same information because that's just connecting to the internet as well. And that's just running a query directly through the internet. So some of the information we glean with Wireshark, you can use other tools to get some of that, but Wireshark is the most complete tool. Now, one more thing related to this DNS here. This one, it says no such name existed. Why? I know that's a computer on my network. Why would it say no such name? Now, I'm going to connect to the router on my network that is actually providing name resolution services. I'm going to go to advanced here. Yes on the warning, and it has a DNS server natively built in. So a DNS server can be a router, it can be a Windows server, a Unix server. There are many appliances you can buy that actually have DNS natively built in. But what I'm going to do, I'm going to add a DNS entry. Test dev was the name of that machine. And I'm going to enter its IP address, which was 192.168.1.200. And I'm going to apply. So now that shows up, test dev with that address. Well, what I'm going to do now, I'm going to start another query. I'm not going to save this one, so I'm going to continue without saving. And I'm going to ping test dev. So we received our replies, same as we did before. But now when I go back to Wireshark, the query, test dev files.router -router.home, same as before, but now the response says A for that A record. Test dev resolves to this IP address. Pretty fascinating. So we know that now worked. Where before it was saying no result found, solely because now the device that we're using as a DNS server actually has an entry that resolves that name to that address. I'm actually going to remove that because I have no need for it. And you'll see if I simply run that again. Go back to Wireshark. Now it's back to saying no such name actually exists. So pretty neat overall. Now we do spend a lot of time looking at DNS servers configured on a Windows server in one of the later modules in this course. So this is just an example of something you would see on a small office, home office network, or in your environment if you wanted to use Wireshark and examine some of these things. A smaller network, whatever you're using as a router or gateway likely has that same capability. Now I'm filtering this. So right now the list is not growing, because it's only filtering DNS traffic. If I clear the filter, because that query is still running, you can see in that time, we did gather, in excess of 200 packets. So I'm going to stop that capture. I'm going to start a new capture. And in this one, I'm going to ping Microsoft.com. No, we already did that once, but we're going to ping Microsoft.com again. Notice we get no reply. And that's going to go through 4 timeouts here. Now I'm going to ping RTS Networking. So rtsnetworking.com. And we get 4 quick replies. Well, I'm going to stop this filter again, or this capture rather. And now I'm going to type ICMP. So now I'm only filtering my ping traffic, the ICMP protocol. But a few things to look at here. Notice there are 4 requests. I won't really highlight all of those, but you'll see here. Request, 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 request. Well, look at the IP address they've resolved to. The destination is 20.53. That's the address for the Microsoft.com. So here I can tell Microsoft did not respond. Now we know that from the command prompt, but I can see my computer IP address 196. We sent out a ping request to .50 and it did not respond. And I sent another and another and another, and it just never responded to me. Then when I started pinging RTS networking, I know this 185 is one of the addresses for RTS networking. We sent a request. We then received a reply, and I can see the source for that reply is the remote side of this. Then I sent another request, another reply, another, and another. So you can just kind of observe that process at the packet level. So it's kind of neat overall, but does not tell us anything we did not already know. Now I'm going to show you something I find interesting. One of my remote machines here is a domain controller. So what I'm going to do is actually restart this domain controller. It's going to take a minute for that to restart. But what I'm going to do, I'm going to start a brand new capture, and I'm not going to filter anything. I'm not going to filter ICMP, but I can see a lot of traffic's being captured. Now, I just know the IP address of that domain controller. So what I'm going to do is filter this so it's only showing me traffic that has a source or destination address of the domain controller itself. So to do that, I'm going to type ip.addr equals 192.168.1.230. So ip.addr equal sign the IP address. Now notice you're seeing other addresses show up here because we didn't actually click it yet. So you either hit enter or click the arrow over here. Sometimes I don't know why, but hitting enter does not work for me. And I have to go click the little arrow here. Then that actually activates the filter itself. So it can be a little glitchy at times. But now every result here is going to be related to IP address ending in 230. Now, some of the things here, if we start scrolling down a little bit. Okay, I can see this machine is either powered back up or it's starting up. So if I just go back to that, yep, it's already back at the login screen. So that machine restarted that fast. But some of the things I can see. That machine is a domain controller in my environment. Its name is RTS-DC. But I can see here it's a server, it's a domain controller. It is the time source for my entire domain. So something like that on a network, a machine running Active Directory is your domain controller. And when it starts up, it simply advertises all of its services. Now, we don't really care that it's a domain controller or time source or anything like that, but many servers in your environment, even some types of appliances, they at startup will advertise the types of services they offer, and then they will periodically advertise those across the network again. So it just helps devices know who has what types of roles actually assigned, what services are available on the network level. So pretty neat overall. Everyone's been told that when you go to a website, before you ever input personal information, make sure the website is secure. Make sure there's like a lock icon on the page. Make sure the URL is HTTPS. We can see why that's so important. I'm going to start a new capture, and I'm going to pull up my browser. And in the browser, I'm going to go to HTTP techpanda.org. So an HTTP website. You'll see right here, it does say not secure. I'm going to just enter an email. I'm going to say kevin@home.com, and I'm going to enter a password and submit. So we'll say that's my login info. Seemed like it worked. Now, this site is made just for demo purposes, for this very reason. So those credentials are not valid credentials. You can use this just to run this type of sniffing test on the network with these packet capture tools. I'm going to stop this capture, and I'm going to filter solely based on HTTP. Now, there is a lot going on here. A lot of things show up here. But I specifically know this post is actually what I'm looking for, this HTTP post. When I expand HTML, that is the username, kevin@home.com, or email that I supplied. The password I typed in was my weak password. So that is revealed in clear text, because it's not an HTTPS website. If it was HTTPS, it is impossible you could ever discern what that actually is. So that just puts a visual to why that's so important. Do be aware that there is an HTTPS, techpanda.org as well. That is secure. So if you ever do run this on your own, just be sure that you type HTTP, because if you don't, it will just default to the secure HTTPS, and you just won't get the results. If you want to just look at those in your own environment on clear text, it's all going to be encrypted traffic. Pretty neat overall. In the following lessons, we will use the term domain, domain controller, and Active Directory. If you're not familiar with those concepts, I have a link under this lesson to a YouTube video, Understanding Active Directory and Group Policy. That will give you great insight to what Active Directory actually is. Now, you don't have to have a deep understanding of Active Directory to take this course itself, but these are very common services that everyone that works in IT should be aware of. So I do recommend you watch this video. You will hear some of those terms referenced: domain, domain controller, Active Directory, in some of the upcoming videos. So if this is a new technology for you, this will give you some insight into exactly what Active Directory is. So I do recommend you watch this. If not now, even after the course is over, you would still benefit from this. The YouTube link to this video is under this lesson. In Module 2, we will cover Dynamic Host Configuration Protocol, more commonly known as DHCP. I'll cover the overview of the DHCP server role. We'll look at how you deploy DHCP and the entire configuration, and we'll also cover how you manage and troubleshoot DHCP configuration issues. To get started with Lesson 1, I will cover the benefits of using DHCP, so we'll know why you would want to use that, whether you're on a small network or a large network. I'll show you how DHCP allocates IP addresses, how the lease generation process actually works, and what happens when you need to renew your address. So we'll cover the entire process, so you'll know how this works if you are on a home network using some type of appliance like a wireless access point or a router, or if you're on a corporate network using an enterprise level product, the process is still the same. Let's take a look at how DHCP actually works. Any network you go to, even your home network, you're going to have clients that are capable of using DHCP. So here I have a phone. Now you probably don't have an IP-based phone at home, but some of you may. You typically would have these in your offices. A phone that has to have an IP address to communicate. Printers. You're going to have your different types of computers. So I could have a Linux, Mac OS, Windows. I'm going to have desktops, laptops possibly. I'm going to have mobile devices, whether that's an iOS device, if that's an Android device, does not matter. All of these devices are capable of obtaining IP addresses from DHCP. So let's look at DHCP. When I go to DHCP, you could have different types of devices supplying IP addresses. Many switches, Cisco switches, other manufacturers, even some Linksys, D-Link, the types of devices you would use on a small office or home office network, many of those have DHCP natively built in. So this is not just a Windows technology. Many routers also have the capability to run DHCP. And you can use servers. Now, typically when you talk about servers, we're going to reference a Windows server, but Linux could do this as well. The way DHCP gets configured is basically the same on any of these devices that you actually use. I will define an IP range start and end address, meaning DHCP will issue 192.168.1.11 in the example I have here. And that's just a random number that I picked, the 192.168.1.11. And I have it end at 192.168.1.254. So the first device over here that gets assigned an address would have that address that ends in .11. The next one would be .12, .13, and so on, capable of leasing IP addresses up through ending in 254. I can also define the default gateway that I want to have assigned, and I can define my DNS servers. So now, any of these devices that request an IP address from DHCP, they will get assigned this IP configuration. The benefit to this is I now have a single point of administration. I configure DHCP on my router, switch, server, does not matter which one you choose, configured on that device, and now my clients just need to be set to obtain an IP address automatically. That is the default for most clients. Windows operating systems default to obtain an IP address automatically. Your mobile devices, your phones, even your printers, all default to obtain an IP address automatically. So if I were to get a new printer, a new computer, a new phone, all I have to do is connect to the network, whether that's Ethernet or if that's wireless, just connect to the network and your device will automatically obtain an IP address from whatever DHCP you have configured on the back end. So that's how DHCP works. Now we want to take a deeper look at some of the configurations and some of the advantages, some of the things you may be concerned with when you deploy DHCP in the environment. There are several benefits to using DHCP. Two of the most common would be reducing complexity and reducing administrative work. When I assign IP addresses using DHCP, we'll just call that an automatic IP configuration, compared to manually assigning IP addresses, which we will call static. That's the term you normally hear for a manual IP configuration, will be a static IP address. Well, let's look at the manual side first here with these static addresses. This would require me to manually type the IP address in each individual device. Now imagine if you have 1,000 computers in your environment. You would have to type the IP address in all 1,000 devices. You then have to document which device has which IP address. If you get a new computer, you have to then go to your documentation to see what address is available, what address should you use next. If you re-image a computer, you have to go look up the IP configuration that should be used on that computer. Just an increase in administrative work. If you make a mistake, type an incorrect IP address, which inevitably that will happen, then you have some type of disruption. And any type of mistake will result in some type of communication or network issue. And it's also not mobile. Imagine you have a laptop and you use a static IP address on your laptop. That's when you're in the office. But your user takes that laptop home. They travel. Sometimes they work from coffee shops. The IP configuration would have to be redefined on that device for each of those locations because each location is going to use a different IP configuration. So not a solution for mobile users. If we look at the DHCP side, supplies IP addresses automatically, ensures the correct configuration information. I configure my DHCP, and once that configuration is done, we'll verify it is correct. Then I no longer have a concern about clients being misconfigured. Any change that I need to make to my IP configurations, maybe I need to change the addresses I lease or some other configuration, you make that change in DHCP and your clients automatically process that change. And DHCP also eliminates a common source of network problems, which would be administrative mistakes, typing in the wrong numbers and all those things that could happen when you use static IP addresses. So those would be our benefits of the DHCP side when we compare this to using static or manual IP addresses on the other side. Now, with this said, clients will typically use automatically assigned IP addresses from DHCP. Most servers will always use static IP addresses. Now, that makes sense for a few reasons. One is because servers are typically in a rack. They do not move. So I'm not concerned about mobility or anything like that at a server level. And there are some services you run on a server that require static IP addresses. For example, domain controllers running Active Directory, they require static IP addresses. DNS servers will always have static IP addresses. Something like a file server or web server could have a dynamically assigned IP address. But typically in our environments, we will also give those static IP addresses. Let's talk about how DHCP actually leases IP addresses and how to make DHCP resilient. One of the concerns with DHCP, if you have just one DHCP server in your environment and it's leasing addresses to all of your clients, the concern is if that server fails, then none of your clients get leased IP addresses and you have an outage on your network. Simple solution, you could simply have more than one DHCP server. Now, this is something we look at in a little more detail because if you're going to deploy multiple DHCP servers, there are a few different options you have as to how you actually do that with split scopes and failover clustering. We do look at that part in the next lesson and configure both of those options. But for this graphic, how the lease generation process works, let's say I have two DHCP servers. The DHCP server 1, I'm just going to say I lease addresses here. 192.168.1.11 through 192.168.1.150. DHCP server 2, I just lease a different range of addresses. 192.168.1.151 through 192.168.1.254. Now, we don't really care about the range of addresses. All we care about is that the range of addresses is different. It does not matter which DHCP server you actually lease an IP address from. It's going to have you on the same IP network, so you're going to have full connectivity. So I truly may not have a preference if you get an address from DHCP server 1 or DHCP server 2. Well, with this, the actual process, my client here is set to obtain an IP automatically. I'm just going to say obtain an IP automatically. So that's how the client's set. It's going to try to get an address from DHCP. My client will send a DHCP broadcast message, which is called a discover message. Now, technically it is named DHCP discover, but normally you'll just hear people say discover. This is a broadcast that's sent to every device on the network saying, are there any DHCP servers here? If so, I need an IP address. Every device hears that. Both of my DHCP servers will send back an offer. Now, that offer does contain an IP address. So effectively the server saying, hey client, I see you asked for an IP address. Here's an IP address. Let me know if you would like to use it. Now, in this graphic though, both DHCP servers actually sent back an offer because here DHCP server 1 has no idea that there's another DHCP server on the network. That's not how it works. It just says, I hear someone sending a discover for an address, I'm going to offer an address. So both of my DHCP servers send an offer to my client. Now, one of these has to be received first. It could be a millisecond ahead of the other. But in this example, let's say the offer from DHCP server 1 was received just ahead of the offer from DHCP server 2. So my client is actually going to use the one from DHCP server 1. So what my client will do is send back a DHCP request, which we just call a request, that says, hey, server 1, you offered me this IP address. I would like to go ahead and actually use the address. Server 1 is going to hear that, and server 1 is going to send you back a DHCP acknowledgement. Normally it's just called an ACK, that ACK. This says, okay, these are the details of your address lease. This is the IP address. You have this leased for a certain amount of time. Here you go. So at this point, my client is actually done at this point. Now, this process we call DORA. Discover, offer, request, acknowledge. So DORA. This process is identical if you were using a router, a switch, a Windows server, or some other appliance. It's going to go through the same exact process and even send the same type of packets: the discover, offer, request, acknowledge. So at this point, we are done. My client now has an IP address. We'll say 192.168.1.11 is the IP on my client. It can communicate. But there's one other thing we're concerned with. We did have an offer from DHCP server 2. Well, we don't want to just leave it waiting. It sent an offer. We want to let it know that we no longer need that address. So what my client will do, once it finishes this process here, the DORA process, it actually sends back a DHCP decline. That decline basically says, DHCP, you offered me an IP address, but I don't need it anymore. I've taken one from someone else, so I decline the offer you sent me. The DHCP server will then send back a negative acknowledgement. Basically just finalizes the conversation and says, okay, I offered you an IP address, you declined it. I'm just letting you know that offer is no longer valid. I'm going to just give that address to the next client that obtains an IP address automatically. You would be done with that process. You may have noticed on your home computer that you may have the same IP address for months, possibly years on your home computer. You may notice the same with your work computer. It may always have the same IP address, but that address may be assigned from DHCP. That's a configuration. This goes back to how DHCP works. When you configure DHCP, if you're using a Windows server, by default, you have an 8-day lease duration. So anytime you lease an address, that address is leased to you for 8 days. Now, if you think about that, if I have a desktop that's always on my network, there is no point to give this desktop a different IP address every 8 days. I mean, if you have a valid IP address that works on your device, why would I ever want to change that address? Instead, it makes more sense to just keep renewing the address you already have. That's where this comes into play. I have my DHCP server. I have already been leased an address. So my client here, I'm going to say 192.168.1.11. That's the address my client has been leased, and we're going to say it's an 8-day lease with a default duration. Well, now, when my client is at 50% of that duration, so in this case, 4 days, it will actually go back to DHCP and it will attempt to renew the address that it already has. That is a DHCP request, which we just call a request. Says, I already have this address assigned, you leased it to me, but it's 50% exhausted and I want to renew it. DHCP will send you back an acknowledgement and your address is now renewed for another 8 days. So in reality, it pushes out 4 days. You have an 8-day lease duration. You get to day 4, it gets renewed, so it's now pushed out another 8 days. So in theory, If your DHCP server is always online and your client is always online, your lease duration will never be less than 4 days, because at that 4-day mark, it would simply renew and it'll just keep doing that indefinitely. Now, let's say there's some type of issue. Maybe when you go to renew, there's a network issue, the DHCP server's offline, for whatever reason, that process fails. If that were to happen, you fail at 50%, your renewal process will begin again at 87.5%. Now, that's an odd number. Well, truly, that's an odd number, and it's kind of weird that it's not like 75%. You don't see many things that'll be 87.5. If you were to do the math, if you made this a fraction, it would be 7/8. So just going back to that 8-day lease duration, you would attempt to renew at day 4. You would attempt to renew again at day 7, is where this 87.5% comes in. Now, there is no point for you to even try to remember this 7/8. That's just a fact that I find interesting. The renewal interval is not adjustable. It is 50% and 87.5. So they just are what they are, not something that you could ever modify or anything like that. If it fails at 87.5, so that would mean if we're using our default lease duration, this failed at day 4, and now it fails again at day 7. Hard to imagine the same problem has existed across that number of days. But if it did fail for some reason at the 87.5 as well, then you will actually have your address expire. It's going to go up to 100% and it automatically expires. But the moment it expires, you start broadcasting that DHCP discover, so you start looking for another DHCP server in the environment to lease you an IP address. Something I've done many times is replace DHCP servers, and this is an easy way to do it. Let's say DHCP server 1. Now, we're not concerned about redundancy or fault tolerance or anything in this example here, but let's say you have just one DHCP server. It's configured and you have it already assigning addresses and you've long had it. But now you want to replace that server. You go get another DHCP server. But then the question comes up, how do you switch from one to the other? Well, what you could actually do is fully configure DHCP server 2, have it start leasing IP addresses, and you could go to DHCP server 1 and you could simply deactivate, is the term we'll use. Deactivate the scope on DHCP server 1 so it no longer leases addresses. Any new addresses would be leased from DHCP server 2, but you do not disrupt your clients, because if they already have an IP address, they're going to try to renew at 50%. It's going to fail. It's going to fail again at 87.5. Then when it completely fails at the 100%, it sends the discover and they now get an address from DHCP server 2. When that's done, you can just get rid of DHCP server 1 altogether, repurpose it or remove it from the environment. So pretty easy to switch over. Now, one other interesting thing that DHCP does, it has a setting built in called conflict detection. So let's say here, DHCP server 1 is leasing addresses. Now, I won't bore you by writing out all the addresses, but we'll say it's 192.168.1.11 through 192.168.1.254. So that last octet, last number, 11 through 254. Well, when I deactivate this, I could actually go here and I could set the same range of addresses. So DHCP server 2 is handing out the exact same addresses as the DHCP server 1. The question that always brings up, well, how does that not cause a conflict? If my client here has already been leased this address ending in 11, and then you build a brand new DHCP server that leases the same addresses, it's going to try to lease the .11 address. Well, when we enable conflict detection, what happens? Before this DHCP server ever leases an address, it'll actually do a quick ping across the network just to make sure no one responds to that message. Sends a little, it's ICMP traffic. It's like the ping protocol. But it'll verify that no one responds to that address. No response, it then leases that address, and you have no issues. Now, that conflict detection does slightly delay the process of leasing addresses, but negligible. Not something you would notice on your network. And if you did have concerns even about that slight delay, once you have completely removed DHCP server 1, you could simply go disable conflict detection if you really don't want it on or you don't believe you need it at that point. Pretty fascinating how the process works. And again, this process is the exact same if I'm using a Linksys router at my home, if I'm using a Cisco router to assign DHCP in the enterprise, or an access point to assign DHCP. They all work the same. They all use the same percentages. So none of this is Microsoft specific, just industry standard. Pretty fascinating. One concern with DHCP is what happens if you are set to obtain an IP address automatically from your computer and it simply does not work. There's some type of issue that prevents you from communicating with DHCP. Well, what happens is pretty interesting. Automatic private IP addressing, which is just called a PIPA. This is a process that will automatically assign an IP address to your local computer when the DHCP is unavailable. This is a setting on the device itself. So your Windows 10 computer, even mobile devices have this. So non-Microsoft devices, Microsoft devices, if they're set to obtain an IP address automatically and that fails for some reason, no DHCP server ever responds, then your client will automatically generate an address that is 169.254. That's going to be the first two numbers, the first two octets of the IP address. The last two numbers will be unique to your device itself. This is controlled, if you're on a Windows PC, by a setting in the registry that will automatically generate this 169.254 address. Now, all is not lost. Let's think about a scenario where maybe my DHCP server was backed up over the weekend and somehow it was shut down and no one realized this. So I have users that now show up Monday morning and they power on their computers and their computers do not get a valid IP address assigned. Instead, they get these 169.254 addresses. Well, that's not really a big problem. What happens, your computer will send a DHCP discover, which is that broadcast message, every 5 minutes. So I could simply power on my DHCP server or device, and I know within 5 minutes, all my clients would have automatically sent that DHCP discover broadcast. They would now have obtained a valid IP address, and that's going to be configured on their computer. So now they would have network connectivity without any issues. A common question I get is, well, what's the point of giving you an IP address if it does not connect you to your network? Well, the reason, long ago, many, many decades ago, let's say you wanted to build a very small network. You could have a switch. Back then, it would actually have been a hub. But what I could do, I could know nothing about IP addresses. I could simply get 4 computers or 2 or more, how many ever you need to connect, and you could simply connect them to the same network. You don't have to assign IP addresses. Each one of these computers is going to get an IP address on that 169.254 network, and they would be able to communicate with each other. Now, you would never have internet access or access to other networks, but the computers would be able to communicate with each other. That was the original thought behind having the 169.254 automatically assigned. Realistically, in today's world, networks are so complex that almost every network you go to, you will have internet access. If you are even on a restricted network where you may not connect to the internet, you likely connect to other subnets or other networks within the environment. So today, the 169.254, it's more for troubleshooting purposes. If I'm on my computer and I type ipconfig and I see that address, I just know I didn't get an IP address from DHCP, and we can start to figure out why that may be. On this computer, I'm going to go to Start, Control Panel, my Network and Internet, and I'm going to open the Network and Sharing Center, and I'm going to click on this Change Adapter Settings. Then when I go to Ethernet and Properties, I'm going to go to the TCP IPv4. So I'm looking at my IP version 4 settings. You can see this computer is set to obtain an IP address automatically. I'll just close those windows there. Now I'm going to go to the command prompt. So I'm just going to go to start and type CMD. And in the command prompt, I will type ipconfig. Notice the auto configuration IPv4 address is 169.254. We know that's an APIPA address, so we know exactly what that means. This computer is set to obtain an IP address automatically, but there is no DHCP server available, or if there is a DHCP server on your network, perhaps it's offline. But either way, no DHCP server responded, and you did not obtain an IP address. So that's how we know that a APIPA is actually been assigned, just looking at the IP address in ipconfig. Or if you prefer to do this in PowerShell, in the command prompt, I'm going to type PowerShell. Now, even though this is still in the command prompt itself, notice that it says Windows PowerShell, and this now says PS, where before it was saying like C user/administrator. So I am in PowerShell right now. I'm just going to type get-net IP address. And we also know it's PowerShell because if we scroll back up a bit, it is yellow. Nothing in the command prompt itself is yellow by default. We can scroll down through all of this information, just a lot more output. But there you'll see the IP address again, 169.254, so we know it is in fact a APIPA. Lesson 2 is deploying DHCP. I'll cover installing and configuring the DHCP server role, this concept known as DHCP server authorization, allocating and managing IPv4 addresses using DHCP, configuring some additional options, and this concept of a DHCP relay agent. Very interesting topics. To configure DHCP, I can use Server Manager. That's the graphical tool. I can just add roles and features, walk through that wizard, and I can add the DHCP service. The other option is to use Windows PowerShell. If I want to use PowerShell, I will run the commandlet install-windows feature DHCP. Some other requirements. The server that is your DHCP server requires a static IP address. I mean, it cannot assign itself an address, nor can it be assigned an address from another server and still lease addresses. So if it does not have a static address, you can install the service, but it would never actually lease an address to any devices. Post-install, a few things we have to do. We need to create some security groups. There is a DHCP users and a DHCP admins group. DHCP users have read-only access. DHCP admins have full control over the DHCP service. So those need to be created. We need to restart the DHCP server service. That's just so it can start leasing IP addresses. And I need to authorize this server in Active Directory Domain Services if I am in a domain environment. Now, we expand on this in just a moment. But these other options, creating the group, restarting the service, we have an automatic way to do that we'll see in the interface. So they are post-installation tasks, but they're not things I have to manually figure out how to do on my own. It's incorporated into the actual process itself. Before you install DHCP, it is imperative that your server has a static IP address. That is a requirement for a DHCP server, so be sure that's done. But as long as you have a static IP address set, we can go to Start, Server Manager. I'll say don't show this again for this little pop-up message here. If I go to Manage, there is an option to add roles and features. In the Add Roles and Features, I'm going to go Next. A few times we'll go Next. Then DHCP Server shows up in the list. I'll select that, and we'll accept all these features by selecting Add Features. And we will accept the defaults for everything else. And we will install. The install is done, but do notice there is an option here to complete DHCP configuration. We will talk about exactly what that means in just a moment, but for now, I'm just going to close this window here. So DHCP has been installed. If I go to Tools, DHCP is in the list, and we can see it is present. So installation is complete. Now there are a few post-installation tasks that we want to talk about, then we'll look at those in the interface as well. One of the concerns we have with the DHCP is something called a rogue DHCP server. If you think about the easiest way to launch a denial of service attack, this would be near the top of the list. I could configure a DHCP server with invalid IP addresses. If your network is a 192.168.1 network, that's your IP configuration. I could create a DHCP server that leases completely different addresses connected to your network, thinking your clients will lease addresses from me. Some will lease addresses from me, some will lease addresses from you. But the clients that lease addresses from me, they won't be able to connect to the internet, to the network. Essentially, they will be offline for all purposes. So Microsoft added a way to give us a little bit of control over that, this concept of DHCP authorization. What this does is registers the DHCP server service in Active Directory. Only if your DHCP server is registered in Active Directory can it lease addresses. So the way this works for us, DHCP server 1, every time it actually restarts, it's going to automatically query Active Directory and say, hey, I'm DHCP server 1. Am I on the list of authorized DHCP servers? If Active Directory says, well, yes, you're on the list, DHCP server 1 will change its status to authorized and it will start servicing requests completely online. But let's say you have DHCP server 2. DHCP server 2, when it starts up, contacts Active Directory and says, I'm DHCP server 2. Am I authorized? Yes or no? If Active Directory responds in the negative and says, nope, you are not on our list of authorized servers, this server will remain in an unauthorized state and it's not possible for it to lease IP addresses. So with this, only an authorized server will lease addresses. So this would stop the concern about rogue DHCP servers in the environment. Now, two things to think about here. This only applies to Windows servers. There is no authorization for a router or a switch that's providing the DHCP server service, so unique to Windows servers. And the other concern, if you are in an environment that does not have an Active Directory domain, maybe on your home network, you are just playing around with DHCP and you decide, I want to use DHCP on a Windows server on my home network. If you have not created a domain in your environment, then you do not have authorization. A server in a workgroup does not use authorization, only once it's joined to an Active Directory domain. When I look at my DHCP server, notice IPv4 and IPv6 both have these red down arrows. It's kind of hard to see, but you can tell it's a red icon. Just a white circle with a red down arrow. That means the server itself is not authorized. Now, we have a few options. One, I could simply right-click the server and I could choose Authorize. That would authorize the server and we would be done. But if we go back to Server Manager, when DHCP, the installation had completed, it did give us this option to complete the DHCP configuration, these post-installation tasks. Well, if you had clicked on that, or you come back at any point and click on it, because it'll have this triangle on it, this notification. When I come back, it says it's going to do two things for me. One is it's going to create two security groups on the server. DHCP administrators. This group will have full control over DHCP, so they can manage all the settings in DHCP. Then there is also going to be a DHCP users group created. The DHCP users will have read-only access. And it will also authorize the server as long as the server is joined to a domain, which typically that would always be the case. So I will just click Next at the bottom. Then it says, what credentials do you want to use for authorization? I'm just using my administrator credentials, and we will click Commit. That's done. Now, if I go back to DHCP, we had these two red arrows here, denoting it was not authorized. If you refresh, Now we have this green circle with white check, so we know it's authorized. And at any point, if for some reason you wanted to unauthorize, you could unauthorize and reauthorize. But unlikely you ever do that, but it is possible. When you want to assign IPv4 addresses, the first thing we have to do is create a scope. This scope that we create will define all the information about the IP configuration settings that I want to assign the clients. Now, the key components of this scope will be the range of IP addresses, a subnet mask, a lease duration. Well, we mentioned that earlier. The default lease duration is 8 days. A scope may contain default gateway address. That's required if you want to connect to a network. That's required if you want to connect to the internet or to a different network. May contain a DNS server and suffix. This would be your DNS server addresses. That would be defined almost always. And there are quite a few other options that you could define as well under the scope options. You can also reserve a specific address. Let's say I have a printer in my environment, and I want the printer to obtain an IP address automatically. I don't want to use a static address on it. Now that makes sense because printers do get moved around quite a bit. If I set a static address on my printer, then anytime that printer gets moved to another network, you'd have to go through the menu on the printer and change the IP address. I don't want to do that. But I want the printer to always have the same address. What we can do is create a reservation. To do that, I simply need the MAC address of that printer. Now, this could be any client. I'm using a printer for an example. This could be a smartphone, a Mac, a Windows PC, does not matter. Any device that DHCP can lease an address to could have a reservation created. But what happens is I simply take the MAC address and I will reserve an IP address by typing in the IP address I want to reserve and the MAC address of the device that I want that reservation to be for. So now, anytime the device with that MAC address sends a DHCP discover, DHCP will always assign that specific IP address that I defined. So I know my printer always has this address no matter what. Now I am back on the first DHCP server that I set up. I'm going to go to Tools, DHCP. I'm going to adjust the view a bit, so we'll just change a few things here. But when I click on my server, it is authorized. We've done all that before, so I see the green circles with the white check. I'm going to go to IPv4, and I'm going to right-click IPv4, and I'm going to choose a new scope. So we get this new scope wizard. The first question is, what do you want to name the scope? Doesn't really matter what you name it, but something that identifies the actual purpose itself. I'm going to name mine NYC-BLDG1-FL. So New York City-Building 1-Floor 2. We'll say that's what this is intended for, so anyone that looks at it, they just have some idea of its overall purpose. And you could also put detailed information in the description if you choose to. Now, when we go next, it says, what are the IP addresses that you actually intend to lease? Start range. I'm going to say 192.168.1.51 is going to be the first IP address I lease. For the end range, I'm going to say 192.168.1.200. Subnet mask, it just defaulted to that subnet mask based on this 192 being a Class C address. But if you have a custom subnet mask in your environment, you just change that here. So at this moment, we have the name of the scope and the range of addresses that I intend to lease from this DHCP server. If you want to exclude any of those addresses, maybe you have some device in your environment and the powers that be tell you this device must have an IP address of 192.168.1.100. That is in the middle of your scope. So what I can do is simply say, I want to exclude this address from ever being leased from my DHCP server itself. That would be an option. Now, you could specify just one address. If it's going to be a range of addresses, you just enter the end address and it would exclude that entire range. But I'm going to put just the one. And I'll add, so you'll see now the address ending in 100 is excluded. never will be assigned from my DHCP server. Now, there is also a delay. So if I wanted this scope to wait a certain amount of milliseconds before it leased an address, then you could simply build in a delay. One of the things we mentioned earlier was having 2 DHCP servers in your environment for fault tolerance, and you want one server to primarily lease addresses, and you want the other to function more as a backup. This was a way to achieve that. You could go to the one that you wanted to function more like a backup type server, and you could simply say, I want you to have a certain delay in milliseconds before you would lease an IP address. So your clients would typically lease all their addresses from the DHCP server scope that does not have a delay, but completely optional. We'll go next. Now, how long should you have an address lease for? There is no right or wrong answer, depends on your environment. 8 days is the default. Some environments, like if you go to a coffee shop or restaurant or something like that, and you get on their Wi-Fi, they may lease you an address for 1 hour because they assume that you are there for a very short duration. Other environments you may go to and you may see an IP address is leased for 30 days. So it just depends, but 8 days is always the default. We could be done. This is asking me if I want to configure some advanced options. But if you think about what we've configured thus far, the only thing I've done is give this scope a name, define the range of IP addresses, any exclusions or delay, and that's pretty much it. And the lease duration, we should say. But that's it. Right now, I don't have DNS servers defined, so you would not be able to surf the internet. I don't have a default gateway, so you would not be able to connect to the internet as well, or even connect to a remote network. So almost always, you're going to say, yes, I want to configure these options now. Now, if you say no, you can come back at any time and do this. But any network you go to, they're going to have these options defined. So this router is asking for your default gateway address. I'm going to say 192.168.1.1. That's going to be my default gateway. For your DNS server, now because this is in an Active Directory domain, it is already aware of your domain name and who the DNS servers are in the domain. So this is already populated. Now, this is my DNS server in my environment, but if I have multiple DNS servers, I'm going to add 192.168.1.240. When I hit add, it's going to think for a moment and then come back and tell me that's not a valid DNS address because that's not a DNS server in my environment, but we can still see how it would actually work. So that's the message saying that IP address ending in 240 is not a valid DNS. Are you sure you want to add it? I'm going to say yes here just for our demonstration, but notice 230 is on the top, 240 is on the bottom. That means if this were to lease you an IP address, your primary DNS would be 230, your alternate DNS would be 240. Now you can jockey these up and down. So I'm going to click down. Notice 240 is now at the top and 230 is at the bottom. That means 240 would now be your primary, 230 would be your alternate. So that's how we define the DNS servers themselves. This Win servers, we don't use Win servers anymore. That's a legacy technology, so that we always skip over. And the last question, do you want to activate this scope now? I'm going to say yes, activate it. And we are finished. So my scope is now active. But we'll refresh. Now, if I click on my scope, I can go to the address pool. I can see my start address ends in 51, end address ends in 200, and we excluded the address ending in 100. Right now, I have no address leases or anything like that. But to run a quick experiment, this is RTS DC. I'm going to minimize this, and I'm going to go to my other server. And on this server, I'm going to go to my network connections. And I'm going to set this server to obtain an IP address automatically. Right now it has a static address, but we'll say obtain automatically. And while that's running, in PowerShell, I'm just going to type ipconfig. Now you could type getNet IP address, but that just gives you more output. Well, you can see it already worked. I can see the IP version 4 address is ending in 51. If I run ipconfig/all, I can see the DHCP server is ending in 230. So I know I leased an address from that DHCP server. I can see both DNS servers, the 230 and the bogus 240 address we put in. So I know that worked. Now, if I minimize this and go back to my address leases on the DHCP server itself, I'm going to refresh that view. And now you'll see that shows up. So from the DHCP server point of view, I know that RTS-SVR was leased this address, the 192.168.1.51. So we know it completely worked. Pretty neat. Now on my other server, I will go back and set that static address. Now, if you do this on your own, you could be using whatever addresses you want. But my address here was this 231. And that's my DNS address. Now, if I were to run ipconfig/all again, now you'll see my address is the 231, not obtained from DHCP. In DHCP, we also have the ability to create a reservation. A reservation will just take an IP address and associate it with a specific MAC address. So maybe I have a printer in my environment. I'm going to say printer 01. And I want this printer to always have the IP address 192.168.1.101. I need to obtain the MAC address of that printer. But once I have the MAC address of that printer, I can simply enter the MAC address, and now that IP address ending in 101 would only be leased to the device with that MAC address. So my printer will now always have the same IP address when it's on the network. If you have a current lease for an address, you can actually right-click, and there's an option to add to reservation. So if you do that, it created a reservation for that IP address. If I go to the reservation and go to the properties, it pulled the MAC address of that device. So now, anytime the device with this MAC address leases an IP address, it's always going to be this address here, ending in 51. So that's the easiest way to create a reservation. Let it just obtain an IP address automatically from DHCP, then you can just right-click and convert it to a reservation. Now, the consideration there, when you do that, you don't actually choose what the IP address will be when you convert it. Whatever address it was assigned, it just gets converted to a reservation. If you have a specific IP address that you need to use, that's when you will manually go through and you'll create the reservation and type in the MAC address. So that's our reservation configurations. Even though we have been looking in Windows servers, all of this information is really universal. It's not Microsoft specific. Some of the terminology can differ slightly from one vendor to another. An example, I'm on my Files by Verizon page here. This is my router that was supplied to me by Verizon for my internet connection. If I go to Advanced, now it does not use the term DHCP here, but under Routing, it says IPv4 address distribution. Now it says DHCP leases. So I can see devices in my environment that have been leased IP addresses. But if I go to the bottom, there is Add Static Connection. It wants the name of the device, the IP version 4 address I want to assign the device, and the MAC address. Now, this is considered a static connection here. But in Windows Server, or if you're using Cisco, most devices will reference this as a reservation. But that's the way it actually works wherever you see it. IP address associated with a MAC address, and that's the IP address you will always be leased. To install DHCP using PowerShell, I'm going to go to Start, and on PowerShell, I'm going to right-click and go to More, and there's an option to Run as Administrator. So you do need to be running this as administrator to install. In the PowerShell console, I'm going to change my font here so that's a little easier for everyone to see. Let's try 24. That looks better. To install DHCP, the command itself is install dash Windows feature DHCP. I will add this dash include management tools. If you run this command and you do not add dash include management tools, then you can only manage DHCP through PowerShell. It won't install the graphical console that you'll see in your administrative tools. That says it's installed. Now, to show you what I mean, I'm going to go back to Server Manager and I'm going to refresh my Server Manager. Notice DHCP does show up over here. And it says we need to complete some required configurations. Well, if you click that, our post-deployment configuration. We did not add the security groups yet. We did not authorize the server. But if I go to Tools, you'll see that DHCP is in the list. If I had not added dash include management tools, it would never show up here for me to actually click on. Now, if we want to finish this configuration from the command line itself or from PowerShell, to add the security groups, I'm going to run netsh DHCP add dash security groups. That completed successfully, so I will have my local groups. Once I do that, I do need to restart the DHCP service. So I'm just going to run restart-service DHCP server, and that's going to quickly restart. So that does not restart the server that you're actually on, just the actual service for the DHCP server itself. Now, what that has done, if I go back to Server Manager here, I'm going to go to Tools and Computer Management. And in Computer Management, I'm going to click on Local Users and Groups, Groups. You'll see at the bottom, DHCP administrators, DHCP users. Those groups were not present prior to us running that netsh DHCP add security groups command. So we know that worked. Lastly, if I want to authorize the server, to do that, my command is add dash DHCP server NDC. Now PowerShell does give us tab completion, so I just hit tab and it completed that command for me. So add dash DHCP server NDC dash DNS name, the name of the server. Now, this server is named RTS-SVR. That's the name of the server I'm actually on, and it is a member of the rtsnetworking.com domain. So we're going to put that in. Add dash DHCP server NDC dash DNS name, name of the server that you want to authorize, and the IP address of the server. So dash IP address. The IP address of this server is 192.168.1.231. That's just a static IP address that I set. That seemed like it worked because I did not get an error message. But to verify, I can run get dash DHCP server NDC. Now, sometimes it takes a moment. So you may run this and it may not show up. But if you think you've done everything correct, then you just wait a few more moments. But now you can see I have two servers authorized. The one I did in the GUI, the RTSDC, where we just click through and set it up. Then we have the 231 RTS SVR. So both are now really at the same point. We just configured one through PowerShell, configured the other through the actual graphical tool. If I'm using a Windows server for DHCP, it does give me two high availability options. One of those is failover. With failover, I can have a server, my server A. I configure a scope with all of my IP configuration settings. That scope then replicates to a second DHCP server. These DHCP servers are in communication with each other. If one fails, the other will then start leasing IP addresses. This is so powerful that you can use this either in a load balance mode where both servers actually lease IP addresses, or you could have it in a hot standby mode where server A leases addresses, server B has a replica of the scope, but it does nothing, just listens. If server A goes offline, then it will start leasing IP addresses. So it does have some configuration options that we can define. The other option is a DHCP split scope. This option is much older than the DHCP failover. So failover now is most likely what you would opt to use, gives you some advantages. But with the split scope, all that happens, you have two servers, server A and server B. They are just configured to lease a different range of IP addresses. Server A leases 192.168.0.1 through 150. Server B leases addresses ending in 151 and above. So there's not a conflict because each server leases a different range of IP addresses. Both servers are online, both servers lease addresses, and the theory would normally be, I don't care which one you get an address from because it's going to put you on the same IP subnet. You can choose to build in a delay in your scope. So if I want server B to function more like a backup DHCP, there is no such thing as a backup DHCP server, not by name, but if that's the way you want it to function, more in a standby type mode, then I could simply build a delay on server B. So now, anytime a client requests an address, that broadcast, the DHCP discover, is going to be received by both server A and server B. Server A will immediately respond with an offer. Server B is going to wait until that delay expires, then it will respond. The theory would be server A would respond so rapidly that your clients would always lease an address from server A, lest it's offline. Then when server B sends its offer, your client would then take the address from server B. So you have one primary server that you're using and another that functions more like a backup so you don't have a single point of failure. And that delay that we define is going to be measured in milliseconds. You define how many milliseconds, but that's what it's measured in. To configure a split scope, I'm going to expand IPv4 under my DHCP. I'm going to click on my scope that I have. When I right click, there's an option for advanced split scope. Now, if you were doing this on your own, when you click on the scope itself, you have to left click, then right click. If you do not left click first, when you right click, this menu will be entirely grayed out. It's just a weird Microsoft thing. But when I go to advanced, split scope is an option. So I'm going to go next on the first screen, and it says, what is your additional server that you want to split the scope with? Well, I know my other server is named RTS-SVR. So I'm going to type that name and add server. And I can see it shows up here in this list, the RTS-SVR. So I'm going to select that and click OK. This window, for whatever reason, often says not responding, but then it does work. So that did work. That's my additional DHCP server. Now when I go next, it says, how do you want to split the scope? It defaults to this 80-20 percentage. So the server I'm on right now is the host server. So right now, this server will lease 80% of the addresses. The other 20% of addresses will be leased by the server I just added, the RTS-SVR. So you can see what it does. Here, it says the start address on the server I'm using right now, which is the host, will be 171 to 200. The other server will lease addresses 51 to 170. We can see how this works. It says, following is the exclusion IPv4 address ranges. So the host server I'm on right now will exclude addresses 171 to 200. It will not lease those addresses. So it's going to lease everything below 171. The server I'm adding will exclude addresses ending in 51 to 170. So it will never lease those addresses. So really it's going to lease 171 up to 200 would be its 20%. So there is never overlap with the addresses being leased. Now, if I move this slide bar, notice the exclusion address ranges actually change. So if I move this to 50/50, now the host server excludes addresses 126 to 200. So that just changes as you change your percentages. Now you can move the slide bar, or you could just do that here. Just type it in. But that's really all there is to it. I'm going to leave it on 50/50. So what's going to happen when I go next, it says, do you want to build a delay in milliseconds in either of these servers? We discussed that already. I don't want to build a delay. So I'll just click next, and that's it. I'm finished. It says everything was successful. I'm going to click my server and refresh. Now, when I click my scope, if I go to address pool, you'll see the addresses 51 to 200. But this is the additional exclusion. So excluded from leasing addresses 126 to 200. The other server will lease those addresses. Now, what's interesting, I could actually go to the other server. So I could minimize this and go to the other one. Or I could simply right-click DHCP and add server. And I'm going to choose RTS serve here in this list. I'm just going to add it to the same view here. So that worked. Now, eventually, it will convert this from the IP address to the name, but we know that is RTS SVR. If I expand IP version 4, that's my scope. Now, notice the scope is not activated. I will have to manually activate it. But when I click on the address pool, you'll see it has the same scope, 51 through 200. It's excluding 51 to 125. Compare that to our, to our exclusion here. And we were excluding 126 to 200. So you have the same exact scope on both. They just have different exclusions to make sure they never lease the same IP addresses. And by adding the other server to this console, I can now remotely administer all the DHCP settings on that, so I don't have to keep minimizing one VM and going to another. On the server that we added, I'm going to delete that scope. So I'll say yes to delete. So that scope has now been deleted. And on the address pool here, back on my host server that I'm on, the RTSDC, I'm going to delete that exclusion that was created when we did that split scope. So that's all there is to configuring a split scope on two DHCP servers. The entire configuration is done on one server, and it remotely creates everything on the other DHCP server. If you're using a Windows server, the DHCP database is stored in a file named dhcp.mdb. That file is stored under your system root system32 DHCP. So the default location is C Windows system32 DHCP. That's where you will find the database file itself. The DHCP database is automatically backed up every 60 minutes. You could also manually back it up at any time. If I know I'm about to make a change right now, you could manually just back it up, then make your change. In the unlikely event you needed to restore, you could simply restore from that previous backup. You can also reconcile the DHCP database to repair any inconsistencies. I can also move the DHCP database to a brand new server. You just copy the contents of this DHCP folder in System32. I could just copy that to my new server, and we have migrated to our new server. So very straightforward service to actually work with. To configure failover, I'm going to go back to my RTS DC. I'm going to expand IP version 4, and I'm going to go to my one scope that I created. When I right click that, there's an option to configure failover. This is the only scope I have, but this would give you a list of all the available scopes. So if you had more than one, they would all show up, and either you could select all, or you would individually select which scopes you wanted if you wanted to customize it. But I only have one scope, so that's fine. Who is your partner server? RTS SVR in my case. So I'll select that, add server. I'm going to select this authorized DHCP server and we'll select RTS-SVR. That'll take just a moment. So that is done. Now when I go next, it has this mode. Maybe the most important thing here. Do you want this to load balance? Meaning, do I want both servers to lease IP addresses? Or do you want to put this in hot standby and simply have it be a backup server? So if the primary active server fails, only then would this start leasing IP addresses. Strictly preference. But I'm going to put this in load balance. What percentage do you want to balance between the two? This defaults to 50-50, and I'm going to leave it on 50-50. But if you wanted 80-20, whatever percentage you want each server to actually manage, you can simply define that. If this does fail over for some reason or one server were to go offline, every 60 minutes it would check to see if the other server is back online. That server would then start leasing addresses as part of this failover relationship. Now, you could use message authentication. Now, that's not really important to us as far as leasing IP addresses, but that is used to determine how the servers communicate with each other. I could enter a shared secret, whatever you want that to be. Happy trees, I'll say. So type in whatever shared secret you want. The other server will require you to also type in that shared secret. If it's not defined, they don't communicate with each other. However, I'm not going to use a shared secret. We also have this maximum client lead time, or MCLT. Now, that's an interesting name that's not really descriptive as to what that setting does. But what it means, if I have leased an IP address to a client, and that client has an 8-day lease, then the client attempts to renew the address. Let's say it's at the 8-day expiration. For whatever reason, it has failed to renew. The maximum client lead time lets the client automatically extend that address, in this case for 1 hour. You can make that whatever you want. It could be 24 hours if I actually want it. So instead of having an address just expire automatically at the duration of that lease, if something's gone wrong on your network, it can automatically extend that a certain number of hours or minutes that you have actually defined. I'm going to choose next. And we are finished. That was successful. So I have my scope, my address pool. Now this is the server I just configured everything on. If I go to the other server and refresh IP version 4, it's going to think for a moment. The first time you open it always takes a little longer than all your subsequent times. I'll click on my scope here, and you'll see my address pool, and it's exactly the same. They lease addresses 51 through 200, and they both have a single exclusion, 100. So when you go to either of these, they look exactly the same. Now, that's interesting because it just makes you wonder, well, how does it really work? These two servers, when they are in a failover relationship, they have agreed with each other that if a MAC address is in this range to this range, you lease an IP address to it. I will lease MAC addresses from this range to this range. We have no idea, and we'll never know exactly what those ranges are. But depending on your percentage, if you have done 50-50, 80-20, they work this on their own through some type of algorithm on the back end to decide, I'm going to lease these devices' addresses, you lease these devices' addresses. If one of these servers goes offline, the other server will assume full responsibility for leasing all of the IP addresses. So this overall is a much better option than a typical split scope, and it's a newer option, although split scope, as we saw, is still a viable option. The backup in DHCP, if I want to do it manually, I can simply right click and back up. Now to look at this location, I'm just going to go to start, and on start, I'm just going to type C:\Windows/system32/DHCP. So that's going to open the DHCP folder. There are a lot of database files and temp logs and things like that here, but I'm going to open the backup. And that is the actual backup configuration. So this has automatically backed itself up. Now, as we said, you could manually force a backup. If not, it's going to back up every 60 minutes. But now, I could actually go back to my DHCP server if something has gone wrong, and I could restore. Tells me the DHCP service has to be stopped and restarted. Our message says the database was successfully restored, so it has its own backup capability natively built in. So that's pretty neat. Depending on the device you're on, like if you're on a lower end small office, home office router, may not have a backup built in. Something like that, you may be able to export the configuration, but they typically won't have backup capability built in. So only enterprise level devices, servers, Cisco routers, things like that would typically have this capability. One of the easiest migrations that you can perform is the DHCP server migration. You can migrate the DHCP server by simply exporting the data from the old server, then you can import it into the new server. That's it. Once I do that, your entire configuration resides on your new server. You can actually do this by copy and paste. You can copy the DHCP configuration file, like the database files, to your new server. On your new server, you can go to create a scope and choose to import that, and it's going to apply those same exact configuration settings to your new DHCP server. So this is a process that can take just a matter of minutes. Now, if I'm using a router, like a Cisco router, you can export that configuration as well and import it into a new router. So whatever solution you're using, most will have an option to export and import. The only place you typically don't see that would be for small office, home office devices like your Linksys and D-Link. They may not have an option for you to export the DHCP configuration. Just depends on the manufacturer of the device and often the model of the device itself, because that's more of an enterprise class feature that you need to migrate the database. Module 3 is understanding and implementing the domain name service, better known as DNS. The lessons we'll cover will be implementing the DNS server itself and understanding how the name resolution process works. I'll show you how to configure zones in DNS. We'll configure name resolution between different DNS zones and different DNS servers. I'll also cover configuring DNS integration with Active Directory domain services, and we'll look at some of the advanced settings that we can also define for DNS. Lesson 1 will be implementing DNS. So we're going to start off with looking at how the name resolution process works. We'll look at the components of an overall DNS solution. We'll look at the DNS zones and the different types of records that you can create. I will show you how to configure DNS clients. We will also look at the tools and techniques for troubleshooting any type of name resolution problem. We'll cover managing DNS servers and how do you test your DNS server to make sure it's actually functioning correctly. Pretty interesting topics. As we begin to dive into DNS, the first thing we want to look at is how DNS resolution actually works. And we want to touch on some of the components. As far as the name itself goes, there are 3 main components. We have a host name, a domain name, and we have a top-level domain. The host name is just the computer name itself. That computer name will have a domain name appended to it and a top-level domain. Those make up the fully qualified domain name, or FQDN. So in the example I have here, whoever set up this computer, they named it ACCT-DIR-PC. So we'll assume that's short for Account Director PC, we'll say. This computer has been joined to an Active Directory domain. That domain name is a datum. And the top-level domain name, which sometimes it's called an extension, is COM. So when Active Directory was set up here, this domain name was named a datum.com, is the actual domain name itself. Now your fully qualified domain name, or FQDN, is your computer name plus the entire domain name along with that top level domain extension. So accountdirpc.adatum.com is the fully qualified domain name. Now, if you are on a home network with your personal computer, then you are not a member of a domain. A computer like that would simply be a member of a work group. So there, you would only have the name of the computer itself, which normally everyone calls a computer name. So computer name or host name whichever you choose to call it, they are always used interchangeably. But in an environment like that, you have just the computer name. Once you join a domain, then you have the fully qualified domain name. But again, it's doing nothing more than appending the domain name to the back of the computer name itself. Now, we'll see why that's significant in the resolution process itself.
In this lesson, we're going to take a look at what happens when my user tries to browse the website www.rtsnetworking.com. From my user's computer, RTS Client 1, the first thing the computer does is check its local client cache. That client cache contains name to IP resolution for any websites or any servers that you have recently connected to. If you have not connected to the rtsnetworking.com website within the past few minutes, it's not going to be in cache. If it's not in cache, the second step is to check the local host file. The local host file is present on all machines. I can open the C drive, Windows, System32, drivers, and the etc folder. In that folder will be a host file. The host file is a static version of DNS. It has name to IP addresses typed directly in the file. Any entry in the host file, your computer will always resolve the name to that specific IP address. Host files used to be common long ago, in the days of Windows NT, Windows 2000. They're not extremely common now, but the host file is still a part of the resolution process. If the entry I'm looking for is not in the local cache, if it's not in the host file, the client computer knows it cannot resolve this name. The next thing the client will do is pass a recursive query to the local DNS server. The recursive query simply means the client asks the DNS server to resolve this name on its behalf by any means necessary. If that requires the DNS server to contact other DNS servers to resolve the name, that is what the client expects the DNS server to do. So the onus is completely placed on DNS to resolve this name. The DNS server itself, the first thing it will do is determine if the name you are connecting to is a local name or if it's a remote name. A local name means the name you're trying to resolve is a name that's in the domain that you're actually in. If my domain is named fabricam.com, if I'm trying to resolve a file server or a web server in my domain, then my local DNS server actually holds that record. If I am trying to resolve anything outside of fabricam.com, any website on the internet, for example, my DNS server does not hold those records, and it has to query other DNS servers to have that resolved. So in our example, this is a remote name. One of the concerns we always have with DNS is how many queries it receives and how much stress is placed on the DNS server itself. The fifth step in the process is for the DNS server to check its own local cache. The point of the DNS server cache is to offload the stress on the DNS server itself. For example, let's say my coworker went to rtsnetworking.com a few minutes ago. Now I go to rtsnetworking.com. The DNS server will simply check its cache to see if it has resolved this name for any other users on the network. If it has resolved that name and it still resides in cache, it will simply retrieve that from cache and send it back to the client computer. In the example here, we will assume we are the first person that's going to rtsnetworking.com, so it's not in our cache. Step 6 is an iterative query, often referred to as a simple query. This iterative or simple query will pass a request to the root of the internet. The root of the internet is always represented by a dot. That root is actually a collection of DNS servers that hold all the records for all the internet-based public top-level domains. The .com, net, org, all the domain extensions you see on the internet, they are all referenced from this root domain. So in practical terms, what that means, My DNS server queries the root and says, I'm trying to get to rtsnetworking.com. Can you tell me what IP address that resolves to? Well, the root says, no, I can't directly tell you that RTS networking resolves to a certain address, but what I can tell you is you should go query this other group of servers. They hold the .com namespace. Every publicly registered website in the world that ends in .com, they would have a record for that website. So my local DNS server receives that response. The local DNS server will then query the .com namespace, specifically looking for RTS networking. The .com name servers will have a public host A record for that. So those servers know that RTS networking has an IP address 23.236.62.147. That is sent back to the DNS server. Now my DNS server is aware of the IP address that rtsnetworking.com, that name, we now know what address it resolves to. Step 10, the DNS server will place that response in cache. So in the event a coworker attempts to browse that same site a few minutes from now, the DNS server does not have to reach back out to the internet, communicate with the root, and go through that same resolution process again. So it'll be temporarily stored in cache. Step 11, that resolved name to IP address is now passed back to the client. Now the client knows the IP address of rtsnetworking.com. Many of the things I just touched on in this graphic, we can actually interact with in the interface. So in the next lesson, we will look at the local client cache in step 1, and we'll see how we can manipulate that and how we can view the contents of it. I will also show you the host file and how we can add an entry into the host file and exactly how that process would actually work. On the DNS server, we will also examine the DNS server cache, and we will look at the root hints to see how they are defined on the DNS server itself. Now let's take a look at that lesson.
A DNS server is made up of a few different components. One of those is the DNS server itself. This could be a Windows server, it could be a Unix server, they will function the same. So I have my DNS server. Then we have a DNS zone. The easiest way to think of a DNS zone is to think of a folder. It even looks like a folder, but it's called a DNS zone. This zone contains all your resource records. So in the zone itself will be records. Now the records will map a name to an IP address is one example. That would be a host record, which just says your computer name is PC01, your IP address is 10.1.1.57. So those types of records will reside in the zone itself. And then lastly, we have DNS resolvers. A resolver is some type of client that your end user actually uses. This could be a PC, a mobile device, anything that queries DNS. So if I'm a user on this computer and I'm trying to browse a file server in my environment, when I type in the name of that file server, the name has to be resolved to an IP address. So that request gets passed to my DNS server. That makes my client the DNS resolver because it needs the name to be resolved from the DNS server itself. So those are the key components that we're going to look at in this module. What are DNS zones and what are DNS records? A DNS zone is a specific portion of the DNS namespace that contains various types of DNS records. Now, the zone itself is always going to be represented by a folder icon, and we'll see this when we look at DNS in the interface. But it's represented by a folder, and it's always like the name of your domain. If my domain is rtsnetworking.com, then in DNS, I'm going to have a folder, which is actually a zone, but this folder looking icon, and it's going to be named rtsnetworking.com. Every DNS record for rtsnetworking.com will reside in this. So I'm going to have all my different types of records show up here. Now these records, typically just think of a record as just resolving a name to an IP address. It's that mapping is an easy kind of generic way to think of a record. But all those records would reside in that zone. So if rtsnetworking.com, if that domain has 1,000 computers in it. All those computers will have records under that DNS zone. Now for the zones, we have forward lookup zones and we have reverse lookup zones. A forward lookup zone resolves a name to an IP address. Now, normally that is what you think of when you think of DNS. I know I want to connect to a certain website, Microsoft.com. I have no idea what the IP address of the Microsoft.com website is, but I know the name of the website. Well, with a forward lookup zone, you just type in the name, that query gets passed to DNS, and it resolves that name to an IP address and passes the IP address back to the device you're using. So normally when people talk about DNS, that's actually what they're talking about. We also have a reverse lookup. Now this is not as common. A reverse lookup takes an IP address that you know and resolves the IP to a name. Now the first thought was okay, why would I ever do that? If I know the IP address, most likely I probably already know the name, but why would I care? I could just connect to the IP address. That's true. You normally, as an end user, you don't care. But some applications will actually use a reverse lookup zone as a security check. Think of it like this. If I connect to a certain website, I'll say google.com. When that forward lookup gets past the DNS, it takes google.com, goes out, finds out what IP address it resolves to, then it sends it back to my device. A reverse lookup would then take that IP address that has been sent back to me, and it would actually query through a reverse lookup in DNS to say, does this IP address resolve to google.com? Almost like a final check, making sure you are who you say you are. Some of the benefits of the reverse lookup, it could reduce, if not eliminate, things like spoofing, where you connect to a name, but you get redirected to the wrong IP address because it's been spoofed or something like that. So it can add an extra layer of security, but just not normally what people think of when you talk about DNS. Now, the resource records that reside in the zone, there are several types that exist. Some of the most common are these A records, sometimes called a host A record. We also have an MX record, that's for email servers. We have these service locator records, or SRV. Every DNS server actually gets its own special type of record. It's called an NS record or name server. And we also have these canonical names, CNAME. Now, more often, you'll hear this now referred to as an alias. Just an alternate name that you want to go by. So truly an alias is more descriptive of a correct term. In the reverse lookup zone, we have these pointer records, which are called PTR. So there are many different types of records that exist within these zones. Now let's actually take a little deeper look at the record types themselves. The A record. Now this is often called a host record. Sometimes it's called a host A record, or you'll see host in parentheses, you'll see an A behind it. Interchangeable. So host, host A, or A record all mean the same thing. This is the most generic type of record you'll ever see. It is for an IP device, an IP version 4 device, I should say. It just resolves name to IP for an IP4 device. So every client on your network, every server, everything that registers in DNS that has an IP version 4 address, it's going to have that type of record show up. The CNAME, just an alias. Now, one example of this, let's say I have a web server named web01. Whatever your domain name is. Well, at that point, when users connect to my website, I don't want them to type in the IP address of my website in the browser. I don't want them to have to know the name of the server that hosts the website is web01. I want them to be able to type something like www.my domain name. If that's true, then I could simply go to DNS, and in DNS, I would create an alias www, and I would say this alias www actually is an alias for web01. So now no one ever has to know the name web01. Users just open the browser and they could type in www, and most websites now don't even require that you type that, and it'll just be resolved. But that's what an alias actually is. So truly, it's just an alias that eliminates the need for me to have to know individual server names from an end user's point of view when they want to connect to certain devices on your network. MX record stands for mail exchanger. This is always for an email server. That's its entire purpose in life, only for email servers. We also have these service locator records, or SRV. This is used to locate services in the domain where you do not know the IP address, nor do you know the name of the server that hosts. One way to think of this: I have my domain controller for my domain. I have a client. I want to log on first thing in the morning. I'm in the office and I'm trying to authenticate with my username and my password. I just want to authenticate so I can log on to my client PC. Well, to do that, my authentication request has to ultimately be passed to a domain controller. Well, what happens when I try to log on, I don't know the name of a domain controller. I know I'm trying to log on. Now, when I try to log on, the service that's actually used to authenticate is called Kerberos. When I try to log on, I'm trying to connect to this Kerberos service. So what happens is my client computer simply queries DNS saying, DNS, I'm trying to find out who hosts this Kerberos service. Do you know? DNS is going to have a record, a service record that says, oh, this Kerberos service is hosted on this server here, your domain controller. So what DNS will do is actually send you back the IP address of that domain controller, and ultimately, that's what you connect to anytime you authenticate. Now, we do look at that in a little more detail, how that process works, in one of the upcoming sections here, but that's the purpose of a service locator record. You know the type of service you want to connect to, you simply do not know the computer name or IP address of a server that hosts that service, so DNS will have records to help you locate. We also have these name server records. This is just a record for DNS servers. So all your DNS servers will have this type of record. It just denotes that it is in fact a DNS server. We don't really do anything with those. They just exist. We also have what's referred to as a quad A record. This record here, this quad A, is very similar to the host A record we talked about at the top of this slide. The only difference is this is name to IP, but it is specifically for IP version 6. So if you use IP version 6 on your network, the types of records that would be registered would be these quad A records, but that's the only difference. A is for IPv4, quad A, IPv6. The reverse lookup zone. Now, when I mentioned the reverse lookup zone on the previous slide, I did say that the purpose was to take an IP address that you know and resolve it to a name. That's a reverse lookup. This type of record in the reverse lookup is a pointer record, or PTR. So these are the common types of records that we'll see in the DNS server itself. To create some records in DNS, I'm going to go to Tools and Server Manager. DNS is in the list. In DNS, I'm going to expand this forward lookup zone, and I have a zone named rtsnetworking.com, the name of my domain. Now, this was automatically created when I installed Active Directory. So none of this that I manually set up or create or anything like that. It's just automatically done for you. What I'm going to do, I'm just going to right click in here and I'm going to make a new host A record. I'm going to name it PC1. It automatically appends my domain name, rtsnetworking.com, to the back. And I'm going to set the address as 192.168.1.232. I'll just click Add Host. Now I'm going to go to the command prompt and I'm going to type ping pc1.rtsnetworking.com. We can see that completely worked. Well, it failed, but it worked for what we wanted. I can see that PC1 resolved to the IP address ending in 192.168.1.232. I just have no device with that address on it right now, so I'm not actually getting a reply from that device. It just says host unreachable. But we know it completely resolved that name to that IP address. Now I'm going to create an alias. One of my servers has an IP address of 231 RTS SVR. So what I'm going to do, I'm going to create a new alias, and I'm going to make the alias www. Now it wants me to browse. So I'm going to browse for my RTS SVR. So let's pretend this is actually a web server. But when my users connect to it, I don't want them typing rts-svr.rtsnetworking.com in the browser. I want them typing www.rtsnetworking.com. So when I click OK on that, now I have my RTS SVR resolved to this address ending in 231. Now I also have an alias www, which resolves to RTS SVR, which then in return resolves all the way down to that IP address 231. To make a long story short, when I type ping www.rtsnetworking.com, 231 is the address that actually resolves to. Pretty fascinating. So we know it completely worked. Now that machine is not powered on at the moment, so that's why we get the request timed out. But from a DNS point of view, we know it completely worked because it resolved that name, www, ultimately to the correct IP address based on our alias that we set up here. So, success. If you were doing this on a device that's not in an enterprise, I'm back on my files router here, and under advanced, it has dynamic DNS and it has DNS server. I'm going to click on DNS server, and I can see all the name to IP addresses that's actually storing. And I can see the source of the IP address itself is from DHCP, although we are examining DNS. But if I scroll down, I can add a DNS entry. So this will let me just say, this device will resolve to this IP address. So if you wanted to manually define that, you could have it done manually. Just like an enterprise DNS server, these records are also automatically created. So all of these here, like this RTS mobile, I didn't manually come here and define this. It will automatically register DNS clients for you. Same as a Windows server or any appliance performing DHCP can do this automatically, or you could manually do it if you elected to. As I said earlier, in DNS, if you're in an enterprise environment, you will have a zone that's already created. So I have my rtsnetworking.com. Every client, every server in rtsnetworking.com will have a record that shows up under this zone itself. This zone is Active Directory integrated. Now we know that because that is the default type. If you are in an Active Directory environment, when Active Directory is installed, it will install DNS for you and will automatically configure an Active Directory integrated zone. You can right-click your zone and go to the properties. And in the properties, you can see the zone type. So as we said, this is Active Directory integrated. If I go to change, you could change this. If I do not want this to be Active Directory integrated, I could deselect this, and this will change from Active Directory integrated to a primary zone. So when I click OK, it says, do you no longer want this zone to be Active Directory integrated? I do not, so I will just click yes. Notice it now says it is a primary zone. But I'm going to go back to change, and I'm going to select store the zone in Active Directory again. Now, one of the notable differences, when this zone is Active Directory integrated, when I go to dynamic updates, it says none, which means I have to manually create every record. Every host A record, somebody has to right click, new record, manually created. Non-secure and secure is kind of the opposite. It means any device that points to this as its DNS server, whether it's a iPhone, iPad, Android, Windows, any device, does not matter who owns it, it would automatically create a host A record for that device in the DNS server itself. That's the non-secure and secure. So you can really think of that as like all records would be entered. Then there's a secure only. Secure only registers if you are a member of the domain. So if you have guests visiting your network or mobile devices that are not joined to the domain, they will not clutter your DNS by creating an entry. Always think of this. if I go back to non-secure and secure, imagine you are at a coffee shop. You have Wi-Fi for your customers. Your customers will point to some DNS so they can get out to the internet. You never want those records from your customers to be registered. Now, there are many ways to combat that. One, use a public DNS out on the internet, then it's a non-issue. But even if you use some internal DNS as their connection point, you could simply say either none or secure only, and you know they won't be registered because they are not a member of your domain. If I make this a primary zone, so we'll deselect store the zone in Active Directory again. Notice secure only is no longer an option. None and non-secure and secure as a single option. So either it's none or all, unless you are an Active Directory integrated zone. But again, I'm going to leave this on Active Directory integrated. Now, you can create a new zone. If I wanted to manually create a zone, I could just right-click New Zone. I'm going to choose the zone type. I'm going to make it a primary zone, so I will deselect Store the Zone in Active Directory. And I'm going to name it rtsittraining.com. And we'll click Next. It's going to create a zone file, rtsittraining.com.dns. Dynamic updates we just discussed, and we are finished. Now I have RTSIT training. So now I could create new host records, aliases, all those types of records. So you now manually have a zone that represents that namespace. Now you just populate it with all of your records. The zones we have by default were just created when Active Directory was installed, but you just as easily could manually create those as well. When I want to configure my DNS client addresses, there are two ways to do it. One is to obtain automatically. So on my client device, I could say I want to obtain automatically. If I do that, I will get an IP address from DHCP. And if I do that from my IP address, I have the option to do that for the DNS address as well. So as long as that's correctly defined on your DHCP server or your DHCP appliance, then you know your client will always have the correct DNS configuration defined. If I use static IP addresses, I can define that on the device itself. So on my Windows 10, Windows 11, Mac, whatever device you're on, you can simply enter a static DNS address. Now, typically you would always have two DNS addresses. The exception is if you're on a home network, you normally only have like one appliance. But if you're on any type of corporate network, you almost always have two. It is a best practice and recommended to have two addresses. The preferred DNS address is the address that you resolve, all your names get resolved to that address. So that is the only one that you actually use. But let's say this fails. For some reason, that server is offline, you can't connect to it. If that were to happen, then the alternate DNS server would actually be used. But the only time you would ever communicate with the alternate is if the preferred DNS server actually failed to respond. So you can think of this alternate, well, like an alternate or almost like a backup. If there's a failure of the preferred, so you can still have name resolution. Now you'll see over here, if you click the advanced button, that's what it would open up to, this tab here. I could jockey these up and down in the list. Whichever one is at the top is the preferred, whichever one is at the bottom is going to be your alternate DNS server. So you can simply just move those up and down in the environment here. Now, something that is pretty common, and I've done this in most of my environments, you have multiple DNS servers in your environment. So I would have clients on some IP networks would use this address, and this example ending in .10, this would be the preferred for many of the clients on my network. The 21 would be their alternate. So exactly the way this is configured. Then I would have another large number of clients, and they would use 21 as their preferred, and they would use 10 as the alternate. So effectively, we would be load balancing DNS. If half my users use the 10 as their preferred, the other half use the .21 address as their preferred, then each one is effectively doing half the work. But if either one of those fails, you know the remaining server will resolve names for all of your end users, and you have no disruption in the environment. You can also manage this through PowerShell. Set DNS client server address interface index, whatever your interface number actually is, and I'll show you how you obtain that in just a moment, dash server addresses. Notice that is plural. I make a mistake typing this in often of just typing dash server address, because if I look at it, that's what I see, server address. But it's plural with the ES on the end, so server addresses. Then in parentheses and quotes, the IP address, comma, the other IP address. Now, if you only want one IP address, then it's still going to be the same format. If it's just one DNS server IP address that you're actually defining, still going to say dash server addresses, even if there is just one. But typically you would have two of those actually defined. The other settings here typically will stay as default. At the bottom, there is DNS suffix for this connection, and it says register this connection's address in DNS. That means you will automatically have a host A record created with your computer name and your IP address, and you want that. So we're not changing that. That's just the default setting. And above that, append primary and connection-specific DNS suffixes. This means if your computer is joined to a domain, it will automatically append your domain name to any queries that you actually attempt to resolve. So what that means to me, let's say I have a file server and it's named file01. The fully qualified domain name of that is going to be whatever your domain name is, .com. File01, rtsnetworking.com, or whatever domain name you actually have. Now, if I'm an end user, when I browse the network in our environment, I don't want to type file01.domainname.com. I just want to type file01. This append primary and connection-specific DNS suffixes means it will automatically append that domain name to any queries that leave my device with just the host name itself actually defined. So it just makes searching and locating resources a bit easier. But that is the setting that is defined by default, so we're not making any changes to that. Normally, the only change you make if you were using static IP addresses is just to type in the IP address of the preferred and alternate DNS server in the environment. Pretty straightforward to set up overall. In Lesson 2, I'll show you how to create records in DNS, how to configure DNS zones. I'm also going to cover the concept of primary and secondary zones and Active Directory integrated zones, and we'll look at how they can be configured to replicate with each other. When I want to create records in DNS, the process is very straightforward. You would already know the types of records that you want to create. In this example, let's say what I actually have is a web server. The name of this web server is ATL-SVR1. And the IP address of this web server is 172.16.18.25. So that's the way the server is actually configured. Well, if I needed to manually create a record for this in DNS, I would simply create a new host record, sometimes called an A record we talked about earlier, sometimes called a host A record. But I would create that in DNS, and I just define the computer name, and I define the IP address that I want it to resolve to. That's all I have to do. Now, notice this does have the fully qualified domain name, and it has contoso.com appended to the end. This is the zone name. So when that zone was created, that's the name that was given to that zone. Every record you create under that zone is going to automatically have contoso.com appended to it. But I said this is a web server. If I stop right now, that would mean users either have to type in atl-svr1.contoso.com to connect to my website, or they have to type in the IP address. Neither of those is a viable solution in our environment. This is where that alias comes in, or CNAME. With this, I can say I want an alias of www. Notice it automatically appends contoso.com to the fully qualified domain name. So now www.contoso.com, I'm telling DNS is actually an alias for atl-svr1.contoso.com. So what happens now? I have an end user, and they are just browsing the web. They type in www.contoso.com. That query goes to this DNS server. DNS says, oh, that's an alias for ATL-SVR1. That rolls over and says, okay, ATL-SVR1, what is your IP address? The 172.16.18.25, that's the address that ultimately gets resolved to, and my user is now connected to the website. But the user never had to know the IP address of the website, never had to know the name of the web server. They just typed in the common alias www. There are many reasons you would use an alias. You could use these for proxy servers, telephony systems. I've seen a lot of media servers that have aliases defined. So very common for numerous reasons. You may opt to have an alias in your environment. I could also manage this through PowerShell. Add-DNS server resource record A. That A just defines the record type, so it's a host record, this A record. -zone name, whatever the name of the zone is. In my case, we'll say contoso.com. -name, this would be the name of the computer or device. -IP address, followed by whatever the IP address is for that device. So this is exactly the equivalent of creating the new host record. The add-DNS server resource record, you could create any type of record. I could create an alias, pointer record, so any type of record you could create in the DNS portal. You could also do that through PowerShell as well. To begin configuring DNS zones, I start with my namespace. So I have my rtsnetworking.com. That would be my domain name. That's going to be my DNS namespace. My forward lookup zone is going to be my domain name, RTS Networking. In that is where I would have my host A records we talked about. And again, sometimes they're host records, sometimes they're called A records or host A. But whatever you call it, we know it is name to IP resolution. So this client 1, that's the IP address of client 1. The reverse lookup is the opposite. It's going to take the IP address and resolve to the name. So IP to name. So the easiest way to think of this process, if I'm on DNS client 1, if I send a query to the DNS server and I'm trying to connect to client 2, maybe I'm going to ping that computer. I just want to connect to it for whatever reason. So I'll just try to browse client 2. That request gets passed to the DNS server. All the DNS server does is say, okay, I see you want to locate client 2. It says, okay, that's client 2, looks up the IP address and sends it all the way back to you, and you are now connected to it. A reverse lookup, on the other hand, starts with the IP address. So it goes to this 192.168.2.46. It sends a reverse lookup. That will query for that IP address and verify that it resolves to client 2. So that would be the reverse lookup. IP to name. Forward lookup would be name to IP. When you create a forward lookup zone or a reverse lookup zone, it's going to ask you another question. If we approach this from the forward lookup zone first, when you create your forward lookup, it's going to ask you which of these 4 zone types do you want your forward lookup to actually be. So we have a primary and secondary. Those will be the 2 that we focus on first. Then there is a stub and an active directory integrated. So these are the 4 zone types we have on a Windows server in DNS. The primary zone is a read and write copy of a DNS database file. Now again, think of a zone as a folder, and it just contains all your records, like your host A records we talked about, and other types. With a primary zone, I can create and delete those records. A secondary is a read-only copy. So this would be another server somewhere else. A simple way I think of this concept, let's say at my headquarters location, you have a primary DNS. You have a branch office somewhere else. We'll say BO for branch office. You decide you don't want users in your branch office to constantly cross a WAN connection to connect back to your primary, like connecting through the internet or through some service provider. You don't want that. So what you want to do is you want to put a secondary DNS server here, and you want users in the branch office to query that secondary DNS server. That makes sense. We simply have any change that originates here in the primary, it transfers to the secondary. So these two servers are identical. You create a record on the primary, delete a record on the primary, it simply gets transferred down to the secondary. With the theory being, that will be less traffic than having all the users in the branch office constantly cross your WAN connection to communicate with the primary. Now, as we will see, the primary, secondary, they are not the recommended zone types now, but there are certain situations that it may be the most appropriate depending on how you're actually configured. When we get down to Active Directory Integrated, that is going to be the most common and the preferred zone type if we meet all the requirements. But we need to fully understand how primary and secondary work so we know the advantages, disadvantages, even though most likely it's not a zone type that you would actually use in most environments. But you have to understand it to know why you may opt not to use it. The Active Directory Integrated Zone is actually stored in Active Directory Domain Services. So the domain controllers you would have in your environment actually store that information, and it replicates with Active Directory, which means your DNS server also has to be a domain controller if you want to use Active Directory Integrated Zones. But we have a section dedicated to just Active Directory Integrated Zones, and the other is a stub zone. A stub zone is a copy of a zone, but it only contains records to locate other name servers. It does not contain a full copy of a primary zone. What we will do is configure all four of these so you can see exactly how they're configured and exactly how they work. What are Active Directory Integrated Zones? Let's take a look. Active Directory Integrated Zones allow multi-master rights to the zone. So what that means to me, I can have multiple DNS servers with an Active Directory Integrated Zone, and all of those have write capability. So I could create a record on one DNS server, it would replicate that record to another DNS server, and I could delete the record from the other server. So there's not a primary, secondary concept. All of your DNS servers are equal to each other. You can create a record on any DNS server that hosts an Active Directory Integrated Zone. You could modify or delete a record on any server. Whatever change you make simply replicates to the other DNS servers. This gets replicated with Active Directory Domain Services. So the same way a user account would replicate in your environment, a computer account that you created in Active Directory, it now also replicates all of your DNS zone information and all of your records. Now, the advantages to that, I don't have to be concerned about this staying up to date. That's automatic. It will leverage the replication topology that we already use in our environment. And it only replicates changes. So it has incremental updates, meaning when replication occurs, if no records in DNS have actually changed, there is nothing to replicate. When something does change, it's only what was changed. If that's a new record, if that's a modified record, only that information would actually be replicated. And from a security point of view, one big advantage is it allows for secure dynamic updates. What that means to me, if your computer is not a member of the domain and you bring it to the office anyway, maybe it's your personal laptop or maybe it's a mobile device, you connect it to the network. When you do that, it gets an IP address from our DHCP server that tells it this is the DNS server that it needs to use. That's fine. You can have complete name resolution. You will be able to resolve names on the internet, possibly even names internal, depending on how things are configured. But what the enable secure dynamic updates will actually do is not allow a record to be created for a device if that device is not a member of the domain. So any computer that's in a work group, any mobile device, full name resolution, but I won't clutter my DNS by having records for devices that are not members of my Active Directory domain. Now, you can turn that off. If it's decided we want every device to be registered, then you can disable these secure dynamic updates. We have some other options we'll see we can configure, but the secure dynamic updates are unique to Active Directory Integrated Zones. That's the only zone type that actually allows for the secure updates. What is a stub zone? A stub zone solves one of the problems that we had with the primary-secondary concept. When I have a primary zone, every record will transfer to the secondary without exception. So if you have 1,000 records in your primary, you have 1,000 records in your secondary. The downside is most of those records would be for like client computers. You have a handful of servers, but the majority would be clients. So I'm transferring 1,000 plus records. I'm transferring any changes to those records every few minutes, but the records that are being transferred are probably records I don't really care about because they are these client records. A solution to that problem is a stub zone. So let's say here, I have contoso.com, and I'm going to say I have 5,000 records in this contoso.com root domain. Then I have the North America, South America, and let's say each of these has 1,000. Then I have the New York.NorthAmerica.contoso. We have the Rio, and I'm going to say these have about 1,000 as well. Then over here we have Fabricam, and I'm going to say that has 2,000 records, and over here we'll say 500 records. So that's a lot of records. If I am here in the New York.NorthAmerica.contoso.com, if I need name resolution for all of these other domains, now if we think about this from a primary zone, secondary zone point of view, that would mean my DNS server here in the New York domain, it would actually have to have records for all these other domains. So I would have 5,000 from the parent, 2,000 from Fabricam, 1,000 from the South America, North America, 500 from the North America Fabricam, and then you keep all those records up to date. That is not efficient. I won't be resolving names in these like every minute of the day. I want name resolution, but I don't want to house every record and then keep it up to date for all of these domains in the forest. That's where my stub zone comes in. What's interesting with the stub zone, when I create a stub zone, the stub zone only has records for the DNS servers in other domains. So from my point of view here, I would have all the DNS servers in the root domain, that contoso.com. So now, anything I want to resolve in contoso.com, when my user, say, browses something from their computer, they use the DNS server in the New York domain. That DNS server says, yeah, I don't know what that name actually resolves to. That's not a record that I store. So what happens, it actually contacts one of the DNS servers in the root domain and says, I need this name resolved. That DNS server will look up the name, find out the IP address it resolves to, and return that information. The end result is I get full name resolution through my entire Active Directory forest, but I don't have to store records for all the computers and all of these different domains. I just have what amounts to a master list of DNS servers for all the other domains. That is a stub zone. Only contains records related to DNS servers in other domains, so you can have name resolution across all of those domains. One of the easiest things to do with a DNS server is to have name resolution through the internet. It's easy because it's automatic. All DNS servers come with a root hints file. If you are on a Windows or even a Unix DNS server, there's actually a file named cache.dns. This file, cache.dns, it contains all of the root servers for the internet. Now, surprisingly, there are only 13 root servers for the internet. Now, they are highly available, so they would be in these massive clusters. But if you look at them, they are considered to be A through M, so just 13 of these root servers. Well, every DNS server has a file that has the IP addresses of all of these root servers. So the way root hints actually work, if I want to connect to Microsoft.com, and let's say Microsoft resolves to the IP address 86.42.97.5. We'll pretend that's the IP address of Microsoft. Well, when I want to resolve that address, from my client computer, I just type in the URL, Microsoft.com. So I type that in the browser. My computer has no idea what that is. So what my computer does is it looks at the preferred DNS server address and it will pass that traffic to the DNS server to be resolved. It's going to send what's known as a recursive query to the DNS server saying, DNS, I need you to take this name and resolve it to an IP address for me. Well, the DNS server, let's say my domain here is contoso.com. This DNS server says, well, I only have records for contoso.com. I have no idea what the IP address is for Microsoft, so I can't directly resolve that for you. But what I can do is look in my root hints, and I'm going to pass this to one of my root servers to be resolved. So this DNS server I have in my environment simply queries the root servers. The root servers have a list of all the top level domains in the environment. So the root server will query the .com namespace because the URL I'm trying to connect to is Microsoft.com. When it queries the .com namespace, it's going to get a list of all the DNS servers that host the .com namespace, and it's going to pass a query to one of those servers saying, can you look up the Microsoft.com IP address for me? So it simply looks up the Microsoft.com IP address, determines that is this 86 address I have here, and that gets passed all the way back to your client. Now, the beauty of this is it's automatic. Every DNS server works this way. The only thing I need to make this work is an internet connection, and my client needs to use those DNS servers as the preferred DNS, so traffic gets passed to it. But that's it. You're going to have full internet name resolution no matter what. The way root hints work, I can simply click on my server, and there's a root hints that shows up. Now I could click on that here and open it, or if you right click your server and go to properties, you'll see a root hints tab that shows up. This is always populated by default. So these are all the root hints that exist, A through M. It appears there are only 13, but they would be geo-clustered, so they're highly resilient. So not concerned about failure of those, but this root hints is always populated. Now, where this actually comes from, if I just browse through my server here, I'm going to go to cwindows/system32/DNS. So cwindows system32 DNS. There is a file present on all DNS servers named cache.dns. I'm going to open this with Notepad. And you'll see it has those list of servers that you can read in clear text. So I can see the IP version 4 address, IP version 6 address of each of those servers in the list. So when we look at the root hints tab here, all you're seeing is that file that was installed when DNS was installed. It just populates this tab with your list of root hints. So now, as long as this server has internet access, that's it. A client can point to this as its primary DNS server, and it's going to resolve directly through the internet those names because it'll just query the root hint servers. Pretty neat overall. An option that is generally considered to be a little more efficient than using the root hints is to use DNS forwarding. With DNS forwarding, we would use an external DNS server. This is actually the IP address of the Google public DNS. One of their IP addresses. They have multiple. But 8.8.8.8 and 8.8.4.4 are the two common addresses you see for the Google public DNS that anyone can use. Now, the way forwarding actually works, I try to connect to Microsoft.com again. My client does not know how to resolve that name, so it simply passes it to the local DNS servers I have on my network. I configure my DNS servers here to forward all traffic to the IP address 8888. So now what happens? Anything that is external, assuming I am here in contoso.com, any query passed to these DNS servers that is not for contoso.com would simply get forwarded to this 8.8.8.8 address. Now, onus is on the Google DNS to do all the lookups. it can contact the root servers on my behalf and go through the entire name resolution process. I am done at the point I forward traffic to this. I simply wait for a response. Now, the reason that this is considered to be more efficient, this public DNS is used by millions, tens of millions, maybe hundreds of millions of people. So the cache repository on this DNS server is enormous. So most common names like a Microsoft.com or anything like that you want to resolve, someone else has resolved that name shortly before you, almost certainly, because so much traffic goes to this, that what happens is when that query gets up to this Google DNS server, it simply looks in cache and says, oh, I already know what it resolves to. I don't have to query the root or go beyond that. It simply returns that response to you. Where the root hints we saw, not quite as efficient. So that is why forwarding is so common. Now, for fault tolerance, you can use a forwarder, and then you can also say, if my forwarder is not available, then I want to use root hints as like a fallback option, so you're not creating a single point of failure just by using forwarders. So either I can use root hints, or I can use DNS forwarding to resolve external names. To configure DNS forwarding, you can right-click on your server and go to Properties, and there's a Forwarders tab that shows up. On the Forwarders tab, you can edit, and you can just type in the IP address of the DNS server you want to forward to. A very common server is 8.8.8.8, which is one of the IP addresses of one of the Google DNS servers. So if I put that address in, now my machine here does not have internet access, so it's going to give me this little red circle with the X in it saying it can't actually resolve that. But what happens now, I'm going to slide this over. Actually, I'm just going to OK on that and OK on this. Right now, I have a zone for rtsittraining.com and a zone for rtsnetworking.com. If you try to resolve something in RTS networking, then that query gets sent to the DNS server. It's going to go to this zone, and it's going to look for that record in the zone. Same for RTS IT training. So if it's pc1.rtsit training, it's going to go to that zone and look for the record. Now, if you are trying to connect to Microsoft.com, Yahoo.com, any public website, that query goes up to your DNS server and it says, oh, I see the query is trying to resolve something in Microsoft.com. Says, I have no zone from Microsoft.com. So then it moves over to the Forwarders tab, and it will simply forward that request to whatever is defined here on the Forwarders tab. Now, if you don't have a forwarder actually defined, which you would manually need to define, but if you've never done that, then it would have gone directly to the root hints. So forwarders would always be queried prior to root hints. Now, if you add a forwarder here, and that forwarder is unavailable, there's some type of issue and that forwarder is offline and it can't be contacted, then this little check at the bottom, use root hints if no forwarders are available, as a failover. Instead of just giving you an error message, it would then attempt to use root hints if it can't contact your forwarders. And you can also add as many forwarders as you want. Another Google server is 8.8.4.4 is another Google DNS. So you can add as many of those as you want. And it would always query the first one. If that does not respond, it would query the second. If that does not respond, as long as you leave this checked, it would then roll over and use root hints. So you would still have external name resolution. So pretty neat overall and just very straightforward to set up. Just define the IP address of the DNS server that you wish to forward to. Module 4 is Understanding IP version 6. In this module, we will cover an overview of IP version 6 addressing. We'll look at how to configure an IP version 6 host, how to implement IPv6 and IPv4 coexistence, and how to transition from IP version 4 to IP version 6. Very interesting topics. In the first lesson, we will look at why you would use IP version 6. Then we'll cover the differences between IP version 4 and IP version 6. I'll go through an overview of IP version 6 addressing. Then we'll look at the address structure, the types of IP version 6 addresses, and we'll look at the options for configuration, whether that's manual or the auto configuration options that exist for IP version 6. A common question is, why would you use IP version 6? You have IP version 4 already running, it works fine. Why would I ever need to switch to IP version 6? The short answer is, you may not need to. IP version 6 will primarily benefit internet service providers that are issuing public IP addresses. Since so many devices now connect to the internet, we just need more public IP addresses. However, you can use IP version 6 internal as well. Some considerations. Organizations should consider IPv6 because of the exponential growth of the internet and the fact that at some point we will exhaust all IP version 4 addresses. But again, that is related to public IP addresses, which are typically assigned from your internet service provider. The need for a more simple configuration. IPv4 is pretty simple to configure, but IP version 6 has some unique configuration options that can eliminate the need for DHCP and still have addresses automatically assigned. That we do cover in this lesson, but compared to IPv4, it can have a more simple configuration. One of the most important, the requirement for security at the IP layer. IP version 6 has an encryption protocol, IPsec, natively built into it. So when I use IP version 6, based on what I'm actually sending, at the protocol level, it'll just decide, oh, this should be encrypted, and it just encrypts it. If you use IP version 4 and you want IP version 4 traffic to be encrypted, you have to manually configure encryption policies yourself for that to happen. So that is a huge, huge benefit and can be a deciding factor of an organization implementing IPv6, just the added security benefits. Better support for real-time delivery of data, known as quality of service, or QoS. Many people just call it QoS, but quality of service. The example I often use for quality of service is having an IP telephone. It is very common that if you go into a corporate environment, you'll see an IP phone on the desk, like Cisco or some other vendor, but it's an IP phone. And when I say IP phone, I mean the phone has a network connection on it, and it plugs into like an Ethernet cable the same way as a computer could. So that's an IP-based phone. It communicates over your IP-based network in the environment. Well, it's very common that if you look at an IP-based phone, you'll see there's an Ethernet cable that runs from the phone to the jack in the wall. From the computer, there's an Ethernet cable that runs from the computer and it runs to the switch port on the phone. So essentially, they are daisy chained to each other. So I have, well, we'll say this is the wall in our office. I have my RJ45 Ethernet jack here. Okay, that's supposed to be a phone. I just have an Ethernet connection. So my phone is now directly connected. My PC, the Ethernet port on my PC, can simply have a cable that runs to the Ethernet switch port on the phone. So now they are daisy chained with each other. Now, we do not at all care that they're daisy chained, but what it makes very clear, if you are making a phone call, all the traffic has to go through that cable, and then it runs, through the wall and goes back to a closet somewhere through routers, switches in your environment. Well, when I'm surfing the internet, all the traffic from my PC goes through that cable, goes through the little switch port in the phone, and it goes through this same connection. So it just makes it a clear illustration that my voice traffic and data traffic are going through the same physical cables, same physical devices. Well, the concern, if I am streaming something on YouTube, maybe the World Cup is on, and I'm streaming that online, and it is using a lot of bandwidth in the environment, and I have a lot of coworkers that are streaming the World Cup as well when they should be working. That's what they're doing. The concern, we may have so many people streaming the World Cup at the same time that our network gets saturated because there's too much traffic on it. The concern is, now, if I try to make a phone call, my phone call may have gaps of silence. They call that like a dirty line, but you may hear just gaps of silence. Sometimes you hear static, or your call entirely disconnects. It's comparable to having a bad cell phone signal. Well, that's my concern. I cannot have my phone calls drop because there's too much traffic on the network. So what we've always done in the past is we would go to our devices, like routers and other network devices, and we would create these quality of service policies. Now, voice traffic is a different type of traffic from data traffic. So we would create a policy, and that policy would give a higher priority to voice traffic, and it would give a lower priority to data. So if this network ever does get so congested that some traffic has to be discarded, it knows that a phone call has to be real time and it would never be discarded. Instead, it would discard data from the PC because that can be reset, it can tolerate delay. What's neat about IP version 6, the quality of service capability is natively built into the protocol. So it can identify a voice phone call versus data, and it automatically gives preference to the voice over the data. So it can eliminate the need for me to go configure these quality of service policies on all my hardware network level devices in the environment. So those two things are considered to be game changers. Natively, it can encrypt traffic with IPsec without any configuration from me. You're not even aware it's happening. It just does it on its own. And quality of service, but again, you're not aware it's happening. There's nothing for you to configure, just the way the protocol actually works. Some of the most common differences between IP version 4 and IP version 6 will be the address length. An IP version 4 address is only 32 bits. An IP version 6 address is a whopping 128 bits, so an enormous increase in just the size of the address itself. In DNS, we have these A records, sometimes called a host record. That resolves a name to an IP version 4 address. For IP version 6, they are quad A records. Still just takes the host name and resolves it to the IP address, but it resolves it to the IP version 6 address. The most common difference you would ever see is the number of IP addresses available. An IP version 4 address is giving us 4,294,967,296 IP addresses. That is in total. No, that's a lot. 4 billion plus addresses. When we go to IP version 6, we get 340 undecillion IP addresses. Not often do you even hear the term undecillion. Worded another way, it's 340 trillion IP addresses. Or as I prefer to say, a lot. More than we would actually need. Now, to numerically look at that 340 undecillion, this is what it would actually look like, typed out. So that's 340 undecillion. That's why I prefer just to say it's a lot of addresses. To look at the breakdown of an IPv6 address, this represents the 128 bits that make up an IP version 6 address. An IPv6 address is broken down into 8 16-bit blocks. So just each of these here just represents one of those blocks. Now this is in binary, just ones and zeros, just to give us a representation of the 128 bits. The IP version 6 address itself is always going to be converted to hexadecimal. Sometimes it's called base 16, but usually just referred to as hexadecimal. This is an example of an actual IP version 6 address. FD00, 0DB8, all zeros, 2D4C, all zeros, 00DD, 1122. Now, you see the problem that could create. Imagine trying to ping an IP address and you have to type out that entire address. Or you're trying to support a user and you've asked a user to run ipconfig and read the address back to you. That's going to have some typos in it if I'm typing it in. So you will normally never see an IP address that long. IP version 6 uses a process called leading zero compression. What leading zero compression actually does is remove, you guessed it, leading zeros and contiguous zeros. To look at how that process works, FD00, then I have 0DB8. This is a leading zero. So I can simply remove that. FD00 colon DB8, the leading zero has been removed. That's the way it would be represented. Then notice I have 2 blocks of all zeros, I can remove all contiguous zeros. Does not matter how many blocks it actually is. They can all be removed and represented by a double colon. So this double colon counts for all contiguous blocks of zeros. Then I have 2D4C. So no leading zeros there. So that drops down exactly the same. Then up here, I have another block of all zeros. This is going to be represented by colon 0 colon. The reason this cannot be a double zero, the reason this cannot be a double colon, imagine if it was. We'll see why that's not allowed. You would no longer know what the IP address is. FD00DB8 double colon, 2D4C double colon. You would have no way to know if this represented 2 sets of zeros and this represented 1 set, or if this represented 1 set and this represented 2, which would completely change the IP address. So for that reason, you can only use a double colon 1 time. Now, you may be thinking, how do I know how many blocks that double colon represented? Well, if you look at the IP address, we have 1 block with the FD. The DB8 is block 2. The 2D4C is block 3. The colon 0 colon represents block 4. The DD represents block 5, and the 1122 represents block 6. There are 8 blocks total, so 2 are missing. So instinctively, we know this double colon here represented 2 blocks of zeros. To finish the address, I do have this 00DD. The 00 gets dropped, so it shows up as DD. And then at the end, we have just 1122. So this is the address that you would actually see. That's the address you could type in. If you want to ping the address, that's the address you would actually use. So that is our leading zero compression. Again, the rules to this, leading zeros are automatically going to be omitted. Contiguous zeros can be represented by a double colon, but that can only be used 1 time. If you have any other blocks of zeros, they have to be represented by colon 0 colon. Now let's compare some of the common structures of IP version 6 to IP version 4 addresses. In IP version 4, you are considered to have an IP address of 0.0.0.0. If your address is unspecified or undefined, you will temporarily have that address of all zeros. The equivalent in IP version 4 is just colon colon. Now, normally you never see an unspecified IP address, because if you are even set to obtain an IP address automatically, then you would have one generated through that automatic private IP addressing, or a PIPA we talked about. Normally, the only time you would see an unspecified IP address is if you have tried to use an IP address already in use. For example, if I have a computer and its address is 10.1.1.42, maybe that's a dynamically assigned IP address to one of our clients. I bring my laptop into the office and I try to set a static IP address on my laptop, and I use the address 10.1.1.42. Well, that's a mistake because that address is already in use on the network. But when I set it on my computer and click OK, I will get a message that says duplicate IP address exists on the network. And since that address already exists on the network, they don't want to disrupt the device that already has the address. So even though I type this in my properties, my computer will actually use address 0.0.0. In IPv6, same concept, works the same way. It would just be represented by double colons. So normally this is not an address you ever see unless you have some type of misconfiguration. The loopback address for self-test, if I just want to test my network adapter, IPv4, 127.0.0.1, and IPv4, it's colon 1. Now, we know what that means. With that colon 1, it ends with 0001. These leading zeros are dropped. And then we had the 7 blocks were all zeros. I won't bore you by writing out all the zeros, but we know all the zeros we had in each of these. From the previous example, this would be all zeros to the entire IP address. The very last number would be a 1 if you typed it all the way out. So all those zeros get omitted, and it just comes up as double colon. And these 3 get omitted, so it just shows up as 1. So colon, colon, 1. But that leading 0 compression is why it looks that way. Our auto-configured address for IP version 4, the APIPA, automatic private IP addressing, is always 169.254 is the network ID, last 2 numbers random. It's always FE80 in IP version 6. But it works on the same principle. Your computer is set to obtain an IP version 6 address automatically. Nothing assigns you an IP version 6 address. Maybe you don't have DHCP configured for IP version 6. So even though you're set to obtain automatically, you do not get an offer for an IPv6 address. So your computer will just generate its own FE80 address. Now, in IPv4, we call it a PIPA. In IP version 6, I don't know why they just don't call it a PIPA, but they call it link local. But it serves the exact same purpose as a PIPA for IPv4, just different names. We have 3 types of IP version 6 addresses. One is a global unicast. This is the equivalent of a public IPv4. That's what I always think of it as related to. A public IP version 4. Global unicast is always used on the public internet for IP version 6. A global address also will always start with a 2 or a 3. Most you see will start with a 2, but some will start with a 3. But always a 2 or 3. We also have a unique local address. This always starts with an FD. Actually, I'm going to put that down here. Unique local, FD. This type of address is equivalent to a private IP address. If we were talking about IP version 4, the exact equivalent. It is only used on your internal networks, and it can route within your environment, but it cannot directly connect to the internet, is not internet routable. So effectively, they're the public and private addresses in the IP version 6 world. They just have completely different names. Then we have the link local. The link local is always going to be FE80 colon, then just random numbers, but always FE80. This is the equivalent of the APIPA, automatic private IP addressing, for IPv4. DHCP did not give an IP version 6 address, so your computer just generated its own address. One thing I like about IP version 6, once you understand IP version 4, you understand IP version 6, because the concepts carry over. They just have new names. But for the most part, I mean, an IP address is an IP address, so they are far more similar than dissimilar. Not as different as it appears to be. Many people see that they're hexadecimal and just assume it's something that's going to be incredibly complicated, but it is not. To look at the breakdown of an IP version 6 address, this is an example of a global unicast address. As I said, they are routable on the IPv6 internet. They can be subnetted. There are 16 bits available if you need to break this down and create multiple subnets. And they do begin with a 2 or 3. So the breakdown for your IPv6 address, it's pretty impressive. The first thing to notice is this interface ID. That interface ID itself is 64 bits. The interface ID is the unique portion of the IP address that is assigned to the client. Just that unique interface ID for your client is twice the size of an entire IPv4 address, which was only 32 bits. So that's how we get this 340 undecillion IP addresses, just a large interface ID that can be assigned. The 16 bits here could be used for subnetting. So if you wanted to create subnets within the environment, you could only subnet those 16 bits there near the middle. You cannot subnet into this interface ID. That is a 64-bit block for all of time. Nothing you can do to subnet into that. The 48 bits here that remain, they are all for routing. The first 3 bits here, this is managed by IANA, the Internet Authority for Names and Numbers, so that's just assigned. And the 45 bits here will be assigned by your internet service provider. So like getting a public IP version 4 address assigned, you really can't do much with it. Most of it's controlled by your ISP. Same is true here. So there's nothing that we can do with the first 48 bits. If I want to subnet, it's really bits 49 is what this would be, through bit 64 would be the bits you could subnet. Then the 64 bits that remain are your interface ID, unique to your client. Unique local addresses are equivalent to IPv4 addresses. They require the organization ID to be randomly generated, and we'll see that here, the organization ID. So a similar breakdown as to the global unicast we just saw. You have 48 bits here that will be unmanaged, really. 16 bits are allocated for internal subnetting. So just like the previous one, you have an interface ID of 64 bits, unique to your client. If you want to subnet, it's just these 16 bits here near the middle. As we said before, bits 49 through 64 would be the bits that you could use for subnetting. So just a different purpose. And it does always begin with FD. Now, the most common address you'll ever see with IPv6 presently is link local. Automatically generated on your IPv6 host. They serve the same purpose as a PIPA for IPv4. We just said that a moment ago. What's unique here is this has something called a zone ID. The zone ID identifies the interface. Now, the reason this is important, many computers have more than one interface. Many laptops have an Ethernet port, and a laptop is going to have a wireless card as well. So you get assigned an interface ID for each interface in the device. And each of those interfaces will get an IPv6 address. So you can see here, let's say this top one is my wired. It's like an Ethernet connection. And the bottom one is my Wi-Fi connection, or adapter, I should say. Both have IPv6 enabled, and both are set to obtain automatically, and they generate these link local addresses. Each one is going to have a percent number behind it. That percent number is the zone ID. The number means nothing. You'll look at this on one computer and it may be percent 13, it may be percent 12 on another. That number, there's no significance behind what the number is. You cannot look at that and determine if it's a wired or wireless. It is just a unique identifier that's assigned to the network adapter itself. So you'll see that show up. And as we said, always FE80 is what my link local address will actually start with. IPv6 has some unique auto configuration capabilities that do not exist with IPv4. When I bring my IPv6 client online, say you power it up, the first thing it does is derive a link local address. That is the FE80 address we talked about earlier, equivalent to the PIPA address for IPv4. Once that's done, my client will check for any type of conflict using neighbor solicitation. So it's going to make sure there's no conflict with any other device using that same address. It would be nearly impossible to have a duplicate address that would cause a conflict simply because there are so many possibilities for IPv6 addresses. So that's unlikely, but it always checks just to make sure. If there is a conflict, it simply will use a different link local address. At the third step, it will check for a router on the network. Now that router has to be running IPv6, so we'll call it an IPv6 router. Technically, there's no such thing as an IPv6 router, but you will see this term in a lot of documentation. All it means is the configuration on your router allows you to set IPv6 addresses. It means nothing more than that. Well, what's unique though, it will check the router for prefixes. If the router has an IPv6 address assigned, then what your client can do is add those prefixes to itself. Now, think of a prefix as a network ID. So if this router here has some, we'll say FD00:1234, it has its address. My client will look at the network ID of that address and it will set the same network ID for itself. Whatever that address is. That puts it on the same IP subnet. Pretty interesting. Has that capability. Once it adds the prefix, it's going to generate its own unique interface ID, which is the host portion of that IP address. But once that happens, This has a valid IP version 6 address, and I do not have a need for DHCP on my network to lease IP version 6 addresses. My client will automatically set an IP version 6 address that logically places itself on that network IP-wise, and it'll have full communication. But I do have one more possible step. There are two flags that exist, a managed flag and an other flag. Now, they're just called an M flag and an O flag is normally the term you actually see. Depending on what those flags are set to, I can have this automatically query DHCP. So instead of using the IP address based on the prefix of the router, it'll just go query the DHCP server, and it'll lease an address from the DHCP server. With these flags, if the managed flag is set to 1, then I have told the client that I want it to set its address based on the prefix of the router. If you have set this to 0, you've told your client that I don't want you to set your configuration based on the router. I want you to go out and query DHCP or find an address somewhere else, but don't set it based on the prefix of the router. The other flag, the O flag, if that's set to 1, then you can have this router configured with information like the DNS server address that should be used. If that's set, the client will read that information from the router, and it will set its entire IP configuration based on that information. So now it has an IP address, the correct prefix, it has a default gateway assigned, it has the correct DNS servers assigned, so it fully participates on your network with a unique address, and you did not have a need for DHCP. If that flag is set to 0, then you're telling clients, don't get that information from me, you would also get that information from DHCP. And then you would be using DHCP to lease addresses as if it was an IP version 4 network. Now, if you do not have a DHCP server, maybe your router supports IP version 6, but you never configure IP version 6 on it. These flags are always, well, really, they're undefined by default, the equivalent of a 0. So if you just throw a router on the network and you don't do anything to it, it's not going to have your client assign prefixes or anything like that. Your client would have that FE80 address, and that's the address that would remain on your client unless you configure the router with that additional information. Now, if you have a DHCP server in the environment and you have no IPv6 router, then it's still going to check for a router. It's not going to find one. It would then just query the DHCP server and lease an address from the DHCP server. So this IPv6 router configuration here, I just always say that's optional. Like if I'm going to use a DHCP server to lease these IPv6 addresses, then I have no need to go to the router and configure flags or anything like that on the router. Just leave it the way it is out of the box, undefined, and you're going to lease your address from DHCP. Pretty fascinating. Configuring IP version 6 addresses is the same process as configuring IP version 4 addresses. When you go to the IP settings, you can choose to obtain an IP address automatically on your client. You could use a static IP address and you just type in the IPv6 address. The prefix is exactly the same as a subnet mask. It's just called a subnet prefix length. You type in the default gateway. You can have your DNS servers obtained automatically, or you could use manual or static DNS servers. You just type in. The only difference is you are typing in IP version 6 addresses in the hexadecimal format instead of IP version 4 addresses, but the process is exactly the same. If we go to the DNS tab here, if I use static DNS servers, they show up here. You could have, ideally, you'd have at a minimum 2. Whichever one you define first is your preferred DNS. Your second server you defined would be your alternate DNS. You can move those up and down if you want to change the preferred and alternate, same as IP version 4. You can append your DNS suffixes. So whenever you do a search, your domain name would be your suffix, would be appended to any type of search that you do in the network itself. If I want to use DHCP, as long as you use Windows Server 2016 and newer, which everyone would now, it supports IP version 6 by default. You can configure DHCP by creating and configuring scopes for IP version 6. You define all your scope options. Same configuration as IP version 4, you're just using IP version 6 addresses. On the DNS side, DNS for IP version 6 is supported in Windows Server 2016 and newer. Has full support for IP version 6 by default, so no special configurations or anything like that. Computers or your DHCP server can register those quad A records that we discussed earlier, which just resolves your actual host name of your computer. It takes that name and resolves it to your IP version 6 address. So those records will automatically be registered in DNS. You can also manually create records, same as we could when we were talking about the A records for IP version 4, so automatic, which would be through that dynamic configuration, or manually create records. You do need to create and configure reverse lookup zones. That is true no matter what. IPv4 or IPv6. You do not have reverse lookup zones in DNS for those, so that always has to be manually defined in the environment. And they are technically not a requirement. Your network works fine without a reverse lookup zone, but it is recommended that you do because overall it can increase security in the environment, but not a technical requirement. What are node types? When you talk about IPv4 and IPv6, node is a term that comes up quite a bit. I can have an IPv6 only node. What that means, someone has went to the network adapter properties here, and they have deselected the checkmark for IP version 4. So this computer has no IP version 4 address, only an IP version 6 address. If you disable IP version 6 on your computer, then you are considered an IPv4 only node. But it is nothing more than selecting or deselecting checkboxes at the network adapter levels to change your node type. Nothing more than that. By default, IPv4 and IPv6 are enabled. So your client by default is actually both an IPv4 and IPv6 node. There's some interesting things to know when we have both IPv4 and IPv6 configured. Windows Server 2016 uses a dual IP layer that supports IPv4 and IPv6 in a single protocol stack. Now, even though they're in a single protocol stack, because it's a dual IP layer, one has nothing to do with the other. Meaning if you have a corruption in the IPv4 protocol itself, that does not affect IP version 6. And the opposite would be true. If there is a problem with the IPv6 protocol itself, it does not in any way impact IP version 4. DNS records required for coexistence. We a few times have already mentioned these host records. Sometimes it's host, sometimes it's A record or host A, all used interchangeably. They are synonymous terms. But we need those host A records for IP version 4 nodes. Just resolves the name to IP address. We've also said several times IPv6 will use these quad A records, resolves the host name to IP version 6 addresses. Both of those can be automatically created in DNS. Reverse lookup pointer records for IPv4 and IPv6 exist. In our reverse lookup zone, we have pointer records. You would have a pointer record for IP version 4 and for IP version 6 as well. An interesting fact is your computer, if you have IPv6 and IPv4 enabled on your computer, which is done by default, and you have another computer and it runs IPv6 and IPv4 as well. If I try to ping from one computer to the other, my computer will actually use IP version 6 first. So computers with both enabled will communicate using IPv6, not IPv4. Now let's say the computer, I'll call it computer Bravo, it does not have IP version 6 enabled. My client computer does not know that, so it still briefly tries to use IP version 6. No response comes back, then it will use IP version 4 to establish the connection. But since we're using dual IP layers, it has to use one before it can use the other, and it just defaults to use IP version 6 first. An example of that, in my command prompt here, I'm going to ping a computer on my network. Test dev is one of my computers. Notice it comes back with the FE80 address. We know that is the link local address for IP version 6. So that is communicating using IP version 6. If I want to ping using IP version 4, I can just put -4. This will force ping to use IPv4. So ping test dev, name of that computer -4. Now it comes back with the IP version 4 address. So my computer sent that ping, that ICMP echo request using IPv4, and the reply was using IPv4. Most networks still use IPv4 internally. There are a few reasons for that. Some things you have to consider when you are planning to use IP version 6 in your environment. Do all of the operating systems you use support IP version 6? That would be on your different types of computers, laptops, desktops, Windows, Linux, Mac. If you have mobile devices, do all those devices, do their operating systems support IP version 6? Now, today's world, they do. Any device you get that's IP based today, the operating system is almost certainly going to support IPv6, but you would still want to be aware of that. Do all of your routers and firewalls support IP version 6 configurations? Again, if it is a recently acquired router or firewall, it does. Other network devices in the environment, this would include devices you may not even think of. If you have like smart card readers in an environment where you have to swipe a badge to get in the door, those devices have IP addresses. Do those devices all support IP version 6? Typically, those devices are rarely upgraded. It would normally, when it fails, it would be replaced with a newer device, but they have a singular purpose. So some of those types of devices may not be IP version 6 compatible, so you'd have to check all those devices as well in the environment. Applications. The applications you use, do they support IPv6? Again, most newer applications do. And if you have any custom applications, this is probably the largest issue here. But if you have custom apps, and many companies do, many custom applications were designed for a very specific purpose, and that purpose in the company does not change. So you may have applications that are a decade or more old that have only had minor reconfigurations performed on the applications themselves. So any custom apps, we would have to make sure they do have support for IPv6. And the only way to know that with a custom app is through extensive testing in the environment. IP version 6 has been around for a long time. It was actually released in the year 2001, and it was fully supported by Windows XP Service Pack 1. So this is not a new protocol. Many people did not even know that IPv6 existed until around the Windows Vista Server 2008 timeframe. When they were released, they had support for IP version 6 natively built in. Even for many IT people, that was their first exposure to IP version 6. The reason this took so long to implement, there was initially not a way to coexist with IPv4 and IP version 6. If I had an IP version 6 address on my computer, I could only talk to other computers with IPv6. If you had IPv4, you could not communicate with me. So essentially, you had split networks, is what you would have had if you had deployed IP version 6. The solution to that issue is tunneling. So we have some technologies that we can use, and it gives me the ability to take an IP version 6 packet and tunnel it inside of an IP version 4 packet. The benefit to that is you can now send IP version 6 traffic, tunnel it over IP version 4, and you can communicate using IP version 6 through an IP version 4 network. The process is actually pretty simple. It is no more involved than taking your IP version 6 packet we have here. You have your IP version 6 header. That's going to have like the source IP version 6 address is added to the packet. The destination IP version 6 address is added. All it does is take that entire packet and it puts an IP version 4 header on it. So it has IP version 4 routing information in the header. Now, when I use IP version 6, I can now route that through an IP version 4 router. It can go over what we refer to as the IP version 4 internet. When it gets to the other side, it can be stripped off, and it is now just IP version 6 traffic. If we look at this example here, this is an IP version 6 client. This is an IP version 4 network, but this client, we'll say, uses IP version 6. What happens My computer here sends all its traffic in IP version 6 up to the router. The router then takes that packet and puts on the IPv4 header, routes it using IP version 4, and when it gets to, in this example, when it gets to the client, that header is removed. So this could be done at the actual client level, or you could have another router here in the network that would remove that and then have it routed as IP version 6 traffic. So a few different configurations possible, but it is nothing more than putting a header on an IP version 6 packet.